വിട്ട് താമസിച്ചു. Oh, okay, Professor.
Yes.
Hello, Professor.
Yes.
Good morning to all. Good morning to all. In fact, we have a little bit late due to the absence. I found that the Professor Victor Babu has already. In fact, yesterday I mentioned him, but he has not replied. Whether and we have to put his name as the chair. But now I invite Professor Bhattacharya Lu to chair the session of our great Professor Dilip Ghosh. Since he is also in the area of design of experiments. Professor Bhattacharya Lu is already, in fact, both are known to the participants, but even then Professor Bhattacharya is a professor from the Osmania University, and he is also an expert in the area of design of experiments. And we have a giant in the area of design of experiments as the Professor Ghosh. So to chair this session, I think Professor Lu is relatively better in this group. Especially.
Okay, thank you.
Thank you, Professor Satish Kumar sir, and for giving this opportunity. Good morning, Professor Ghosh. Now, it is a great pleasure to me to introduce the Professor D.K. Ghosh. So, Professor D.K. Ghosh did his the graduation and post-graduation from Bhagalpur University, Bihar, and PhD in statistics, specialized in design and analysis of experiments from ISI Delhi under Professor Aman Das. Professor Ghosh worked as professor and head Department of Statistics, Saurashtra University, Rajkot since 1986. Presently, he is assigned as the UGC BSR Faculty Fellow after his retirement. He holds the positions the Fellow of the Royal Statistical Society, ex-professor and head Department of Statistics, ex-in-charge professor head Department of Mathematics, and the post-graduation diploma in hospital management, the ex-coordinator, and ex-in-charge professor and head for the Department of Human Right and International Humanitarian Law, and also worked as IQSC director and adjunct professor of Banastali University, Rajasthan, and fellow of the Gujarat Science Academy.
मैं 50 के बाद आऊंगा
Sir is also hold the many positions. He also involved in many of the research projects and research investigator in Bhagalpur University during the period 1976 May to September, and research fellow of Central Marine Fisheries Research Institute, Cochin, and the junior scientist assistant Takla Experimental Research Institute, the CSIR, the Jorat in Assam during the period of 1978 to 81, and worked as senior research scholar of the CSIR during 81 to 84, and also having more than 150 publications of reputed journals in national and international, and he produced around 43 PhDs, and he is author for the 3 textbooks related to the distribution theory and factorial experiments and biostatistics, and also he is involved in the chapter publications of the 4 the academic and also he is involved in many of the other the abroad countries also visited, and he delivered many of the invited talks in various national and international conferences, and also the member in various the statistical societies like Gujarat Statistical Review, Assam Statistical Review, and Bulletin of Pure and Applied Sciences, OpSearch, and Indian Statistical Association, and so that he's having more than 20 the journals. He's involved as a editorial member or board member, and also the reviewer for various the articles, and he's also a professional membership in various the statistical bodies like Indian Society for Agriculture Statistics, ISPS, Gujarat Statistical Society, and Sankhya, and also involved in many of the committee members. Now I request the professor to
good morning, sir.
and it is very great pleasure to me.
9:50, actually, I have one talk now
Yeah.
at conference, international conference. 9:50 will be over. I will come 9:50. Okay.
Now I
thank you.
request Professor Ghosh to start the session.
Good morning to all. Let me first give my heartiest thanks to Professor Satish Kumar, who is my very close friend and meeting several places, and gave me this opportunity to share some of my work with you. I am also thankful to Chairman Dr. Bhattacharya, who has very nicely spoken about my development. With this, I start. My topic is variance balance design using Helmut matrix and group design. So I have taken first, I will give some motivation. Various authors have worked on these tricks. Then I will go for construction method, then the efficiency factor, and then example. And finally conclusion. So let us see who are the persons who have worked in the variance balance design and why the variance balance is needed. So in literature, balance in complete block design are either variance balance, efficiency balance, or pairwise balance design. And it is also established a result that if any block design is variance balanced and equireplicated, then it will be efficiency balanced design and vice versa. So 1971, in the theorem of Raghav Rao, his book, theorem 4.5.2, he has discussed among the connected designs, and in that class he discussed the balanced design or most efficient design. He said a design is said to be variance balanced. The variance of the estimate of each of the possible elementary treatment contrasts is same. That is, all Ti denotes the ideal treatment effect. Then variance of Ti estimate minus Tj estimate is constant for all I not equal to j equal to 1 to v. Later on, certain idea about the C matrix of the block design. In 63, he said, it is well known that balanced complete block design are most efficient but do not exist for all parametric specification. And they are equireplicated and equal block size. This is a very great difficulty for having the balanced incomplete block design for all the parameters because it requires binary, equireplicated, and equiblock, and as well as balanced. So in some situation, it is found that BIBD which equities or unequal block sizes, any balanced design, or both are needed. Let it be not the BIBD, maybe another balanced design, maybe another block design, but it's required. So they felt that the variance balanced design can have both equal and unequal number of applications and as well as block sizes. The importance of variance balanced design in the context of experimental material is well known as it yields optimal design apart from ensuring simplicity in the analysis. Now let us see who were the persons who worked on this area in the beginning. So with the varying block sizes, the peers did work on 1964, and with reliable variance balance design with unequal representation, Mukherjee and Kayama 85, he did some work. Then Hedayat and Federer, Puri and Nigam, they actually, in fact, it is defined by Puri and Nigam after that. He defined that a design is said to be variance balanced if every normalized stimulus linear function of treatment effect can be estimated with the same precision. And you know, precision is nothing but the 1 by variance of IP. Then also discuss the necessary and sufficient condition for the existence of BB design by Kageyama 88, who also discussed some method of constructing with unequal treatment replication and unequal block sizes. Khatri actually in very old 82, he discussed, but not in giving that it is a variance balance, but it was say it is the efficiency of variance balance design. Then 85, I with my mentor, Professor Das, he discussed a method of construction of very balanced design, and it was, I think I published in Sankhya. Mukherjee and Kayama introduced another resolvable VB designs. Then Hedayat and Federer, which said the techniques for constructing VB design, which is based on unionizing block principle, is developed by Hedayat and Federer. And it was later described by Kelvin 86. Again, Kelvin and Sinha extended his own work to produce design with more than only two distinct block size that permits fewer replications. And Agarwal and Kumar, he came with another way for constructing the variance balance design. His idea was to construct with group divisible design. And of course, Agarwal and Kumar published 3-4 papers the same sequence for constructing vivid design using designs, other for with triangular design also. Now, this is a well-known result by Rock 58. Any design, block design, whose symmetric satisfied this condition, C is equal to theta times Ig minus 1 by B EBB, where Ig is the identity matrix and EBB is a matrix of 0 and B column whose all elements are 1. And theta is a non-zero eigenvalue of C matrix of a block design. If any design, block design, satisfies this condition, that will be in case called variance balanced design. And we have seen that the balanced incomplete block design satisfied all the criteria, even more than other this criteria also. That's why we can say the PIVD is also a variance balanced design. Later on, Ghosh and Karmakar 85, Ghosh, that was published in Australian Journal of Statistics. Ghosh and Divecha and Kageyama, then Ghosh et al. 1991. We are providing designs through GD designs. Again, Ghosh and Joshi constructed vivid design through triangular design. Kageyama recommended the use of non-binary vivid design with binary vivid design, which are not available for given values of parameters. Agarwal and Kumar developed methods of constructing ternary vivid design with V plus H treatment, having blocks of unique unequal block sizes through block sizes with V treatment. Again, Ghosh, Kageyama and Joshi developed ternary vivid designs using BIB and GD designs. Ghosh and Joshi further developed more vivid designs using the lattice square PBIB designs. And 2012, Ghosh studied the robustness of vivid design against the loss of K treatments and one block. Now, we are coming to the method of construction. So here I discuss method of construction using Hadamard matrix. Let us see first what is Hadamard matrix. It is a matrix whose elements are 1 and minus 1, and it is a square matrix such that if write Hn is equal to Hn prime into Hn is equal to Hn prime into Hn is equal to I times n. With the first matrix H2 is equal to 1, 1, 1, minus 1. It is 2 by 2 matrix. So, Hadamard matrix, the beautiful idea is that its elements are 1 and minus 1. So, if I convert minus 1 as a 0, I keep 1 as such, it means the incident matrix has a 2 element only, 1 and 0. And that is a binary design. So once I have a binary design, and also number of plus 1 and number of minus 1 is coming an equal number of times. If this comes equal number of times, this shows that is a unequal repetition. Similarly, the block size also. Block size also, each block number of element plus 1 and minus comes an equal number of times. That is also a beauty, that is a equal block sizes. So what are my criteria for obtaining VB design using Hadamard matrix? That we can always have a VB design with parameter V is equal to n minus 1, where n is the size of the Hadamard matrix. And B is equal to n, R is equal to n by 2, and K is equal to n by n2. So it means you have the two type of block sizes. One is n by 2, but reflection size is same. It doesn't differ. It is equal replicated design. And after solving all these things, I found why I am writing CIN. Because in 85 paper, we have established a very simple result that any VB design can be explained very beautifully by using CI matrix. And CI matrix is nothing but summation Nij into Nmj by N dot J. Means ratio of the sum of product of the two elements in two columns upon the block sizes. And that gives, if this same for all the pair of treatments or all the pair of columns, then that design will be variance balanced design. So if I can show this result, we got the variance balanced design. And N is the size of the Hadron matrix. So what we'll do, in first case, we have a Hadron matrix of size N. Delete the first row. Why? Because in Hadron matrix, there is only one row which contains all elements plus 1. Leaving that row, other elements contain plus 1 and minus 1 equal number of times. That's why we are deleting the first row which contains all the elements as 1. Now, when once I delete the first row, literally the dimension of the matrix will be reduced. So it has a n minus 1 rows, but column remains same as n. And then now we are replacing minus 1 by 0 and 1 we kept as such. And this matrix now, having n minus 1 rows and n columns, I consider as an incident matrix of a VB design, where rows are treatment and columns are blocks. The matrix contains n minus 1 rows and n columns, and having n minus 1 and b equal to n. This in each row, which contains plus 1 n by 2 times, the first block contains element for n minus 1 times. That I will show you by example, whereas which means the first column has 1 n minus time. So, because I have already deleted first row, for one column, one element is less now, so that's why it is n minus 1. Whereas the remaining block contains element 1, n by 2 minus 1 times. So r is equal to n by 2, this, and k is equal to n minus 1 and n by 2 minus 1. So I just explaining one thing which is very important, which people are interested to work further. That I told you CI means nothing but it is a sum of product of the elements in two columns by the block sizes. If I take any two column, if I take the sum of product, I found this is coming in one block size is n minus 1, and for another pair of treatments, it also comes once, but block size n minus 2. If you solve all these things, you get these results. Now, this is Im, means I is equal not equal to m, is equal to 1 to b. So for all the pair of treatments, I got these results. When I got these results, and this is same for all the pair of treatments, so this is a variance design, it is clear. But this is not a necessary and sufficient condition. For that, I have to find out that if the C matrix satisfied this, that is theta times Ib minus EB by V, where theta is not the eigenvalue, then I can say it is a variance balance design with the corresponding theta. So for this design, I found C matrix as you know, diagonal matrix of R1 to RB and minus nk inverse n prime, where this is a diagonal elements, since it is equireplicated, all has the same diagonal elements, and n is incident matrix, k is the diagonal element of the block sizes. If you solve all these things, you may get these results. Now, after simplification, etc., our idea is to make in such a way that this part becomes IB minus EB by B. So at that I got it. And that is our theta. And that is the non-zero. Hence it is the eigenvalue of C matrix. And multiplicity is n minus 2. So this gives a variance balance design with theta is equal to explain. Now, this satisfies the condition of VB design, hence we can call this is equireplicated with two unequal block sizes variance balance design. Now, if you go to the efficiency factor of VB design, we explain efficiency factor as a ratio of the two variance balance design, one with whom we are working and on we are comparing with the randomized block design. So this is variance of T minus Tm under randomized block design and variance of T minus Tm under variance balance design. And we got that variance of Ti minus Tm is always 2 by theta sigma square. So in the case of RYD, the R is always R, and R in Hadamard matrix case is n by 2. So that variance of treatment effect will be 2 by n by 2 sigma square. And in case of the variance balance design, it was 2 by 2 sigma square. 2 at theta non-zero eigenvalue I have calculated, and sigma square I got this. So if I solve this part, I get a efficiency factor. And we have to say that if the efficiency factor is more than 0.8, means 80%, then it is a good design. It will be proper design. But if it is less than 0.6, etc., we got a variance balance design, but we cannot suggest to do any experimental field experiment using this type of variance balance design. For experimental work of the field, I must suggest to give those vivid design whose efficiency is 0.8 and more than 0.8. Let us take an example. I took a Hadamard matrix of 8 by 8. You can see every row there are 4 plus 1 and 4 minus 1. So it means if I replace 1 as a 0, the 4 plus 1, 0 will be in each row. That's why it's a UQ block size. And I explained to you, first column contains n minus 1, 1. That is there, because if I delete it, it contains like that. But remaining contains n minus 1 by 2. So this is our initial matrix of a variance design. If I take this example, so if I take two columns and take the sum of product of two columns, what we are getting? 1 into 1 plus 1 into 1, 2 plus 1 into 3. And block size is same for each. So 3 by 4, that is a CIM. And if it is true for all the cases, I can say it satisfies the necessary condition of the BB design. And then finally, I got the C matrix, etc., etc. After finding C matrix, this is the C matrix. Theta I got 10 by 3. And it is, if I take RVD, so RVD, since it is a 3R, R is 4, so 2 by R sigma square. And here 2 by theta is 2 by 3, 6 by 10. And take the ratio of the two variances, I will get the efficiency factor. This is 20 by 24. So it means 20 by 24 means 5 by 6. So 5 by 6 is more than 80. So it is a proper design which I can suggest go for the field experiment. Now, next we go for the group design. And why I selected the group design? Because, see, what is our idea in a variance balance design? That every pair of treatment I take, two columns, then sum of product must be same for each and every column. how many columns? V into V minus by 2 columns. And group driven design, a design, this is PBIB design, where some treatment occur lambda 1 times and some remaining pair of treatment occurs lambda 2 times. It means I have 2 type of pair of treatments. So where those pair of treatment where it occurs lambda 1 times, and if add some more blocks where I can show that that pair of treatments also do not occur there. But other cases where it is occurring lambda 2 times, that added block must contain the treatments as lambda 2 times. So this way, the number of treatment lambda 1 plus here, lambda 2 plus here pair treatment will be same, and this will fulfill the criteria of the variance balance design. So this is it. I have taken only this type of group design I have taken. And after taking such group design, proof I am just omitting. Then I found that that CI is equal to, I am giving this as much important. Of course, there are some other criteria to finding the other matrix also, but I am giving this idea as a more proper to find out, but it takes very less time also. There I can say that CIM is equal to lambda 2 by K by solving all these things, but blocks of this design is being repeated K times, then lambda by 2K into K, so 3I become only lambda 2. But for case of the lambda 1, when lambda 1 is 0, the CIM I got it lambda 1 by K plus n times lambda 2 by n. But lambda 1 is 0 and nn cancels, it's again lambda 2. What we are getting? This is very important while doing constructing VB design. Keep this point in your mind. Then easily you can construct VB design. This is a matrix of n, K inverse, and n prime. If in this matrix the diagonal element remains same and off-diagonal element also remains same, it will always give a variance balance design, whatever be this matrix. If this matrix equal block size, VB with equal block size. If it is unequal, it is VB with unequal replicated. But most important is this way. So after solving, I got this is a C matrix, and theta is nothing but this part, R times K minus 1 plus lambda 2. And the efficiency factor, I already explained you, this is the efficiency factor. And here our efficiency factor is this much time, R times K minus 1 plus N lambda 2 by R N lambda 2. I'm going to example directly. So I want to construct a VB design with B18, B164, R22, K, 2 unequal block size, 3 and 2. And for that I have taken a group design whose parameters are B8, B16, R6, K3, lambda 0, lambda 2, M4. What is M? M is a group, Mn is group. So V is equal to Mn is a group. So this is divided in such a way, each has N group and each has the N treatment. That's why V is equal to Mn. And for this group design, group is 4, 2. Now this is a group 1, 5, 2, 6, 3, 7, 4, 8. And this I consider as a 4 blocks. And this is the blocks of the treatment in the blocks of the group design, which is a regular group design, number R54. You can see in the client body table. And solving all these things, I got efficiency factor at E is equal to 8 by 11, which we can use in the another. I think how many minutes you are giving me now?
You are having another 11 minutes, sir.
In fact, yeah, can take another 11
minutes. Yeah, 11 minutes.
Okay, 7 minutes, no problem. I'll complete 7 minutes. So now I extended this result Here also you can see the efficiency factor 8 by 11. Very high efficiency factor. Now, I just extended this result. Earlier result was for lambda 1, 0 and any lambda 2. I extended result for any lambda not equal to 0 and any lambda 2. So in such, if I use these cases, then what will happen? I can find out the blocks will be repeated n times lambda 2 minus lambda 1. M block. What is M blocks? M blocks is the group of the GD designs.
You need some hot water to drink.
Thank you.
Okay. Okay, Professor.
So I'm coming directly to the example, not any discussion. And that is the I want to construct a VB design with V16, V120, R9, K32. And this is a regular BN R46. Let us see. Here lambda 1, 2, lambda 2, 3. So if somehow I can make this lambda 2, 3 for all other pair of treatments for some columns, and this lambda 1 also made 3 for some other columns. If both are same, then our CI matrix is same. If CI matrix is same because K is 3, K is equal block size, that is giving a VB design. That is why we have to take how I can add extra blocks, how many times, so that this becomes the same. This is actually main idea for construction purpose. So this is the blocks of the VB design. And here lambda 2 minus lambda 1, 3 minus 2 is 1. So I have to take group. What is group? Group is, this is group. 1, 4, 2, 5, 3. 3 groups, because B is equal to 6. So each group has the 3 treatments. Now this is repeated n times. N is 3. So 3 times by repeated, then it is giving GD design with these blocks. Here I want to show that part. So this is a incident matrix of a GD design up to this much. Up to this much. So here you can say the block size is 3, 3, 3, 3. And this is the, if you take this total block replication size. Now I'm adding this group. One group, 1, 5, second group, 2, 5, and 3, 6. This is 3 group I added with this. So here if you check 1, 2, 1, this is 2 and 3, and this there is 0. So 3 now becomes the CIM. But block size is equal, so I'm not taking block size. Now if you take the 1 and 4, see 1 and 4, 1, 2, you have 2 only. But if I take 1 for here, it is 1 into 1, 3. So now your CIM is same for all pair of columns. So this will give you a idea of the variance balance design. It will always be variance balance. And I can say it is the best and necessary and sufficient criteria I can find out. This is the. So I completed, and this is the references for you. Some references are lost. I don't know how it is lost.
Thank you, Professor. Any of the queries from the audience? Sir, how a small this one? Generally, a variance balance design with unequal replications. Is it? I think may not be an efficiency balance design.
No. It is not. See, there is a one lemma. Let a design is a variance balance, a design is equireplicated, and then design is efficiency balance design. It's out of 3. If any 2 criteria they are satisfied, the third criteria will be automatically implemented. For example, design is a variance balance and efficiency balance, it will always be replicated. Again, another way, the design is replicated and efficiency balance, it will be variance balance design. And third is design is variance balance and replicated, it will be efficiency balance. So there is not the criteria of unequal block size or unequal liquid size. Criteria is this lemma. And this lemma was developed by Day.
Yeah, even BIBD with unequal the replications also, we can construct the variance balanced.
Yes, right.
Yeah, and I have taken the Hadamard matrices, which are generally the existence for the multiple of 4,
Yeah, right.
0 mod 4.
Right.
Suppose if I want to consider construct for the other the treatments, so can you suggest any other?
Yes, in that sense, what I have done, this I have published that result already. What I have done, say I took a Hadamard matrix of 8 and deleted some rows so that it become less than n. And now I will add some blocks of some another design in such a way that the CIM matrix of the some pair of treatments and remaining of pair of treatments becomes same. If I can get this criteria, then Hadamard matrix of less than n is divisible by 4, we are getting, and we have already got, we have published that one also.
Okay. Even for the some of the efficiency balance designs, by augmenting of the unities J vector, there is a chance for the getting of the variance balance design. Even that actually that I also constructed some of the variance balance designs on the similar lines of if I taken one of the incidence matrix which is already satisfying the variance contrast is same, n and n complement with augmenting of j's, so we obtained the variance balance design.
You are right.
Yeah.
By using augmented block design, not only augmenting blocks, both cases, it is already published.
Yes.
By reinforcing n treatments and by augmenting n blocks or both, we can find out variance balance design as well as efficiency balance design.
Thank you very much, Professor, for enlightening the participants. And I'm thanking to Professor Satish Kumar sir and his team for giving an opportunity. Thank you very much, sir.
Thank you, Professor DK Ghosh, for the talk. In fact, even though because you are suffering from cough, I don't know whether it affects you.
Yesterday night I had a fever. I don't know.
You have much pain. In fact, thank you so much for your support to give the talk in this occasion. And also, we would like to extend our thanks to Professor Bhattacharya for chairing this session in a very nice way. Thank you, Professor. Thank you. Now let us move to the next session. Now it is right time. Professor Shaktive so is here to chair the session, and the speakers are also ready. Professor Sangamitra?
Yes, sir.
Yeah, you please introduce the chair and and help him to execute the remaining answer.
Okay. A warm welcome to everybody present here. I welcome you all to the 29th session chair with Dr. K.M. Shaktive. He is a life member of International Indian Statistical Association, Indian Association of Productivity, Quality and Reliability, Indian Society of Probability and Statistics, and Indian Bayesian Society. His areas of research include distribution theory, statistical inference, statistical quality control, and artificial intelligence. He did his PhD in statistics from Bharatiyar University, Coimbatore, and he is currently providing service as professor in Bharatiyar University, Coimbatore. He has published numerous publications in various national and international journals and presented papers across the world. Without any further delay, on behalf of the whole organizing committee, I once again welcome Dr. K.M. Shaktivel sir to kindly chair the session. Over to you, sir.
Good morning to all of you. It's a great pleasure to chair this section. It's a final day, fourth day of 8th International Conference organized by the University of Kerala. So it's a great pleasure. And I got an opportunity to chair this session. There are three eminent speakers in this session to present their paper. The first speaker is beloved Professor Bhattacharyalu. So it's an honor to introduce him in this August learned professors. So Professor Bhattacharyalu completed his MSc Applied Statistics, MPhil in Statistics, PhD in Statistics, and also he completed postgraduate diploma in DCP. He has a vast experience of 28 years after his PhD in research. He published more than 85 research articles in the reputed national and international journals. He completed one UGC major research project and one UPE minor research project. He produced guided 7 PhD candidates in statistics successfully. He produced 3 MPhil statistics. He presented more than 85 research articles in national and international level conference. He was a president of the Society for Development of Statistics and General Secretary for the year 2018 to 2020. He is a life member in various statistical societies like ISPS, SDS, IISA, APSMS, ISAS, ASR. He published 3 books and compiled 4 lab materials and monographs. He is editorial member to 3 international journals and a referee for reviewing the research article to various national and international journals. He organized 2 faculty development program on data science courses, 2 UGC orientation courses, 2 UGC reference course, 5 faculty development program. He served in various capacities in university, Osmania universities, and other eminent institutions. He was working as a UGC SAP level 1 deputy coordinator in the Department of Statistics and the UGC SAP 2 coordinator. He was head of department since 2021 August. He is a director, Center for Quantitative Techniques, Osmania University since September 2021. He is a nodal officer for Telangana State, appointed by TSCHE for data science courses. He was chairperson, Board of Studies in Statistics in many universities. He is in charge of Department of Statistics during the year 1994 to 2001. He also served as Assistant Controller of Examination for the Osmania University for a period of October 2010 to December 2012. He was a member of Placement Cell Committee in the same university. He received a Best Teacher Award from the Academic Editorial Enterprises in the year 2020. He telecasted lectures on operation research in Doordarshan for B.R. Ambedkar Open University during the period December 2001 to March 2002. Now such an eminent professor is waiting to deliver his lecture in the topic of non-parametric approach for analysis of designs. So I welcome you, Professor, on behalf of the chair and on my behalf. Thank you. Now over to you, Professor.
Thank you for nice introducing Professor Shaktivel sir, and I'm thanking for giving of this opportunity to share the knowledge to the audience, Professor Satish Kumar sir. Is it my screen is visible too?
Yes, Professor.
Yeah.
Make it full screen, Professor.
Yeah. Yeah. My topic is a non-parametric approach for the analysis of designs. Um, so many all that you are familiar with the design and analysis of experiments. So which is the branch of statistics, and it is a systematic and logical method of construction of the experiments, which are used for testing the hypothesis, that is what is framed to analyze the outcomes in depth with maximum information, with the minimal time and cost, and also avoiding the systematic errors and ignoring the spurious effects. There are number of experimental design techniques that are available, and most of the, that means almost all the experimental design techniques are mainly based on the assumptions of the normality, independence, or homoscedasticity, etc. Now, here, if the conditions are violated, then how we are approaching? Because the basic designs, whatever the completely randomized design or randomized block design with covariates, RBD or RBD with R replications or covariates, or either complete block designs or incomplete block designs or factorial experiments or response or mixture experiments, all are based upon the basic assumptions of the normality, and we are trying to analyze the experiments. Now suppose the normality or the independence or homoscedasticity or the magnitudes of the responses are exactly not known, or the nature of the distribution is unknown, or if the experimental the results are measured on nominal scale or ordinal scale, then it is very difficult to continue the experiment or to analyze as per the original plan of the experiment. So that is one of the major problem that what we are facing in the experimental designs. Even though that we have planned perfectly and conducting the experiment and collecting the yields and whatever the responses, but the responses are not satisfying the basic assumptions of the normality, then or we are not in a position to accurately measure, in those cases generally are going for the non-parametric approach. So the popular methods also that you can mostly they are using is a chi-square test, the Friedman test, Kruskal-Wallis and Durbin test, etc. And many of the researchers they have attempted on the non-parametric approach for analysis of the designs. But when you are comparing with the other, the non-parametric approach methods are very few that that you can found, and most of them which are the evolved from the basic the tests of the Friedman or Kruskal-Wallis tests, and even the different type of the approaches. Some of them that you can find out in Puri and Sain, and Kepner and Robinson, and John and John, and there are some other members are also involved in the same. There are mostly they are concentrating about the rank oriented or the mm, uh, rank transformation methods. But suppose the data is on the nominal scale, specifically we cannot find out any of the direct methods, and also some of the ordinal scale methods are also um, here the Kruskal-Wallis or Friedman are existing, even though the test of the Friedman, which is seems to be too dimensional two-way classification, but it is testing only the one hypothesis that what we are generally are applying it. And the assumptions that what you are applying in the Friedman test for two-way classified data. Actually, it is a two-way classified data, but it is testing only the one hypothesis. Uh, the major assumptions are the K populations are identical. So instead of the normality assumption, we are considering the response variable is of interest is continuous, and the sample observations are independent within among the K samples, and measurement of scale is at least ordinal, and the one of the major assumption is no interaction between the treatments and blocks. So that means both are independent, the effects that what we are considering it. And all we are familiar with the Friedman test statistic. We are giving the ranking for the observations pertaining to highest treatment in the jth block as Rij, and evaluate the rank totals for the each of the treatment. And we are testing the hypothesis that the all treatment effects are equal or not, that based upon the variation in the ranks that is suggested by the Friedman, that is T is equal to whatever the formula that is specified at here. And this is generally follows the chi-square, the distribution. The Friedman test statistic is follows asymptotically the chi-square distribution with k minus 1 degrees of freedom, and its relative efficiency when you are comparing with F is 0.95. And it is used for the analysis, consists of k random samples of equal sizes, and the observations within each block may be ranked in order of magnitude. The test statistic can be used for the analysis of k independent samples of equal sizes. And this is the general, the one of the example that for how we are applying. So see here I consider the uh, in the study of the efficiency of chemical process on three types of catalyst A, B, and C. Their influence on four different days was examined, and the concentrations are presented, which are to be analyzed. And here we are giving the ranking uh, in each of the day for the three treatments that what you have applied, and such that the total will be on each day will be same. That means the rank is generally it is following n into n plus 1 by 2 if there are n treatments that are existing it. And that is statistic that you are calculating, that is the Friedman test statistic, that is 6.5. And here we are testing only the hypothesis, because even though the data seems to be a two-way, but we cannot test this because the values are day wise, it is we are not testing it because all the means are automatically same. Now the Kruskal-Wallis is 1952, which is generally you are using for the one-way classification, the analysis in case of the non-normality, and if it is possible to ranking the observations, that is the data must be in at least on the ordinal scale. That is one of the major condition, and the response variable is continuous. That is one of the assumption that what we are considering it. And this is the general the test statistic procedure that what you are going to use for the uh, Kruskal-Wallis test statistic, that is H, that is on the similar line that what we are following, but this is also follows generally the chi-square. And the Kruskal-Wallis test, H is asymptotically a chi-square distribution, and when you are comparing this is 0.955, and the asymptotic relative efficiency is never less than 0.864 for the one-way classified data. And generally these two that this can be applied for the completely randomized design, and Friedman generally are applying for the randomized block design, but it is not testing the two hypotheses. Now, this is one of the example. Now here I proposed one of the uh, alternative test. Suppose the data is measured on nominal scale. This is one of my student, the work that is uh, Anusha. And suppose an experiment is conducted by allocating the V treatments to n homogeneous experimental units in completely randomized design layout. So here I consider this experimental is same as that of the completely randomized design, whatever the principles of the experimental design. And if the data is measured um, related to the response variable y, and which is measured on the nominal scale only, or it is possible to express in the nominal scale. Now, generally what we are testing in the case of the non-normal population, the median. So here I am considering the assumption of the distribution for the data is the continuous in the neighborhood of m. So the probability for y greater than m is equivalent to the probability of y less than m. That is a general assumption that what we are applying almost it is the sign test model. Now assume that the observed responses are measured on nominal scale and are dichotomized with plus or minus 1 and follows the Bernoulli distribution with parameter p under the assumptions of no ties. And assume that the chances for each of the y takes plus or minus 1 is 0.5, and let y be the binary response variable. And here I have taken the treatments. So there are different treatments, and each treatment there are some replications. So
Mr. Abu Bakar, please mute your mic.
Each treatment is replicated some ni times. So these are the original responses, and the transformed data that I'm expressing based upon the median value, the whether it is greater than or less than. So I'm counting the number of pluses, or that means the positive values or negative values. So count that I'm ni plus is the number of positives and number of the negatives, so that for each treatment the ni observations are existing it. Now once it is categorized in this one, generally we can apply the general chi-square test for the analysis of the completely randomized design in case of the nominal scale. And so which is mainly used for testing of this one, and the test statistic, and also that the distribution that what we identified, it is almost the same as that of the chi-square distribution. And the assumption that what we have considered in the same, the observations are identical and independently distributed, and theoretically no zero differences that are existing, just like on the same lines as the sign test in non-parametric. And the most commonly used the approximation for the same in the more than 2, then we can this is almost a multinomial distribution, which is again leads to the chi-square approximation. And this is one of the example that what we have considered. And there are different treatments, and the number of positives and negatives, the counting that based upon the contingency table that you can test and can apply the chi-square. And even the Kruskal-Wallis test statistic. Generally, in the Kruskal-Wallis, suppose an experiment is conducted with a completely randomized design layout on n homogeneous experimental units with V treatments, where the n is equal to the sum of all the observations in each of the treatment, and Yij be the independent observed response. this is the observations. The responses are transformed into ordinal scale by arranging them all in ascending order of their magnitude and assigned ranks. So just like same as that of the critical values that what we are calculating here, Rij be the rank of the response. And so when you are calculating the values, so the same as that of the critical values that what I calculated here, the given the ranking for the observations 1 to V in each of the uh, observations under the uh, observations are equality holds only. So if there is unequal, then it is very difficult to evaluate in the critical values. So Ni must be a fixed, so which is equal to a constant for all the treatments. So that is one of the major assumptions that what we are considering. And so what is the major difference between this? What is this noted here? In the critical values, he has calculated just like on the based upon the R square, the value, but here we are consider the error sum of squares. So the treatment sum of squares and error sum of squares, the ratio that generally what we are considering in the most of the uh, analysis of variances. So instead of going for the R square, so here directly if you are using that also the variance that is calculated and the variance of the ranks instead of the observations, uh, we are not finding much difference between those two test statistics. So the critical values and test statistic is calculated based upon the treatment sum of squares by the total, whereas here the mean square of the treatment and the error. So that is the one of the major difference in this note. And we found that there is no difference, and we examined for the various data and concluded almost giving the same the result. There is a significant difference in the location parameter, and the F statistic is evaluated under the assumptions of the normality is F. Suppose if the normality is holds, and if it is not, generally we are applying the approximation of the same, the chi-square that you can apply it. And the suppose if there is there are some covariates in the same. Now here yi be the actual response and x be the covariate corresponding to y, then the analysis of one-way classification model, that is if the experiment is conducted on completely randomized design layout and the data is expressed in the one-way layout. So we have evaluated the test statistic for the same based upon the correlations. So here you used this Spearman's rank correlation because the data is measured on the rank wise ordinal data and the ranks instead of the computing generally in the regression. We are going for the ordinary Carl Pearson's coefficient of correlation, but whereas at here that I use the Spearman's rank correlation coefficient. And the total sum of squares that is evaluated, and we derive the formula for the total SS and based upon the ranks for the all the observations, and also evaluated the treatments corresponding to the response variable and covariates, and uh, also the cross product terms that also is evaluated, and the errors exx and eyy and exy, those are evaluated, and derived the test statistics h, which is almost same as that of uh, the test statistics that what you applied for the Kruskal-Wallis model. So this is hx for the covariate and for the response variable, and the xy as the cross product. of X and Y. This is the one of the example that what we have considered for the same, and we can test the test statistic by using the chi-square. Now, suppose if I taken the randomizer block design, um, here I consider the two cases for the randomizer block design, because the Friedman test statistic is testing only one hypothesis. Uh, so that is initially that what I have proposed in 1937, and later that is restricting to only one way by Kruskal-Wallis in 1952. And here I want to test both the treatments and also the blocks in the randomizer block design. So then I use the whatever the data that is obtained, converting to ranked ranks, that is called rank transform data. And whenever I'm considering the rank transform data, we can use in two approaches. One is rank transformation for the treatment wise, and also you can go for the block wise. And suppose if it is only on the based upon the block wise, that what is proposed in the Friedman test statistic, and suppose if it is deviating with the column, that also you can obtain. And instead of that, also that we examined the same for the evaluating of the way instead of the R square, the mean square due to the rank treatments and also the error. So these are the means of the ranks of the responses of treatments, blocks, and overall responses, and the total sum of squares that are evaluated for the uh, treatment sum of squares, and also the black sum of squares and error. And we have computed the test statistic for treatments uh, and also for blocks. And this is another, this is based upon the R square, and this is based upon the uh, F model, F aspect. And the same that I consider for the block wise, instead of the treatment wise, that I'm giving the rank. So previously that I block wise that the ranks that are assigned. Now if I'm making this one, then the test statistics that are derived at here, and on the same lines for the blocks. These are the various the variances of the sum of squares, and also that we checked with and also compared with the data when it is evaluated with Kruskal-Wallis and Friedman, and also with the this proposed test, and also giving the same efficiencies. And the another approach that what I'm using, this is so here I consider the comparison of the various test statistics, the whatever the different cases for that I considered. In almost the cases, the hypothesis is giving the same result. So Friedman assigned the ranks to the observations within blocks and examined the ranks in each block should be randomly distributed over treatments. The same can also be applied for blocks for testing. The Friedman evaluated the test statistic based on the ratio of the treatments and total sum of squares in ranks, just like in R square. Instead of evaluating the ratio of mean square, that is mean square treatment with error. And Kruskal test statistic is also evaluated on the similar lines of the R square. And Friedman test statistic is evaluated for two-way classified data, and but testing only one hypothesis. Now the same approach that I extended for the analysis of RBD if the covariance is present. Let's suppose Yij be the observed response, and xij be the corresponding covariate value. And we are assuming that the yijs are generally follows a normal distribution. If they are following a normal distribution, then we can carry out the ordinary analysis of covariance of the two-way classification. Now, suppose if they are not following this normality, then we can go for the rank transform data for testing of the two hypotheses, the treatment effect or the black effect, and for the variates and also covariates. So these are the ranks that are assigned. So capital Rij, that is corresponding to the responses, and small rij is indicating the rank corresponding to the uh, covariates. And we have evaluated the mean of the ranks for the covariates and also for the responses, and overall ranks for the variates and covariates, and derived the uh, correlation between the ranks of the variate and covariates, and which is mainly used to identify the functional relationship between this. And the x and y, actually generally we are going for the functional relationship based, not totally as the regressional approach. And these are the test statistics that are derived on, which are on the similar lines that what you are getting for the Kruskal-Wallis or Feynman test statistics. So for testing the treatment for the covariates, and this is for blocks for covariates, and this is the test statistic for the response variable for treatments and for the blocks. And this is the whatever the interaction term that what we are evaluating for the x and y, because x and y they are there is correlation is existing it, and there is some functional relationship is also existing based upon the ranks. So this is one of the example for the same aspect. And now suppose the data is expressed, the data is in a three-way classified model. We are extending the similar type of the approach for the Latin square design. Let's suppose yjk be the response corresponding to the kth treatment belongs to ith row and jth column, and let the number of observations be v square, and so the treatments, so which are already designated with v treatments, v square total v treatments that are existing at here, such that each treatment is occurring once either in row wise and column wise. And we are going to test the three hypotheses such that there is no treatment effect or block effect or the positional effect. And individually that you have to carry out separately as a combination of the two that you is the complication that is there in the Latin square design when you are extending the Kruskal-Wallis test statistic approach. So these are the ranks that values of Ri double dot bar is the sum of the ranks R dot J dot and R dot K, and similarly for the means for the rows, columns, and treatments. And we have evaluated the sum of squares corresponding to the ranks based upon the ranks for row wise, column wise, and treatment wise, and the total. Even the error sum of squares that also is evaluated, and the test statistic that is evaluated based upon the total sum of squares due to the source of the variation by total sum of squares. So in that approach, based upon R square. And also we can extend the same for the error approach. And this is the example that for the lattice square design. Now the analysis of when the ranks are assigned to source of variation wise. Because when you are going for the positional effect in the lattice square design, so with respect to the treatments that you have to assign the ranks, so corresponding to the each that column sum of squares and treatment sum of squares and the total sum of squares, the variation of the ranks that is obtained, and the test statistic for the positional effect can be evaluated based upon the two, one is column and also treatments. So here there are two approaches. One is the treatment and column and treatment and block. So both that are evaluated. So this is row wise or block wise. And so finally that you are the test statistic for affecting row effect and column effect. So both that you have to consider for the conclusion of the positional effect, just like not as that of the positional effect that you are evaluating in the general way. That is one of the major problem that what you are facing in the positional effect computation. And this is the test statistic, one of the sample data that I considered for the lattice square design for 4 treatments and 4 rows and 4 columns. And sum of squares for the rows and treatments are evaluated, and the H statistic for rows and treatments, and previous is columns and treatments. So both are evaluated, and we are testing the hypothesis based upon the chi-square value. So these are all giving the same as that of the general. If suppose if I taken the normality assumption, giving the same result, which are examined for the sample data of large and also small for the various samples. Now, in this that what I presented, the 3 different approaches for the completely randomized design, when the data is measured on nominal scale, and when the data is measured on ordinal scale with a correction with the correction, it is a note on the Kruskal-Wallis instead of the R square. We are evaluating based upon the F values, and also based for the covariates. The same similarly that is extended for the randomizer and lattice square designs. So this is the what I am presenting. Thank you for giving of this opportunity.
Thank you, Professor, for your wonderful lecture. Now the floor is open for question. If anyone from audience willing to raise any question, please, it's time for you now.
Yes, sir. Good morning. This is Dr. Moise Markonda. I do have one question. Basically, sir, your presentation is very clear and it is a nice presentation. Just I would like to ask one question. That what about the power, sir? Have you compared the power for the normality? If you assume the normality things, and if you are working with the non-normality by taking the non-parametric approach, sir, what happens to power of the test?
Yeah, the power of the test, because we are using on the same lines as the Kruskal-Wallis test statistic approach, the power is 90.95.
So you mean that assuming normality and without normality also we'll get the same power?
Same power.
Okay.
Anybody else to raise questions? Okay, if there is no question, I take up the opportunity to thank our beloved Professor Bhattacharyalu, who gave a very wonderful lecture on non-parametric approach for analysis of design. He introduced three different methods of CRD for ordinal and nominal scale, and extend the same for the RBD and LSD. So it's a wonderful to hear it from Professor Bhattacharyalu. So on behalf of the organizing chair, I once again thank our eminent speaker, Professor Bhattacharyalu. Thank you very much.
Thank you, Professor Saktivel sir, and for chairing the session. And thank you to Professor Satish Kumar and his team for giving opportunity to share my knowledge. Thank you, sir.
Thank you, Professor. Thank you very much. Now, I think Professor Magesh Kumar Banda is in line, right? So it's second speaker of this special invited lecture is Dr. Magesh Kumar Panta. He is currently served as associate professor in Ravansa University, Cuttack. He completed his post-graduation in the year 2005 in the University of Hyderabad, and his MPhil in July 2007 in University of Delhi, and PhD in March 2012 in University of Delhi. He has served in various positions before he served as associate professor. He was served as an ad hoc lecturer in the Department of Statistics, PGDAV College, University of Delhi, and guest lecturer in the Department of Statistics, University of Delhi, and it's a constituent college. And he also worked as a senior biometrician in Novartis Health Private Limited, Hyderabad. And he again joined the teaching profession as an assistant professor in Central University of Orissa, Korapat, and senior assistant professor in the same university. And he moved to or elevated to the position of associate professor to Ravansa University, Cuttack. His research interest includes optimal design, reliability theory, epidemiological studies. He has awards and grants. He received a grant of 2,500 euros to visit Vilnius University, Lithuania, and he received a Uzani Award from Sambalpur University for securing highest percentage in science in the 3 years degree examination 2003. He received a Golden Jubilee Award from GM College for securing highest percentage in science in the 3 years degree examination 2003. He served in various positions, which includes nodal officer in the Ravansa University from August 2022, and he is a NAC coordinator for the department, and he served as a head in charge at Department of Statistics, Central University of Orissa from 2005 to 2022, 2015 to 2022. He is a ex officio member of Academic Council and chairman Board of Studies of Statistics and convener of Board of Studies of Statistics different period of in the Central University of Orissa. He is a member of Board of Studies of Mathematics of Central University of Orissa. He is member Board of Studies of Computer Science from the same university. He also served in various capacities in University of Orissa, such as Social Media Champion and member Secretary Games and Sports Committee, member ICSTC Committee, member Technical Committee, member Website Management Committee. He guided one MPhil under his guidance, and one is submitted. And currently, there are 4 research scholars pursuing PhD in his guidance. And he is associated with professional bodies, life member Indian Science Congress Association, life member Society of Statistics, Computers and Application, life member Indian Society for Probability and Statistics. He is editorial member of Biostatistics Research Journal, and he visited ACB Medical College and Hospital, Cuttack, and Indian Statistical Institute, Calcutta, and Vilnius University, Lithuania, June 2026. He has a very good profile, and right now he's going to give a talk on optimal designs for cubic models without three-way effects and quadratic models with mixture experiment. Dr. Magesh Kumar Panda, it's wonderful to hear it from you with this topic. So once again, I welcome you on behalf of this chat. Now, floor is open to you. Thank you, sir.
Yes. Good morning, sir. My voice is audible?
Yes, sir. Yes, sir.
Yes, sir. Actually, I do have some problem with camera, so I am not able to share the videos. But
No issues,
still,
sir.
I would like to share my screen. I think my screen is. You can see my screen.
Visible, sir. Visible.
Yes, sir. Okay. So thank you, the organizer and Department of Statistics, Kerala University, for giving me an opportunity to actually share my work, what I am working on currently on optimal design for mixture experiment. So let me start with mixture experiment. Mixture experiment is basically it is a special type of design of experiment where the response of interest is depending upon the proportions of the ingredient present in the mixture, and it does not depend upon the amount of the mixtures. Due to the restriction that it depends upon the proportions of the ingredient, the sum of the proportion would be equal to 1, and that's the reason the vector space, vector space containing the q variables is no more q dimensional, but it will be a q minus 1 dimensional set. Let us see some of the examples related to mixture experiment. That let us consider the cake formulation example, and here the response of interest is rare appearance of the cake, and certainly it depends upon the proportions of the ingredients such as baking powder, shortening, flour, sugar, and water. Similarly, we can consider another example. Fruit punch example, it is a mixed of juices of watermelon, pineapple, and the orange. So if you wish to have measure the fruitness flavor of this mixed juice, then certainly it depends upon the percentage of the watermelon, pineapple, and orange. So diagrammatically we can represent this mixture experiment. If let us say the mixture experiment contains 2 ingredients proportion, then the vector space would be a straight line. On the other hand, if q is equal to 3, it becomes a triangle shape. So here we can see that these are the vertices, extreme points are these are the vertices, where this middle point is the centroid in this case. Similarly, here we can see that these are the vertices of the design, and here basically it tells you that your x1 is present. In this case, x2 is present, but x1 and x3 are not present. So it is 100% of the x2 which is contributing to the response, and here also the x3 component is only present. On the other hand, if you see the middle points are saying that 50% of the x1 component and 50% of the x2 component is present. So in this way, we can represent the mixture experiment. Okay, so there are certain standard mixture design has been proposed in the literature of mixture experiment, and one of the such design is simplex lattice design. So a simplex lattice design is actually involves q number of mixture components, and let us say it is of mth degree. Then what is suggests that the points will be basically consist of elements, where the elements will be nothing but basically it is a permutation of these values. So let us say m, if it is the order m, degree n, then let us you divide the 0 to 1 interval into m plus 1 equally spaced, then the elements will be nothing but 0, 1 upon n, 2 upon n, and then 1. So these points will be basically the permutation of all such component elements basically. So let us see what happens if q is 3 and then n is equal to 3. So in that case, it is the values of the elements should be nothing but 0, 1 upon 3, 2 by 3, and 1. So you can see that 3 cross 3 simplest lattice we can get by considering this 0, 1 by 3, 2 by 3, and 1. So in this way, we can get the 3 by 2 simplex lattice. A more generalization of the simplex lattice design is basically this one, where we can see that this point, it is 1, 0, 0, these vertices, and these are the vertices point where only the pure mixture components are present, and the boundary points where you can see that it is 1 upon A, 1 upon A, and then this is the centroid one. So when A is equal to basically 1 upon 3, this is nothing but a simplex lattice design. Now another design was proposed in the literature, that is nothing but simplex centroid design. So simplex centroid design is basically, it contains the elements in such a way, whenever these elements are non-zero, then it must be equal. So in this case, you can see that whenever these two are non-zero, it is of same values only. So this is the simplex centroid design. When Q is equal to 3, it comprises of the vertices, 3 vertices, and the midpoint, basically half, 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 0, half, and 0, half, half. Now, the available literature regarding the present work is like this only. So in mixture experiment, the mostly used model is Cephe's canonical polynomial, and Cephe is basically the who can be considered as the father of mixture experiment only. His work on 1950 and 63 gave a direction to the researcher to work on this area of mixture experiment. Subsequently, Kiefer, 1961, he obtained d-optimal designs for Cephe's model of degrees 1, 2, and 3, and he proved that the simplest lattice design, that is Q1, Q2, having equal mass assigned to each support point, is d-optimal for Cephe's linear and quadratic mixture model. Kiefer, 1961, he obtained the saturated d-optimal designs for the full cubic model without three-way effect, and the special cubic model when Q is equal to 3. Subsequently, Farrell et al. 67 and Lim 1990 derived the d-optimal designs for the general cubic polynomial model with 2 and 3 mixture components respectively. Micheli, 1903, he investigated the d-optimal designs for the full cubic model on this set. This basically the Q minus 1 dimensional vector space. Next, Panda 2022, he obtained the A-optimal designs for the full cubic model without three-way effects, and special cubic model when Q is equal to 3. So this work is restricted to only 3 ingredient components, 3 ingredient mixture experiment. In 22, another paper has been published in Communication in Statistic Theory and Methods. Zhu et al. Has obtained the A-optimal designs for the special cubic model on this set SQ-1. So if you see basically the literature, there are 3 forms of cubic polynomial model. One is full cubic, another is cubic model without three-way effects, and one is special cubic model. So the literature say that when you consider the general cube, getting the A-optimal design is only solved for full cubic model and the special cubic model. So the work was still an open problem for solving cubic model without three-way effects, and also in this present work we have extended the idea to for the quartic model when the degree of the polynomial is 4. The most difficult part of getting the optimal design is basically, especially in A-optimal design, that when we consider the D-optimal design, which is the most widely used design, that whenever we are using D-optimal design, the support points are equally weighted. So weight assigned to each of the design point is equal. On the other hand, when we look for A-optimal design, the support points may not be equally weighted. So getting the weights for A-optimal design is really a difficult task. And in this work, basically, we have tried to get the solution for cubic model without three-way effect and quartic model for 3 ingredients. Although I have solved this problem for general cube, in this presentation, I am sharing it for the Q is equal to 3. So this is basically the model structure. and that eta x equal to f dash x beta, x belongs to x q minus 1, the general linear model setup. And let us say we consider an approximate design where we are taking m number of such points from x q minus 1, and we allocate the weights like r1, r2, rn, so the sum of the weights is equal to 1. So the information matrix would be, for this design, is nothing but based on this information matrix. Basically, we try to find out what is the A optimal design. So A optimal design is say that you take the inverse of this matrix, information matrix, and then let us try to minimize the trace of this matrix, inverse of this moment matrix, which is basically telling that you are trying to minimize the average variance, because you are trying to add all the variance of the estimator diagonally and just trying to find which is the best design among all possible set of design, that is delta. And one of the theorem, equivalence theorem, if any design satisfies this equivalence theorem, it tells that this is the necessary and sufficient condition a design become A optimal if it satisfies the equivalence theorem for A optimality. Now these are the model forms. This is the full cubic model for which the problem is already solved. Now in this case, what is happening? If you see, it is cubic model without three-way effect. These effects are not included in this case. On the other hand, the quartic model is this one, the equation 5. Now, to solve this problem, we refer to the work of Kiefer, 1961. So Kiefer proved that any design xi, let us say for q is equal to 3, he proved the problem. So he took the xi and then he said that you consider the 3 vertices, and let us say you consider the 6 points like a, 1 minus a, 0, a, 0, 1 minus a, 0, a, 1 minus a, the permutation of all such points, and then the centroid. If a is equal to 1 by 2, 1 minus 1 by root over 5, then if you assign equal weights to each of these points, then that becomes a D optimal design. So this was the point of reference. Actually, I consider to choose the choose this support point for A optimal design. Now the problem what I have already solved, that the design xi when q is equal to 3 is a optimal design for cubic model without three-way effect when q is equal to 3. That when a is equal to 0.28, that is the same Kiefer took the values a is equal to these. It is the design which gives you the A optimal design, because in this case you can see that the trace of the inverse of the matrix is the minimum one. Now the questions rises why this problem was not solved for general Q. The question is, the challenge is basically the finding the inverse of the information matrix and verifying the equivalence theorem is very complicated in when you go for the general Q problem. So that is why till this Q is equal to 3, I was not aware how to solve this problem. Later on, what actually I refer to one of the paper, Gorman and Hinman, 1962, and then the idea is basically we are trying to find out the trace of the matrix, and trace of the matrix is nothing but the sum of the variances of the estimates. And fortunately, Gorman and Hinman has got all these variance of the estimates involved, and for the unknown parameter, the estimates were actually the points, these the response of interest was actually observed at these points. For example, the vertices and the points of the form A 1 minus 0 and permutation of these. So that actually helped me to get the trace of the inverse of the matrix without calculating the inverse of the information matrix. So what I did, basically I took the variances of the estimator in this case, and then just I added these variances and then try to minimize these variance, some of the variances with respect to the R1, R2. Now what is R1 and R2? R1 is basically the number of design points you are taking. Let us say you are having n number of points
then how many points you are taking, what is the weight you are assigning to these points. So basically, how many number of observation points you are taking at vertices. Similarly, how many number of points you are considering for these midpoints, and at centroid, how many points you are taking. Since the cubic model without 3 effect does not include these, it involves only R1 and R2, we didn't consider these R3 factors. So following the Gorman and Hinman 1962 papers, the trace of the matrix was obtained, and just it is a matter of using the Lagrangian multiplier method and solve this objective function with reference to the restriction that the total weights would be equal to n. Total number of observation would be equal to n, or total weights would be equal to 1. So once we solve this problem, then it tells you that the ratio of the observations R1 and R2 is nothing but root over G1 to root over G2, and where already we have got this G1 and G2. This is what the result of for the cubic model without three-way effect, where this A is a unknown quantity, but already the previous paper we have solved that when A is equal to 0.28, it becomes the A optimal design. Just you need to replace this A value, and just you have to find out what is G1 and G2. Now the next difficult task was to basically check the equivalence theorem. Fortunately, there is an algorithm available, and this is called as multiplicative algorithm. So this algorithm is I have actually transformed into the way the equivalence theorem for A optimality is required. So this multiplicative algorithm was proposed by Tosne et al. 2009. So this algorithm suggests that you generate initial weights W1 naught, W2 naught, and WP naught if there are p number of parameters are involved. And let us say you start this, r is equal to 0. That means this is the initial stage. Now what you do, repeat this maximum change in weight is smaller than a prescribed value of epsilon. Epsilon we need to take a value, and just you do the iteration, and with this iteration you have to obtain the Wi r plus 1, so which is nothing but the weight you have got at the rth iteration in this into this factor to the power delta. We said delta is equal to 0.5, and we iterate this. We continue iterate this multiplicative algorithm till we got the maximum value, because the equivalence theorem suggests that, let me go to the equivalence theorem. The equivalence theorem suggests that at the design point, trace of my matrix will be equal to the maximum over this value. So once we reach to this condition, we will stop our algorithm. So now the result I am citing for the quartic model. So for the quartic model, the optimal choice of this R1, R2, R3, and R4 value is nothing but, again for Q is equal to 3, is nothing but 0.0264, 0.0421, 0.0508, and 0.1630. So let us summarize what we discussed. So for cubic model, again I am citing the result for Q is equal to 3, but the theorem has been proved for general Q. So when it is Q is equal to 3, the weights assigned would be to the vertices is nothing but 0.0980, and the weights assigned to be these boundary points nothing but 2 by 3, 0, 1 by 3, and its permutation is nothing but 0.1177. So when it comes to quartic model, the points should be of this form. There are vertices, then there are midpoints, where we are seeing that the non-zero components are of equal values, and then subsequently it is 1 by A and A, where A is equal to 1 by 3. That is basically these 6 points are nothing but the 6 points corresponding to the simplex lattice design. So at these points we are saying that we'll assign W1 weights 0.0264 to the vertices, to W2, this W2 that is 0.0421 weights would be assigned to these mid-value points, and then W3 is nothing but 0.0508 to these 6 points of the Thorn 1 by A and A, and to the centroid, we are going to assign 0.1630. These are my references. Thank you. If anyone has any questions, I would like to happy to answer.
Now, floor is open for question. Okay, there is no question from the audience. So I thank Dr. Makmar Panta for delivering a lecture on optimal design for cubic model without three-way effects and Kotick model for with mixture experiments. He narrated everything excellently well with all assumption and good review of literature, and also he told many open research problems. So on behalf of the organizing committee and on my own behalf, I thank Dr. Magesh Kumar Panta for delivering this wonderful lecture. Now there is thank you, Rose. Thank you.
Thank you to Department of Statistics and University of Kerala, Professor Satish Kumar, and the chairman of the session. Thank you for giving me such an opportunity.
Thank you, Rose. Now there is another talk. I think Professor Rajaratnam is not available due to his other commitment. Am I right, Professor?
So he has not joined because he informed me that due to some urgent meetings he has to attend connection with.
Okay, Professor. So therefore, the third talk by Professor A. Rajaratnam is missing. So now every two invited talk in this session is over. So I take up this opportunity to thank Dr. C. Satish Kumar sir and his team for wonderfully organizing this 8th international conference on statistics for 21st century. So I wholeheartedly thank Dr. C. Satish Kumar sir and his team for wonderfully conducting this 4-day international conference. It's the final day. It's excellently went well. So once again, I thank you all. Thank you, Professor. Thank you, Professor.
Thank you, Professor Shaktivel, for chairing the session in a nice way. And also, we would like to thank Professor Bhattacharya Lu and Professor Mahesh Kumar Pandey for their wonderful talks. And in fact, today morning onwards, we are targeting on the design of experiments topics. And in the afternoon, there is a session organized by Professor Kabir on quality control. And in the evening time, after 6:30, there is the two sessions organized by Jaya Satyagopan from Rutgers University of New Jersey, Rutgers, on biostatistics and related areas. And all details are there in the program schedule. So we would request the youngsters to attend all these sessions in particular. Apart from that, there is a parallel session from 2:30 today afternoon, 2:30 to 6. There's a parallel session in which the best paper selection will be done in the final round based on the selection from the earlier rounds, preliminary rounds. So that also have to. So now we have some time. Now it is 11. 11:35. Next session will start at 11:30 or 35. No. By the time, I hope there is a scope for brainstorming or interactive interaction in this online platform. So those who wish to give some suggestions to or some advices to the youngsters, and also wish to put forward some novel concepts or other way or discussion. You can initiate discussions in that way. I think I hope that Professor Shaktivel, you can also just initiate, and you have the other meeting. so I know. We can, and Professor Kalyanam sir is also there in the group. He will also say something to the for the benefit of the youngsters. And other senior professors, if they are, and also the even though the researchers, you can ask some questions or something for some clarifications or anything you need from the senior researchers or senior professors available in the group, the present gathering. Please. Professor Shaktivel, you please start some initiation in this.
Yes, Professor. So now there is a subject called data science, which is emerging. There are many people from other discipline is confusing with statistics and data science. So what's the difference between these two subjects, and how the statistics will be going to be somewhere down the line after 10 years or after 20 years? So somebody can give throw some light on this direction. Professor, your voice is not audible.
I would like this occasion to invite the youngsters also to interact with the senior professors and professors. What Professor Shaktivel and other members. Nowadays, a hot area like this, have to give some students, in fact, young researchers as well as students are mostly confused with these emerging areas, probably.
Yes, sir. Now, because BSc data science available, BE data science available, BTech data science available,
Yeah.
and people are slightly migrating from statistics to data science.
In fact, several areas allied with the data science, and the statistics people are. Yeah. Kalyanam sir will add something.
Yes.
Unmute the mic and unmute. Please unmute the mic. The mic is muted.
Yes.
Okay.
Professor, I can leave because I have to finalize the result of Professor CSK Mutodo, that thing. So I have another meeting with Professor Loganathan.
Okay, Professor.
So shall I leave, Professor? With your permission, I can leave.
Okay.
Thank you, Professor.
Okay. Satish, you asked me anything?
Yeah, Professor.
Did you ask anything?
Yeah, Professor. Please, we expect to. We would like to. We have some time. 20 minutes. He's here to interact with the
Okay. Right.
Yeah.
Are you starting now itself?
Yeah, Professor. Yeah.
Yes. Yes, we can interact. No problem. I'm here. So it's nice that. Shall I start that discussion? Shall I start or somebody?
Yeah, please initiate, Professor. Yeah. Please, sir. You please initiate the.
Right. No, it's a very great experience to be associated with the conference that is going on. And due to the age restrictions, unable to attend all the lectures, and it takes some time to get into the activities directly. However, this is doing a wonderful kind of things doing. Of course, we at the age of 80 have seen statistics at different levels. In the initial stages, there was a talk on the history of statistics also, day before yesterday. And you could see many things that are happening around. And as far as we are concerned, we were more concerned with the early kind of statistics, which were mainly concerned with industrial and field experiments. So we gave more stress, as was given by Dr. R.A. Fisher, Neyman, Gossett, William Gossett, and these people developed these things, initial stages, especially for the use of analysis of data arising out of experiments. So the dependence on normality was a very great thing, and not many people started coming into the field, and only very few people with statistics are going on. But now what is happening is statistics is used everywhere, as people say. And also we come across another topic called as machine learning. And many people claim that machine learning and statistics are almost the same kind of things. But it is not so. A lot of changes, a lot of differences are there. But of late, I am seeing another topic that is coming in, that's called as statistical learning. Actually, I have not heard anyone saying about this topic, statistical learning, and books have started coming in this particular area. Since it's an extempore, I am unable to give you the kind of material for that, but if you can search Google, and lot of papers are available on that. What they do is, it is not statistics that you learn, but what you mean by statistical learning is you have lot of techniques in statistics, statistical methods as we call it. And these methods are used for purposes of using them for machine learning, for which you modify the technique in different ways. That's what is happening. Say, for instance, the unsupervised learning method uses regression in a totally different way. The word regression tells ordinary users that regression that you see in statistics and the regression you see in machine learning are one and the same, but it is not so. Please understand that there is a lot of difference between that. That is, the regression concept is used differently in machine learning, and the way in which you use it is going under the title called as statistical learning. That is a statistical method used for machine learning purposes. So this is what I see from the material that are available here, and how far people are going to take them in the real perspective is we have to wait and see. So a lot of things are available there, like you come across classification problems, and all statistical methods are being recrystallized, and the major contribution for the statistical learning is the creation of statistical methods under what you call as kernel methods. That is, whatever that you do, you make use of a kernel, appropriate kernel for the problem, and then modify the techniques. That is what is going on. I'm just looking at it from the point of view of a person sitting without any work. That's all. So I'm just sharing this experience with you, and it gives wonderful material for people to go through that. So this is what I am able to see over the last 1 year from the last exercise, that what is happening. So conference is going to be great exercise is going to have, we are going to have the valedictory function in the evening. And these people have done it wonderfully well with all the kind of things. If you have any specific question, I am ready to answer. There are people who can put any question which you would like to discuss from the, say I have some experience over the last 52 years I have been associated with statistics. This is the 53rd year going. So there are kind of materials available with me which I can share with you. As far as the Department of Statistics, University of Kerala is concerned, it has a wonderful library. You can have many articles of the early stages, right from the works of Galton, you have the works of Pearson, Fisher, Gossett, and all the classical results are available in the department. And you have the library with all leading journals coming from the first issue. The Biometrica is available right from the first issue. And all American Statistical Association, that is Annals of Mathematics. It used to be called as Annals of Statistics and Mathematics. Now they have Annals of Statistics separately. That's all available right from the first issue. So this is possible in the Department of Statistics. And another kind of thing which I would like to share because of the experience that I have gained by attending some of the lectures here. I don't know whether I can say it here, but there are about a few people around. And see, we are not presenting material on the board. We are just doing it over the Google Meet. So naturally, we are all old people, unable to see the presentation properly if you just write it very in small letters. So you must take care in preparing the presentations, and I think that you may give a note about how to make the presentation. Some of the presentations we couldn't see it here at all. That's all. And also, presentation means you don't put the entire thing on the say PPT. That the whole paper is put by some people are putting the paper itself. That is also to be avoided if possible. That is, you have to put your effort and create a presentation as though you are going to take a class in the classroom, original classroom. That is one observation which I would like to share with you. This is my request. It is not a demand from the organizers, but as a person who is associated with that, I am just sharing the problem that I felt while observing some of these talks. And I think that majority of the talks are almost over, and this thing. And another thing which I would like to share is this. Say, there are a lot of contributory papers, unable to attempt all of them because they are going in parallel sessions. And also the time that is allotted for them is very small relatively, and that's the only possibility. What one could do is this, since you are doing it online, just like your workshop, you can allot another 3 days for contributory presentations prior to the seminar. So the days you can split like this, first 3 days for workshop, and the workshop days itself, you can just organize a few of the presentations so that the contributory presentations can be made in a separate entity for 3 days or 2 days according to the requirements, so that we can have more attendees for every paper that is being presented. Now, I think that today you don't have any session, contributory session, but yesterday it was like that. And today I think that you have only one session which is going to be coming in the afternoon. And that also is one of the suggestions that I can make. So Dr. Sadish, take note of that. Because
yes, sir. In fact, we know, sir, the difficulty. We know the difficulty in attending all these sessions.
Yes, that is.
Yeah.
You can avoid it if you just add 3 more days, because that's not going to affect any of your regular work. That's not going to affect it, because people are going to present from their place. So that's not going to be a very big issue. So this is something that you can think of. Anyhow, all the best wishes. Anything that I can add, I can add. If you have any question, I can.
Okay, sir.
There are about 60 people. You can ask. You can just join the discussion. It's not a monologue. It should be some dialogue that comes in.
Yeah, there were around more than 50 are there here in the group. But you can ask also through the chat box if you are not ready to come forward. The speaker, the researchers or participants, those who can ask questions through chat box also. Just write their inquiries, questions, and if they are not willing to come forward through speaking.
Yes. See, we are offering this as a stopgap arrangement. We have done in a different way, but doesn't matter.
Yeah, what is happening is, sir,
we are not wasting the time. If you really want to make make use of it. See, as Satish was introducing me, I left the department in the year 2001. Now it is already 20 years left. Still I am with him, going along with what all that is being done. So that means that kind of an experience is available. If you ask for it, I am ready to share.
Thank you, sir. Thank you so much. In fact,
I am a person who was working with computers right from 1969, please understand, not a very recent one, because we had a computer in the year 1966 in the department. No one will believe it. That is, that computer is in the museum now in Trivandrum. You can go and see if you would like to see them. So I have been changing myself right from the changes that were happening in the computer scenario, right from the day when we started working with uni-record systems, and now I am just sitting and talking to all of you, sitting right from my place, residence. So all these computing scenario were seen by me in practice. I was witness to all these things actually. So anything that you would like to share, you want me to share, I'm ready to share with you. Yes.
okay.
And also, whenever a person completes his talk, at least there should be some response from somewhere. That's also very essential. Say, whenever I join any particular paper presentation, you can see that I go out without, I don't go out without asking 1 or 2 questions, or at least sharing my views on that and all that. So you must also have a view towards that. That is, people should feel that they are being heard. That's most important. Yes.
So in fact, there are.
Sir, good morning. Nowadays, research needs.
Yeah.
You know, what's the question?
There is a cultural.
Some question.
There's even most of the students.
General studies, data science.
Can you hear me? Can you hear me?
Right. There is a question which I would like, some student has asked. That is, Ankur Biswas. Okay. So nowadays research needs are shifting from general statistics to data science. In which areas we have to concentrate, sir? See, this is a big problem which is both positive as well as negative. And as I said earlier, many people think that data science is the same as statistics. My dear friends, it is not so. I know I am supposed to be, I'm known more for data analysis rather than theoretical statistics, even though I had done a lot of work in both areas. I just to share my experience how I became a data analyst first. Just remember, in those days, we had no other gadgets like what you are having now. We had that hand-operated machines. Many of you might not have seen it at all. If you are in the department, you can see some of the pictures, that's all. Or if you can visit Trivandrum, go to the museum and you can see the entire change that was happening with that. Even the electronic calculators, you know the price of the calculator when it was introduced, can anyone say? It was 8,360 rupees in the year 1973 when we purchased it, one machine. And that was the price of the electronic calculator in the year 1973. Now, you can see it for yourself. So, I'm coming to the point, that is data science, data analysis is the starting point. Data analysis is the starting point means, how do you go to the data analysis? Just by studying statistics. In these days, you cannot become a data analyst because they are more concentrating on theoretical statistics rather than data related work. But in our days, it was not so. You might be remembering the reference to statistics made by Dr. N. Balakrishnan, Pearson system of curves. Many of you might not have even heard of that particular thing, but we had to do them in practical side. We had to do all the practical works with data. So we were more trained for doing numeric computations in our years. That is, late 50s and 60s, what I am talking about. Early 60s and late 50s. And when I joined the department, we had a professor, and professor relationship is totally different from what you see nowadays. Some doctor from the medical institution may come and with his data and discuss the problem with professor. Professor immediately called the junior most. I was the one who was there at 25 years old. I used to be called, Kalyan Raman, doctor wants to do something, do it. This door. Then I just take that, and I cannot at that place ask the doctor what he wants to do. Because the professor-lecturer relations are not like as you see here. She, of course, our professor was a lady, Dr. George, Miss George, was aged around 55 years old, and I was just 25. So naturally, see the kind of relationship that we could maintain. So we had to be very obedient. And I cannot ask. If I ask, oh, why don't you know and why don't you see for yourself, that kind of a reaction will come. So what I used to do was, I used to go and stand near the car of the doctor. When doctor comes, I used to ask him, sir, what I want to do. You know what the doctor will say? Oh, I don't know what to do with that. You have to find out. So data analysis, I'm talking about data analysis. Data analysis is not easy. That's what I'm trying to say. So then what I do is, our library has wonderful material available. So I will go and at random take a journal which supposed to do some health related work and go to the index page and try to see what this doctor has given some other words. Thereby I can get about 3 or 4 papers. If I go to them, they will be analyzing something and just read the paper and sit and do the analysis using calculator in 4 or 5 different ways and keep the results ready when the doctor comes after 10 days. When doctor comes, our professor will call me, I will go there, and give the professor all the 5 results. She used to ask me, why you are giving 5 results? No, I don't know what, I have done it in 5 different ways. Let the doctor find and choose for himself as to what he wanted to do. So then the doctor will look into it for some time and choose one. Yes, I want this result. Now, you see what has happened? Now I come to understand for what kind of data, what I have to do with the data. Because I am not good at health-related work. Domain knowledge, that's what you say. So this kind of repeated doing made me to do good things, and I started thinking about the problems myself and started providing answers to data. So data analysis is not an easy job. And so data analysis were taken over to a different level as soon as the management introduced statistics for the topic. Lot of data started coming and flowing in. And computers were also improving and they developed what we called as management information systems, expert systems, kind of things. A lot of things came in between. Decision support system. All these things were using data to the extent that it answers problems of a management to the extent that was possible. And now, when data came very big in this, the data storage facilities started coming in. So, when data started getting stored in big quantity, a different concept started coming in called as data mining. When data mining started to come and the data storage also started becoming very big, finding patterns was not possible physically and then use the computer for that purpose. So what happened was, just to use the data and find patterns internally and try to answer questions, and that is what is being done in the context of what you call as artificial intelligence using machine learning. That's what is happening. So, my dear friend, the question is, what you have to do is, in order to do statistics with data science, either concentrate on statistics separately or concentrate on matters related to the machine learning things. First of all, you must get yourself used to data use, data analysis. The main difference between statistics and data science, as you call it, is statistics is concerned with providing answers in probability terms. In data science, you cannot just put probability terms and then leave it. You have to give exact answers. That's what, say for Google map, you see, you start from a place to thinking that you want to go to another place. You just to put the time, that is when I will reach that place. Google will predict. You know, over a 6 months experiment, I came across only one situation where the prediction was late by 1 minute. So that is the kind of accuracy that is available in data analysis in these cases. How they achieve it is totally different. You have to find out for yourself. So, difference between data science and data statistics is vast. If you want to concentrate on statistics, don't look at the data science part of it. If you want to concentrate on data science, try to look into lot of data related works. That is, you go to the departments where project works have been done. In our department, you can see a lot of projects going on and lot of data might be available, and you can just see for yourself, first of all, get used to data analysis to some extent. Then try to understand that the statistical learning, which I was just referring to a little earlier, is the area that you have to concentrate and then go for this kind of material. So all computers are there, answers are available in a nutshell, so you don't have to worry much. So you try to take this for A lot of books are available now, and if you, the real answer, the clear-cut answer to you is, if you want to be a statistician, don't think about data directly. You just concentrate on the mathematical side of it. If you want to become a data scientist, please look lot of data related works before taking your decision. The more concentration is, methods are more important for data science. For theory, statistical reasoning is more important. So this is one way by which you can have. So as a final takeaway, please concentrate on statistical methods. That is most important for becoming a data scientist using statistical methods. And of course, there are other data science related work which are not concerned with statistics, and that's also available. So that you can learn afterwards when you take up a course towards that. I hope that this answers. So the answer to your question is, look at statistical methods rather than statistical theory, and that is what you have to do. Okay, right.
Thank you. Thank you, sir. Thank you.
Statistical methods means there are books which are available. Even C.R. Rao's book contain lot of methods. You know how many people know how to convert a percentage into a number? Have you heard of sine inversion transformations? Have you heard of square root transformations? These are all things which were told in the early days of our learning. And all these things are available in C.R. Rao's book. That's more. Yeah. And another thing, if you, I can suggest this. Have you heard of C.R. Rao's first book title? Can anyone say? Statistical Methods for Research in Biometrics. Have you seen that book? It's available in almost all libraries. It should be. Otherwise, Department of Statistics, University of Kerala, a number of copies are available. And you see, that is the book that we studied. If you want to become a data scientist, please take that book and read from page 1 to page last page. You can understand what is meant by statistical data analysis related to statistical data analysis. Then you can use your ideas for data science differently. So that's also another suggestion that I can make. Please read Statistical Methods for Research in Biometrics. And that was the first book of C.R. Rao, and the linear statistical inference came only after it came out of our master's degree. Yes.
Sir, this one I have read, this linear statistical inference. That other one you mentioned, I will definitely try to read about. The first book you have told that I will try to read about.
So you have read? Yes, you please read.
Yes, statistical inference I have read.
Oh, okay. So that gives you a lot of ideas of data analysis as such. Am I right?
Yes, sir. Yes, sir. That's definitely
good
source for the statistical inference. Very good.
Statistical inference is contained. There is nothing more that is available in statistics other than what you see in linear statistical inference. You tell me any problem, I'll show it in linear statistical inference book by C.R. Rao.
Oh, okay. Thank you, sir. But recently, I don't work on that area. But that I have read during my MSc days.
Yeah.
That's a good book. Thank you very much, sir.
Thank you.
Good morning, Professor. Thank you very much for giving good suggestion.
Yes. Finish? Shall we finish?
Yeah. Good morning. Thank you, sir. Thank you so much for the fruitful questions and fruitful advice and ideas to share with the youngsters.
Okay.
Yeah, thank you.
This is an extempore interaction. That's all.
Yeah.
We didn't prepare anything. Please remember that. I remember all these things completely. It's not a God given.
Thank you so much, sir. Thank you so much. Now let us move to the next session. I think Sangam 30, session 30 is 30. Aradi,
Sir?
Aradi, please.
Sir?
Yes.
Am I audible?
Yeah. Aradi, please introduce the chair and help the chair to run this session in a smooth way.
Okay, sir. Thank you. Good morning, everyone. A warm welcome to all. Now, we move on to technical session 30. It's an invited session chaired by Professor Kamlesh Kumar Shukla. Professor Kamlesh Kumar Shukla is a professor from Department of Community Medicine, Noida International Institute of Medical Science, GB Nagar. He has several years of teaching experience in colleges and universities, including international experience. His research areas include distribution theory, mathematical modeling, and migration in demography. He has more than 100 research papers published in peer-reviewed national and international journals, and he has worked on several projects in national and international organizations like IIPS, WHO, DST, etc. It's our privilege to have you, sir, in our conference. I honorably invite you, Professor Kamlesh Kumar Shukla, to chair the session. Welcome, sir. Over to you.
Okay, thank you. Thank you. Very nice introduction. Thank you. So first of all, I would like to thank organizer Professor Satish Kumar along with their team for giving me opportunity to chair the session. Thank you, sir. So in this session, I think three speakers will present the papers. So 11:35 to 12:35, I think 1 hour is given. So 20 minutes time will be given to each speaker. So I will call the first speaker is Hemant Kumar, ICAR, IIPR, Kanpur, India. And he is going to talk penalized regression techniques. So Dr. Hemant, over to you.
Yeah, good morning, sir. Respected chair and audience of this group. I am very privileged and feeling honored and feeling proud also. I am getting the opportunity to deliver a invited lecture in this ISPS conference. Thank you very much, organizer and his team, Dr. Satish Kumar, sir. Thank you very much.
Dr. Hemant, yes.
Yeah.
Now it's coming.
Yeah. The penalized regression technique.
You can click it in full mode.
Yeah, it is. I already clicked in full mode, sir.
But it's not coming like full. Yes, now you.
Yeah, is it there, sir? Full mode.
Click on the presentation mode. I think it will come. Yes, click there.
Yeah, it is coming to my screen.
You can increase the size otherwise.
Pardon?
Next to that, you can move so that the screen size can be enlarged. Otherwise, it's better.
You can enlarge the screen.
The full slide mode is not working that way.
Slide mode is not working. Now it's coming. Yes.
Now it is okay.
Yes. So it is not on the first page.
Little bit you can increase the size of the.
Yeah, this is.
Now it's okay. Now it's okay.
Yeah. Multiple regression models are being widely used in various disciplines, including dairy science, animal science, and predicting the milk
Please start
production.
from the first page. It is not on the first page.
Yeah, this is
First slide is not showing here. Yes. Okay, now it's
yeah. Sir, I would like to talk on penalized regression techniques. This is very much useful nowadays in animal science as well as biotechnology fields. Multiple linear regression models are being widely used in various disciplines, including dairy science, to predict the live milk production of dairy animals. There are good reasons to use linear regression models because these are simple and often provide a adequate and interpretable description how the inputs affect the output. There is a one can imagine how the input variable and the output variable correlate and how can one describe the properly through the regression models. But sometimes linear assumption may not be satisfied in many practical applications if data have lot of noise or unexplained factors from the environment. However, multiple linear models have various problems associated with them. First and foremost is choice of the underlying functional form of the model. If the researchers incorrectly formulate the initial model, the model will be much less likely to perform as a predictive tools. Other problems with the regression are the assumption that mainly is the normality or homoscedasticity. Normality and independence of error term and constancy of the error variance are assumptions which are often made while using the regression models. The prediction accuracy can sometimes be improved either by shrinking of the sum coefficient towards zero or allowing a little bias to reduce the variance of the parameters estimate and predicted value. Further, with a large number of predictors, the interpretation can be improved. We use the smaller subset that exhibits the strongest effect. There are some advantage of penalized regression like this. This provide interpretable models, select variables that fit models simultaneously to birds with one stone, provide stable results with high prediction accuracy. They are computationally very efficient. Nowadays, computer efficient program are available. Or it doesn't require pre-training reduction. Penalized regression methods fit linear or logistic regression models. While fitting models, they can perform variable selection by placing at least one penalty on the size of the regression coefficients. For high dimensional data, a linear models with carefully selected predictor variables works well because a linear model is easy to interpret and a small number of predictor variables enables us to understand the underlying process that generate our data. To understand why interpretability is so important, to think about the following the models. If we tender who uses a statistical model to screen the customer applications, if we need not only make accurate prediction but also explain why an application was accepted or denied. Another advantage of this penalized regression is simultaneous model fitting and variable selection. For regression problems with a large number of predicted variables, traditional selection methods can be computationally very intense because they first identify a subset predicted variables. By successively adding and or removing the variables, then we use least square estimation to fit the model based on the reduced set of predictors. Penalized regression methods, on the other hand, select variables and fit models simultaneously. Its predictive accuracy also better for fitting linear models. Traditional model like
methods achieve simplicity, but they have shown to the models that are often unstable and have low prediction accuracy, especially for high dimensional data, which often include many correlated predictor variables. For analyzing these type of data, penalized regression methods such as lasso selection have become an attractive alternative to traditional selection because they can produce more stable models with high prediction accuracy. Its computational efficiency also more and cost effective because there are a lot of program is available on open source like large algorithm to solve the lasso problem. And this penalized regression doesn't need pre-training. Most penalized regression method can be directly applied to wide data where the number of predictors is much larger than the sample size. Means high dimensional data when number of variables is much more than the number of our number of data point. There are I'm here discussing with three type of penalized regression or shrinkage regression, which improve the OLS estimates. In particular, that first one is ridge regression, which L2 norm here is used. In particular, ridge regression that minimize the residual sum of squares subject to a penalty of L2 norm on the regression models. If we look at this model here this up to this this is a linear regression model. If we
Dr.
add this,
Hemant,
yes,
sorry for interruption. Your slide is not moving.
Oh.
You are on the first page only. Yes, now it is.
Yeah, I think this mode will be better. I think.
Yes.
Yeah. If you will go to that presentation mode, it is not moving. I think it is.
Okay, no matter.
Yeah.
As per your comfortable.
Yeah. The first one is a L2 norm, where means second degree of that penalty is used on the multiple regression model. This is the multiple linear regression models where this L2 norm in ridge regression that is used, and we minimize this residual sum of squares using this condition. Ridge regression we use the one complexity parameter lambda that controls the amount of shrinkage. The larger value of lambda, the greater the amount of shrinkage, but coefficient are shrink towards the 0. But we cannot increase the value of lambda. We have to use the trade-off between the variance trade-off so that we can optimize the value of lambda. However, ridge regression cannot produce a parsimonious model because in the parsimonious model, variable selection is not available, means not available in the ridge regression concept, and all the variables shrinks towards some ratio, with the value corresponding to the this complexity parameters. Another method is shrinkage lasso. Here L1 norm means subject to L1 norm, we give the penalty of L1, and this is the promising technique lasso. Now there are many type of lasso, adaptive lasso and Bayesian lasso. There are many type of lasso has come to in the statistical field, and we use, and many models are developed, and machine language also use this lasso techniques. The lasso is shrinkage method which selects the variable and estimates the parameter in a regression setup simultaneously. It minimizes the residual sum of square subject to sum of absolute value of the coefficient being less than a constant. If you go to this, in L2 norm, this is sum of this penalty is beta square. Here the sum of is the modulus of this beta. And if you go to, this is the defined as the complexity parameter that controls the amount of shrinkage. Owing to the nature of annual penalty, LASSO does both continuous shrinkage and automatic variable selection. Automatic variable selection means some variables coefficient become 0, and that is out from the models. So continuous variable selection, continuous shrinkage, and this is automatically variable is selected. Although LASSO has shown success in many situations, it tends to select only one variable from the group. If there is more than a group of correlated variables, they select only one variable out of this group of the correlated variables. In such situation, it has empirically observed that prediction performance of LASSO is dominated by the ridge regression. Another is penalized regression is elastic net. In elastic net, both L1 L2 norm is simultaneously used, and it generalizes the LASSO and the ridge regression. This is the model. If you look, this is the regression, multiple regression model, and this is the L2 norm. This is the L1 norm, and we use this both simultaneously. And elastic net simultaneously does automatic variable selection and continuous selection, and it can select group of correlated variable also. In LASSO, only one variables of correlated variables is selected out of correlated variables. It is like a stretchable fishing net that retains all the big fish. Means all the good variables, important variables is taken in the model. Simulation studies have indicated that elastic net often outperforms the LASSO in terms of prediction accuracy. There is some comparison between the LASSO and elastic net. When P means number of variables is greater than the number of observation, the LASSO selects at most n variables. Means only number of variables, how many is only that variable.
Dr. Hemant, you have 3 minutes only.
Okay, sir. Because the nature of the convex optimization, if there is a group of variables among which pairwise correlation are very high, then LASSO tends to select only one variable or few of them from the group and shrinks the rest to the 0 and doesn't care which one select. If n is greater than p, if there is a high correlation between predictor, it has been empirically observed that LASSO is dominated by the ridge regression in terms of prediction performance. Sir, I have used the data of, we have taken some animal data, and where this is the number of predictor variables, and we have analyzed the data. Here, this is the coefficient and corresponding error. Here, I would like to just share how this LASSO and elastic net can be giving the model variable selection. If you go to, there are 11 variables like this, and their coefficient. And if you go to ridge regression, all variables are selected in the model, and this is a bootstrap and standard error. And LASSO, if you took the LASSO models, there are AFC, these variables, and this CI2 and SP1 variables, and DP1 is removed from the model. And also if you look the coefficient, it is shrinked. If you go to the here multiple linear regression, this LM first, if you compare the first variables, coefficient is 0.498. If you go to the ridge regression, it is 0.4710, and if you go to the LASSO, it is 0.4. This is coefficient is shrink, and sometimes if you go to the AFC, it becomes 0 in LASSO. If you go to here this LASSO, there are 4 variables are removed from the model, being the coefficient is 0. And if you go to the elastic net models, there are same one more variables here becomes 0 means there's a removed from the models. The means I'd like just share or giving the idea about the how penalized regression can be used in the model selection as well as the prediction variables, and it is very much useful in case of biotechnology where number of sample size very less in less than 100, but number of genes it is much more than lakhs millions of genes is available, and that creates a lot of problem to analyze. But penalized regression, lasso, and elastic net giving.
Dr. Hemant, your time is
Yes.
going to be over.
Yes.
So
Yeah.
please hit within 1 minute.
Yes. Yeah. This is the, if you go to data here, just elastic net is giving the, however, data is not sensitive, but here you can look the elastic net is giving better performance among the this 4 models, MLE, multiple ridge, lasso, and elastic net. Dhanbad. Thank you, sir.
Okay, thank you, Dr. Hemant, for your nice talk.
Yes, sir.
So,
Thank you, sir.
So, dear participants, is there any question to Hemant Kumar? You can ask directly to Hemant Kumar. I think there is no question. Okay, once again, thank you, Dr. Hemant,
Okay,
for
thank
your
you,
nice
sir.
talk. So I have to call upon next speaker. Our next speaker is Dr. Manoj Kumar from Sultan Qaboos University, Muscat, and he is going to talk estimation for a modified generalized 2-parameter estimator for linear regression model. Oh, Dr. Hemant, present over here. Dr. Manoj,
Yeah.
over to you.
Yeah, good morning. I'm just trying to fix the. Can you see the presentation over here?
Yes, it's coming, but it's not in full scale. The presentation mode it should come. So please click on presentation mode. So
Yeah. Let me fix on that. I guess like I'm using a different laptop. My wire for the previous laptop got broken just today, so. It's not working.
okay, share your screen from now is not it.
Let me stop and share again.
Okay. Yes. Go on.
And share. It's coming or not yet?
Yes, it's okay. It's coming screen, but nothing is there. It's black one.
This way.
No, share your slide. It will come.
Yeah, I'm just working. Let me try again.
What you can do it, you can rejoin. It may come if you rejoin.
Which one?
No, you can left it and again join. So that I think.
You want to go for the next one?
No.
Just rejoin. That's you left and join.
What's that?
You can left the meeting and then join again. So then it will come.
Okay.
No share.
Bottom, you know the share.
So share your screen, please.
There is bottom and upward arrow is there. You just click on and select the entire screen.
You are not audible, Dr. Manoj.
Please unmute your mic. You want to say anything?
Unmute your one.
Dr. Manoj?
Yes.
Now it's fine?
Yeah.
Good morning, sir.
Good morning.
Good morning. Is it coming now?
Yeah.
Yes.
You can make it,
make it in full scale.
Yeah. Let me make it bigger. I don't know how to make on the full screen on this one.
No matter, you can go ahead. No matter.
I can go with it. I don't know. I mean, anyway, if you can see, then it's fine.
Yes, you can start.
All right, because there is some problem coming on because I'm using a different laptop now. All right, so basically, good morning, everyone. I'm sorry for getting delayed on this part. So basically, my today's talk, it will be based on a modified GenLI2 parameter estimator, or in the case of a linear regression model. Overall, in this one, what we did, like we compared, there were some existing estimators with a one parameter estimator and two parameter estimator. And in this situation, what we did that we make a new GenLI 2 parameter estimator. We modified the 2 parameter estimator. And then finally, we compared with the existing one, and we found that our result came out to be better in that situation. So this is the overall basic gist for this one. So overall, while starting with the linear regression model, first we talk about the ordinary least square estimator. So basically, like when you have the ordinary least square estimator, so basically the role of the ordinary least square estimator is to estimate the parameter vector in a linear regression model. So so when you have that one, so basically in that situation, when we do that one work with the case of a ordinary least square estimator in linear regression model, it gives many misleading results. So due to that, like it comes with a highly correlated data. And when the highly correlated data comes up, so it gave rise to the problem of multicollinearity. So that's how the multicollinearity problem arises. So when you have the multicollinearity, so we wish to obtain more accurate estimator of the regression coefficient than the least square estimator. So basically, in order to go with this one, we got a new regression coefficient in that case, and we got a new linear tackle the problem of multicollinearity. We came up with a modified GenLi 2-parameter estimator, and we got the modified GenLi 2-parameter estimator by merging the GenLi 2-parameter estimator and the modified 2-parameter estimator. And then we compared with the other existing estimators like ridge regression estimator, an ordinary least square estimator, Liu estimator, modified ridge estimator. So that's what we made a comparison. So this is how we mixed these two parameter which we get like the GenLi modified 2-parameter estimator and the modified 2-parameter estimator in order to come up with this problem. So basically, in this one, overall, if you go ahead with the introduction, so finally, make it bigger. If we go with the introduction over there, so we have a linear regression model, which we take it as y equal to x beta plus epsilon. So where y is your n by one vector of responses of the dependent variable, and that we consider to be linearly related to independent with the variables explanatory variable x1, x2, up to xk, and we have the parameter beta 1 to beta k. So, and we are using for the case of a multiple linear regression model with k number of regressors on that one. And your explanatory variable x1 to xk, that will be giving rise to your n by p matrix, and which will be considered a full column rank p, where p is less than equal to n. And epsilon is your random error component, which is of the form n by 1 vector. And if you take expectation of your error component, that should be equal to 0, and the covariance for the error one, that's equal to sigma square I. This is the basic assumptions which you are following for the case of working on. And then later on, we came up with the problem of the ordinary least square estimator. So in that case of the ordinary least square estimator, we applied the Gauss Markov setup in order to so we applied the Gauss Markov setup. So if you have the errors in the linear regression model are independent and have the equal variance, and the explanatory variable are orthogonal to U, in that case, we get the form of a linear ordinary least square estimator, which is your beta hat OLS equal to x transpose x whole inverse x transpose y. And now what we show that when we talk about, since we are dealing with the situation with the multicollinearity, so here we have we say that OLS is not the best way when the explanatory variables are related, because the problem of multicollinearity arises with the correlation between the explanatory variables over there. That's the reason. So in that case, we say that OLS is not the best. So finally, in order to overcome with that, with some new estimators were proposed, so that we can work on that one. So finally, when we talk about the case of a multicollinearity, so it's basically multicollinearity. It defined the existence of a linear dependency between the explanatory variable. So for that, first, in 1990, Bourne and Connell, they said that the problem of multicollinearity exists when the regression in the linear regression model are intercorrelated and are dependent on each other. So in that situation, when two or more regressors being redundant and have the same information is true, then the linear dependencies among the regressions can also affect the model ability. So finally, what they did, they take the transpose for the x transpose, the determinant of the x transpose x matrix, they tend to 0, and then finally it causes the estimate of the ordinary least square estimator to have a very big absolute value. So finally, we need to reduce the bias under such situation in order to overcome the multicollinearity part. So there were some bias estimators which came up. So many bias estimators have been proposed as an alternative, because as we said that OLS was not the better way with the presence of a multicollinearity situation in that one. So that's the reason some 1-parameter estimator and 2-parameter estimator came up in order to work with this problem. So one those we have the
Dr. Manoj Kumar, can you make it little large zoom so I see us better?
It's fine now?
Click on, no,
It's
it's
getting
click
fine
on the
now?
Zoom. Yes, yes. That's now
It's fine now? Is it fine?
Make it is Zoom, yes.
Okay.
Little more.
Can I make it more big? Is
Yes.
that okay?
Yes. Again.
Is it?
Again, click at least 90, up to 90.
Okay, let me make it. Now it's okay?
Yes, little. Okay.
So there were some like some bias estimator would come up with, like Stein in 1961. He worked on this problem, and James and Stein in 1961 they did other one. And so finally, what they did, what they also call it a shrunk least estimator, and there was the principal component regression estimator that was introduced by Massey in 1965. These are the things which we used to work in the case of a multicollinearity problem. So overall, in like 1970, Hull and Kennard, they basically came up with a very good idea. Like they proposed a restriction, which they call it like beta transpose beta. I mean, that's equal to C, and C is the constant value. So they applied the Lagrange method in order to come up with the case of they proposed that one. They call it the idea of a ridge regression estimator, RRE. And they did this by minimizing the value of your y minus x beta transpose y minus x beta plus k times here. So or like k here, k is the bias, and your and c is your constant over here. So overall, so when they came up, like when they say that your k is greater than 0, greater equal to 0, is a biasing parameter, and the ridge regression estimator, he came up with the beta hat restricted ridge regression estimator for k biasing parameter, that like your x transpose x plus k into I whole inverse into x transpose x into beta hat OLS. So that came up with the idea of your tk into beta hat. This x transpose x whole inverse plus k into I whole inverse into x transpose x, that they give I to tk into this, where the value of k is greater than 0. That's what we consider in biasing parameter. Value should be greater than equal to 0. And same way, they came up with the beta hat RRE, which is restricted ridge regression estimator for that case, for k. It came up with the tk into beta hat OLS, where tk, the value of tk is mentioned over here. Then it comes with the contraction estimator, which was mentioned as your beta hat rho, that equals to 1 plus rho whole inverse beta hat into rho greater than 0. So the contraction estimator can be obtained by mounting the equation of k to per half beta plus epsilon prime that's equal to 0. So by doing that, they got a contraction estimator beta hat rho that's equal to 1 plus rho whole inverse into beta hat OLS. So here your rho, it should be greater than 0, and it's a shrinkage estimate parameter. And what we did, like our main aim is to minimize the effect of a multicollinearity. So you in 1993 merged this with the Stein estimator, and they got beta hat LED. This is for the situation for the case of a Liu estimator, and the value of your D that lies between 0 to 1. So overall, the Liu got this estimator. Now, then came up with the problem with a modified ridge estimator. So finally, they talk about the prior information by it was given by Swindle. They obtained by modifying ridge estimator by the bias estimator to reduce the multicollinearity. So they got like beta hat MRRE, that's with the modified ridge regression estimator for KB, where your K was, as I mentioned earlier, that K was the bias. And they got this x transpose x whole inverse into ki whole inverse into y x transpose y plus kb. And we say that like for certain values of k, when you take for certain value of k equal to 0, it restores the estimate of the OLAC, and b tends to become 0, and it becomes a ridge regression estimator. And when your k is 1, then we get the value of your beta hat d in the case of a it's like x transpose x whole inverse plus x transpose x plus I whole
whole inverse into x transpose y plus d into beta hat OLS. Similarly, then later on the Liu, because the Liu came up with a new idea, and then what he did, like, in order to work on the multicollinearity problem, they said like the beta hat Liu for this one they did with, under this situation, x transpose x plus I whole inverse into x transpose y plus di beta hat OLS, and the value of your d it will lie between 0 to 1. So this is how the Liu came.
You have only 2 minutes. Please try to finish with.
Oh, 2 minutes. Okay. Anyway, so let me come to my part then. I mean, so anyway, so what we did, like in this situation, like when there was the 1 parameter estimator and 2 parameter estimator, so we came up with a new idea, having a modified GenLi 2 parameter estimator, where we, as I mentioned earlier, that like we worked with. So we got the prior information for this one. So this was our modified GenLi 2 parameter estimator by taking the value of k, d, and b, and we got this result. And finally, there were some special cases. Under these special cases, when we just play with the value of your modified GenLi 2 parameter estimator for the one which we got here, so it will be equal to your ordinary least squares estimator. But when your value of k is 1 and your value of b is 0 in the modified GenLi 2 parameter estimator, it will give rise to the situation of a Liu estimator. Similarly, if you have the value of d at 0 and value of b at 0, it will give rise to the ridge regression estimator. And same way, by placing the different value for your k and d and b, we compared it with the other existing estimator, and then finally, we came up with the result, what we got over here, that we got the expectation, bias, and covariance, and then we just found the max mean square error criteria, and then we compared with this one. So we
try to finish within a minute.
Yeah, I'm just coming to the result now. Yeah, so what we got, like we took the Hussein data set. In this one, we found that our one, it was more better if we compare with this. So we found that our estimator came out to be more better as compared to, because here, if you see that we reduced the, when we're working with, because here, if you see in this one, so they have the situation for the parameters for the case of ordinary least square, Liu, maximum modified Liu, 2 parameter, MTP, and this was the one. So where we got that our result came out to be better than the other one. So, and similarly, when we did the Monte Carlo simulation, so for different value of, for taking sample n equal to 20, even in this one, when your k was 0.01, you see that like MGPTE, this result is coming better as compared to the other one. So, and same we did for the case of k equal to 0.5 and k equal to 0.1. Our result, which our estimator, what we got,
conclude your result.
Yeah. So overall, it was overall with the conclusion, we can say that like when you're working for the case of a in the situation for the modified GenLi 2 parameter estimator, it was coming out to be better. So with the finding, we got that like modified GenLi 2 parameter estimator, it can overcome the problem of multicollinearity in a linear regression model, and the matrix mean square criteria was used to prove the superiority of the new estimator over the ordinary least squares estimator and GenLi 2 parameter estimator. As the GenLi 2 parameter is more efficient than the existing ridge regression estimator.
Manoj Kumar.
All right. Okay, sir.
So thank you for your nice talk. So
thank you.
Now the question hour session. So I will ask to audience. So dear participants, is there any question? If you have any question, you can ask to Dr. Manoj Kumar. So may I ask one question?
Yes.
Dr. Manoj Kumar, your model is good, your presentation is nice. So can you reduce the multicollinearity using this model?
Of course.
You know how much it can be reduced? Suppose it is.
That's what I showed over there. Like, I mean, if you compare with the other proposed model, I mean, our one was coming, we are reducing to a very high extent as compared to the Liu estimator and Stein and all those.
Okay, thank you. Thank you once again, Manoj Kumar.
Thank you very much. Thank you.
So without delay, I am going to call to the next speaker. Our next speaker is Rudra Pradhan from IIT Kharagpur. He is going to talk carbon emission pricing, linkages between EU ETS spot and future prices, and completeness of EU ETS future controls. So, Dr. Rudra Pradhan, are you hearing me? Dr. Rudra Pradhan. Not here. Rudra Pradhan.
No, he is not seen in the list. He is not seen. His name is not seen.
I guess like his name is there. He didn't join yet?
So what shall we do? I will ask to Professor Satish Kumar. Professor Satish Kumar, are you hearing me?
Satish?
Sir, just a minute, sir.
RTS. So next speaker, Dr. Rudra Pradhan, I think he is not joining or not here.
So in your session, I guess there are only 3 presentations over there.
Yes, 3 presentations, so 2 has been over, but...
Oh, so I concluded very fast, so maybe I can start.
Okay. Do it. It's better you can conclude properly. So he is absent.
Yeah.
I think better, sir, you have better way to conclude.
Yes. You can utilize his time because he is absent.
And because your talk is very...
it's very good.
Very good, sir. So you can proceed, sir, about the...
I can?
Yes, sir. Dr. Manoj Kumar, I will request again.
You have to proceed about the biasness for the risk regulation estimator.
Yeah. What's that?
Actually, I am very interested.
What for biasing?
Yes, sir.
Yes. So that's what, like, in this one we are reducing the biasing of that one. I mean, basically, like, we add the bias in order to reduce the multicollinearity. We add the bias so that, like, it gives a better one.
Okay. That means effect on bias variation of the other parameters.
What can you say again?
Variation of the other parameters, when you have to vary the other parameters, like increasing the value of n in your results, numerical results.
Yes. I mean, let me put on that part the table.
Yes.
So
if you want, you can share your slide again. no
I'm
matter.
just,
You
I'm
can
just glad
study
that.
time
Yeah,
up to 12:30.
yeah, I'm
Yes.
showing that one. Yeah,
It is
yeah.
better
So
time.
because let me go to that part.
Yes, sir. Go to the table, sir.
Yeah, yeah, I'm going that one. Yeah. You see here, like for different values.
Yes.
Can you see now? Is it fine, or I can make it more bigger?
Yes, yes,
Like
sir.
100. So if you see over here, like I mean, we got these are my estimators, right? So which I'm comparing. So this one is the one
Yes.
which we got by merging the two parameter estimators. So there, and these are the previous existing estimators. And if you see on this one, for different K, because K here, K, as I mentioned, that K is the bias, right? And so for different sample over here, and this is the contraction. So because if I mentioned in the talk earlier, just in short, I went very faster. So I got rho at 0.99 for this one. If you see the value of K for 0.01, K at 0.05, and K at 0.1, it means the bias side, right? So if you check on this, like this is what like we are getting for sigma equal to 1 over here, 2, and for sigma equal to 5. So if you compare with other one, this one is getting more smaller.
Okay.
Right? And same for K equal to 0.05 also is giving that one, and K equal to 0.01 also that one. And similarly, if once I put a simulation for this one, for N20 for 0.9, because previously it was for 0.85. Now if you put for 0.9 for the same value, K at 0.01, 0.05, and 0.1. So we got that. So in that situation also, like, I mean, if you see that MGTP is coming, the one which we compare with other estimators over here, it's coming better, it's giving a better result. It means that by increasing the biasing, we are getting based upon sample size. Only thing is that like we only took sample. See here, it was 50 for N50. We got this again and we took rho contraction at 0.85, and then for different value of K equal to 0.5, 0.001. If you check over here, here NGPTE is coming. This one is coming better, and same if you see for NH100.
Okay.
NH100, you can see like how like if you're adding the biasing, so it's giving the better result in the case of a multicollinearity, because multicollinearity reduced because when we add the bias, so it gives rise to reduce the multicollinearity effect. So that's how if you see over here, this MGPTE is coming to the better as compared to the other existing estimator. Modified Gen Light 2 parameter estimator is coming out better.
Okay.
And
the magnitude, I think magnitude also decreases when your sample size increases.
Yeah.
Okay.
Yes, definitely.
Yes, now it's coming. Okay. Good.
Okay. Really, your presentation is nice, sir.
Thank you
So
very much.
I think with increased sample size, I think decreasing it is variances.
Okay, variances also. Okay,
yes. If we increase to because I don't know, I didn't have more strong computer right now. I mean, so but I want to make it to a more bigger and see. I mean, how it's affecting for a large sample size, very large sample size.
And here you have to choose here sigma is equal to 1, sigma is equal to 3, and sigma is equal to 5 for the smaller standard deviation and for the larger. Okay.
Yes.
Better.
So that's why, like, I mean, NG basically, I mean, I was just comparing between those parameter. I mean, existing parameter with mine one, because I did that. Like, I was fusing. I mean, the two parameters
estimator. I mean, fusing between the Gen-like 2-parameter estimator and modified 2-parameter estimator, GTPE and MGPT. MTPE. So when I fused with these ones, so I got a new parameter, and which I showed that when I compared with the other existing parameter, it showed that it gives the better result in situation of a multicollinearity. So that was the overall thing.
Okay. Thank you, sir.
Thank you very much.
Dr. Manoj Kumar, thank you. Very nice talk. And you utilized the time once again. So
yeah. But in the beginning, I because due to the change today, it happened like I don't know. It just happened today problem because my charger stopped charging, and then I need to have other laptop. So I borrowed from my colleague, and then I'm working on his laptop.
okay.
Yeah.
So again, I will ask to the audience, is there any question you can ask to Manoj Kumar? We have still time, 2 minutes.
Yeah, you have.
Because he's utilizing the time of Dr. Rudra Pradhan.
I might be knowing at that time I might have gone slow, but I skipped many of the part.
Yes.
But I am bound of the time also.
Yes,
so
yes, because
I didn't know Rudra Pradhan is absent.
Yeah, we were not knowing that, like, I mean, the third one is not coming, so otherwise it's not, I mean, yeah. I had somewhat like 45 or 50.
Okay, so no question, I think, from the audience sides. So you can move on.
Okay, thank you very much. So,
okay, thank you. Thank you again.
Have a nice day. Thank you. Thank you.
Excuse me, sir.
Yes.
Sir, extremely sorry for the delay. We have tried to contact Professor Rudra Pradhan, and he said that he will join the meeting soon. Yeah, in 5 minutes.
He's going to join?
Yeah, he's going to join. Extremely sorry for the delay, sir.
Okay.
Yeah, thank you.
Here we have two Manoj with the same name.
Yes. Dr. Manoj Kumar, I think you are in Chandigarh. No, sorry. Where are you?
We are talking to which Manoj? The one in India or one in here?
No, that I know from Sultan Qaboos University, but another Manoj, Dr. Manoj Kumar.
Yeah, this Manoj.
His speaker is yes, his mic is problem.
Your mic is muted.
You can unmute your mic so that we can hear you.
Sorry, yes.
Yes, now we are able to hear.
Yes. So I am working here in Central University, Haryana, sir.
Haryana, oh yes. I got it.
Mahendragarh district. And Professor Satish sir already know me very.
From IIT Kharagpur, he informed me as to some time, 5 minutes time to join because of some technical issues. I think so. So let us wait 5 minutes maximum, and then you can close the session. Otherwise,
okay.
Very much thank you.
Thank you, Professor.
So how are you, Dr. Satish Kumar?
Yeah, there is some. Can you hear me, Professor?
Yes, sir.
Yeah.
So how are you? I mean.
Yeah, fine, Professor.
Yeah. See, right? Okay. Have a nice day. So is the third participant delivering the lecture? The third one from IIT Kharagpur?
Yeah.
Okay.
Yes, from IIT Kharagpur. I think he
Kharagpur.
joined late.
Let us wait a few minutes for him, for maximum 5 minutes.
No matter, no matter. We are waiting.
By these few minutes, let me to display the select shortlisted candidates for the best research paper award. We have shortlisted 12 candidates for the best for the final round for the best research, and their competition will conduct during 2:30 to 8 in the parallel hall C, where the further evaluation will be done and select the 6 among them. And these six awards, best paper awards, will be issued to them. Dr. Rudra Pradhan?
Hello.
Hello. Okay, Doctor. He joined.
No, I have joined. Actually, I had no idea that my paper was actually included, because I checked schedules, it was not there. So I thought because it's my fault that I sent late.
Oh, you have submitted very late.
Yeah, I know that once. Actually, today morning I have checked the schedules. My name was not there, so I was bit of surprising. Okay. By the way, no, my PPT is in my another PC, which is actually going on some updates, so I could not connect. But there is a Word file here, so can I speak through Word file? Then, if it is okay, then I can continue. Otherwise, I can shift somewhere.
Dr. Rudra Pradhan, if needed, in fact, we have included in the program chart and program schedule.
Yeah.
And if needed, we can share it from here for you. You can speak from there.
No, that's fine. My PPT is not here now in this PC. The PC which I have means the PPT which the PC is not working actually. So that's update is going on.
Whether it's a PDF file?
So the Word file paper is there. So if I speak from Word file, is that okay?
Okay. If it is enough for you to speak?
I'd say, somehow, I don't know how much time I need.
You have to present 20 minutes time for the time.
Okay, but I am not actually well prepared. Okay, anyway, let
So
me
if
see.
it is difficult, we can, no problem. We can, for the time being, we can stop.
No, actually, anyway, if he could call me little bit, half an hour.
Professor Satish Kumar, up to what time we can move?
So our this session is up to 105. So now,
Okay, is it visible now?
Yeah.
Hello.
It is.
Yeah.
Yes, visible. It's visible.
Yeah.
You can make it large.
Yeah.
Okay. All right. Is that okay now?
Yes.
Okay, Professor. I am very sorry for this because it's because of my negligence or late submissions, and I could not.
Come on the first page.
Yeah. So this is actually joint paper by my student Saikat and me and my colleague Binod and two of my students Devlina and Ann. And the paper title is actually Carbon Emission Pricing, Linkage between EU ETS Spot and Future Price and Completeness of EU ETS Future Contracts. Okay, this is mostly actually connected to time series modeling. And some of the highlights, let me first start and then I will explain what we have done in this paper and what is the kind of findings. Okay, so by the way, very good morning to all of you, and thank you Professor Satish for inviting me to this conference and to give me chance to speak here, and thanks the chair also giving time to share my research. So anyway, so this is research highlights. Yeah. Okay, that's fine, Professor. This is actually these are all our research highlights. Basically, it's an interaction between spot and future price of European Union emission trading systems, and we have used dynamic conditional correlation specification of multivariate generalized autoregressive conditional heteroscedasticity model. And some of the important findings are there is a high conditional correlations, and these are all highly statistically significant between carbon spot and future markets, and that too in the context of European Union. And also we the study uncovers a high degree of hedge effectiveness for EU ETS future contracts. And of course PPTs are not here, so I am not sure whether there is a visual properly or not. Anyway, so this is basically yeah, thank you very much. This is the study time period is 2019 to 2021, and I think it is a part of time series modeling. So as you know, there are so many time series modelings are there, particularly if you start with the arch clusters, gas clusters, and this particular work is actually connected to gas clusters, and that too we have used MGACH models, which is actually very dynamic one, and that too very advanced one, and that too studying the spot and future price in the context of European Union, and that too ETS future contracts. And so as I have already mentioned, the time period is between 2019 to 2021, and that too again in the context of India. So as usual, actually the study has lots of contribution to the particularly you can say energy market, and that too emission issue. So it has a so far as the policy implication is concerned, it is a substantial contribution to energy infrastructures, and that too the kind of climate change, because it is well connected with the CO2 emissions. And mostly it is we like to see whether there is a connections or correlation between spot and future price. Of course there are several works related to spot and future contracts. Of course we have also have a published work which is published in research policy in the same work, and it is a little bit advanced, and that to updated versions, and that too in the context of European Union. The previous paper is connected to India, and this is connected to European Union. And as you know, I have already mentioned, it has the highlight of this paper, or the importance of the papers, or the significance of the paper is connected to climate change, and that too contribution to the energy infrastructure. So I'm not going in details. These are all basic background about the papers which you have actually connected, and this is somehow a snapshot of CO2 emissions. Of course, everybody knows about this is a big kind of issue today in the context of environmental issues or environmental assessment, something like that, and that too, a particular European context, most of the countries are very serious about this CO2 emission. So that's why there is a high relevance is in this paper. We have highlighted this, and again, so how we can sort out this issue and what are the modeling results, so that can contribute to this particular requirement. So these are also some of the snapshots and that to trends of CO2 emissions across the European countries and related countries. So you can see some of the countries very high, some of the countries at very low. For examples, this is 160, and if you find there is a figure here 100 10,000 sorry 108 800 060. So it's a big variations you can find in the data. Of course, so I'm not going again details. So if you go, I'm directly going to study objectives. So we have actually 3 objectives. So this is objective 1, and this is objective 2, and this is objective 3. Okay. So the first objective is just to see the time varying correlation between spot and future price and using this MGACH DCC models. And the second, modeling the spillovers between future and spot price using this BEKK models. And then finally assessing the hedging effectiveness of European Union ETS future contracts by utilizing the variance covariance matrix of joint estimations. So again, so I have already mentioned, the kind of relevance, and that too, so many papers already published related to different contests, and that to individual country case, and then again, penal wise. Okay, so that means group in the case of group of countries. So some of these available literatures are highlighted here, and I am not going in details. So these are all details about the study, means background about this paper, and some of the limitations that some papers it is attached with only Arch model, some papers it is attached with GACH model, some papers attached with the VAR models. So this paper is a little bit unique in the sense that we have used different models here, as I have already pointed out here. So there are two different models we have used, MGACH and then BEKK model, so which gives some kind of different results, and that too again establishing that there is a still correlation between these two spot and future price. And methodology I have already mentioned, so everybody knows about the Arch and GACH process, and this is something related to again GACH clusters and that to MGACH clusters. So the basic model starts with simple equation like this, and then again we calculated the error estimations and then the volatility issue. So these are all various different aspects of models. So everybody knows about this GACH concept, so I'm skipping all these things. Okay, by the way, whether it is Arch clusters or ARIMA cluster or GACH clusters, any such time series clusters, even VAR cluster, so one of the basic requirement is to check the tenority, and we have also checked the tenority, and just to know whether the particular variables are having unity root or not. So after checking the tenority, we started the linking between these two variables, and then we checked whether there is a kind of correlation associated with these two variables. So these are all details about these models, and this is what the data details. And again, so we to normalize the data, we have used log transformations, and that to against with the help of this transformation, you can see the trends, and these are all various kind of aspects of trends you can see from different year wise. So there is UA spot and UA futures, and against spot futures and difference, there are difference. Okay, so this is how the kind of correlation coefficients, which first we started with the simple correlations, And then again, we have reported the descriptive statistic between these two, and somehow they are closely connected, and that too in a layman's language we can see that there is a correlations, and that too the correlation coefficient actually 0.99, so it's a highly correlated. Of course, since it's a time series data, then obviously there will be a high correlation. So that is how we'll move into different kind of models, just to see whether the correlation is really there in the context of spot and future prices. And these are all descriptive statistic, and against some of the volatility you can observe from here. And we can see that these volatility spots and futures are heavily link each other. That's the kind of objective of these papers. And again, some of the difference descriptive statistics are here. And this is how the GACH models, and you can see there is a peak here, and there is a huge volatility in this particular domain. So this is a conditional volatility of spot returns, right? So again, similarly, this is a conditional volatility for future returns. And of course, from this figure, you can clearly you can get to know that there is some kind of volatility is there, and we are interested to know whether these volatilities are connected to each other. So that means spot returns and then future returns. So this is how the details about the initial inspections, and then again on the basis of these models, so we have some results here, the important results, and that too I have already mentioned. So we start with the first testionality test, and we have used ADF, augmented decoupled test, and both the variables are ternary in nature, and that too at 1 level. So that means the level data is having unit root, and then first difference bringing the ternarity. And since it is having ternarity, so we use actually first difference data for this volatility modeling. So this is how this. So in the volatility modeling, so we have, since it's a GACH model, so we have two different kind of results. First the mean equations, and then the variance equations. That's the volatility equations. So the mean equations results are here. Of course, it is statistically significant, and also in the variance results. So both are also statistically significant. The error variance, errors, and again the variance. And then correlation equations, and it is also showing that there is a correlation coefficient here, statistically significant, and again it is also high, high correlations. And many of the cases it is statistically significant, but the significance, statistical level of significance are different. Sometimes it is 1%, but does not matter. But of course, our objective is to see whether there is a kind of volatility, and the volatility is actually statistically significant or not. Okay, some of the post hoc analysis we have also done, and this is how the dynamic correlation between spot and future price. And again, coming to spillover between the two series, so we have again different kind of models here, and that is MGACH models and VKK models. And this is how the models up to since equation number 18 to 21, and then the results are highlighted here. So we have two different two different results. First set of results is related to spot, and then second set of results future. So we expect that the spot is affecting the future, and future is also affecting spot, but because there is a correlation, and that we have already find that is statistically significant. So we have also taken different lags, and that too through AIC and SBC statistics. And some occasions some lags are statistically significant, and some are not statistically significant. But overall, overall conclusion is that future market having a significant relations with the spot, and spot is also having significant impact on futures. So the of course the results are not highly different. So whatever previous papers are there, and their findings are available. So this is somehow similar, but it is giving some kind of boost to the existing kind of findings, and that too with the updated data, and that too with the different means European context, and that too different group of countries, and against with the different modified models. So these are all little bit diagnostic checks. All these are statistically significant, and so then the next point is the effectiveness of portfolio hedging using futures, and against we use the variance covariance matrix, and that is that to again extension of this MGARCH VKK model, and that to against net returns we find out from these equations, and that to okay. So again, so this is actually coming highly significant. And finally, in summary, you can say that, most of our findings indicate that, high levels of dynamic conditional correlation between UA spot and future returns, as well as a high degree of, hedge effectiveness during the recent transaction phases. That means up to 2021. And the ongoing, that is the ongoing phase of, European Union ETS market. And the such findings coupled with the findings uncovered by prior studies relating to UA ETS phases, that to phase 1, phase 2, phase 3, helps us infer that UA carbon future market in the ongoing phase is more efficient when it comes to hedging once exposed to the spot market as compared to the previous phases of ETS markets. So I have already mentioned that the findings of this paper is not something very unique or something different. It is somehow closely connected to the existing studies, but the importance or the uniqueness of our study is to use different models, and that to again the data with the European context, and that to again updated up to 2021. So this is how we have actually drawn the conclusions, and I'm sure it will give some kind of boost to the spot market and future market, and that too it will give you some kind of boost to the energy infrastructure, and that too in the context of CO2 emissions. With this, I will stop here. Thank you very much.
Okay, thank you, Dr. Rudra Pradhan. Very nice talk. So I have to ask to the audience, is there any question to Dr. Rudra Pradhan? You can ask directly. So Dr. Rudra Pradhan, how you check the validation of the model?
Sir, we have actually, there are certain robustness checks we have used. First, there are three different types of test we normally use: specification test, goodness fit test, and some of the diagnostic test, and that too with the heteroscedasticity, normality. So autocorrelations. These are the indicators through which you check the validity of our models. Of course, the diagnostic results I have not reported here, and we have, of course, since it is a time series models, obviously your question is highly relevant, because if you use, different lags, then you will find different set of results. Then obviously in front of us, which particular model you have to consider while, finalizing or, analyzing your, outcome. So that's why there are two. First criteria is choice of lag length, and second criteria, the moment you fix the optimum lag length, then you have to see whether the particular model is effective against. You can have a different kind of changes. So for examples, one of the robustness we have applied, we have a different time period, means long time periods. So we use actually 70% of data, then 80% of data, 90% of data, and then with the help of error component, so we have finalized which one is actually very effective for our case. So that way we have checked the diagnostics part and effectiveness of the model.
So you can use this model for prediction, especially.
Yeah.
One question.
Yes, sir.
Okay, thank you.
This can be used at any time, means dynamic.
Any time, it may not be any time, because our findings is connected to up to 2021. The moment you change the data, then obviously results can change. So any statistical modeling, any statistical
can change, but that I understood. That is what result will change, but this is only for that particular data, or you can use at any time. That is my question. I don't know this type of research. That's why.
No, the model is actually a model. I have already highlighted the models. So now, if you like to actually predict the particular situation, so in this particular papers, whatever results I have already shown you, so that is specifically in the particular time frame. See, the moment you will change the time frame, then obviously the results may same, may different. Okay, but in 99% chance it will be different. Against, if you keep the time period constant, and if you change the different setups, because this is in the context of European Union. If you take a case of India or USA, then obviously the result will change. So but the model will be remain same. So because of course in the model, this is a broad models, but against the lag length can be changed, because when you change the data and when you change the kind of locations, then obviously lag length may not be same, lag length will be different. So that's why when you say that whether the model is typically useful for different context, the answer is absolutely no, because we don't know what will be happens if you change the time period and locations. So whether the lag length will be 2 or 5 or something like that. So depending upon the situations, you can first check, and then what the core model will be okay. But in a particular context, the lag length choice and the kind of findings, so that will differ. That will definitely differ.
Okay.
Is that okay, Professor?
Yeah, actually, that means once it is every assumption is made, you can use at any time. That's what you are telling.
Yeah. Of course, any statistical model always based with these certain assumptions. If you remove these assumptions, then obviously it will be very serious problems. And here again, we are assuming that other factors remain constant. For example, so we are just connecting spot and future price. So not guaranteed that other factors are not affecting in this particular linkage. So if you bring other factors, then that the relationship can be actually changed. Your question is very valid in the sense, because this is a bivariate link. So the moment you bring actually some other variables, some macroeconomic variables, then obviously keeping other things remain constant, still the model will change, results will change, because there are different variables which can affect differently. And again, if you use different variables, include one after another macroeconomic variables in this context, then probably the lag length will also change. The entire results will change, differently. So that's why there is no surety actually. So what will be what will happen when you say that whether it is typically used for every contest? The answer is absolutely no.
Thank you.
Okay, Professor.
Okay, thank you, Rudra Pradhan.
Thank you, sir. Thank you very much.
So I think this model can be used especially for EU ETS.
Yes, sir.
What about pandemic data? If you have pandemic data,
you are right.
To apply.
Yeah, this
like
is
COVID-19.
Yeah, this is very interesting questions. Of course, actually, we have not taken care of that particular issue. Yes, with the help of dummy modeling, we can actually capture that particular linkage. For example, so exactly during the pandemic time periods, so we can just use a dummy and then check whether there is a pre-post impact. So that is possible, but in this paper we have not done it, sir.
Okay, once again, thank you, Dr.
Thank you, sir.
Rudra.
Thank you very much.
So
Thank you,
very nice
Professor
job
Satish.
And very nice answer.
Thank you, sir. Thank you.
Thank you.
Thank you.
So, Professor Satish Kumar, shall I leave the session?
Yeah, and now let's conclude this session. In fact, we have a very good session. Professor Kamalesh, we like to extend our gratitude to you for chairing this session in a very better way. And all the speakers are also.
Thank you, sir. Thank you. Thank you very much.
Thank you, Professor. In fact, Professor Dr. Hemant Kumar, Dr. Manoj Kumar Tiwari, and Dr. Rudra Pradhan, all are excellent talks, in fact. And we have a In fact, thank you so much. Thank you.
Thank you, sir. Thank you.
Thanking you all. Let us conclude this session for the time being. Thank you, Rudra.
Thank you, sir.
And thank you all
Thank
others.
you very much.
Thank you, sir. Thank you. Thank you. Thank you very much, sir.
Thank you. Yeah. Now in the afternoon. Now we have the lunch break time. We 1 hour next to 2 p.m. In this main hall, our session organized by Kabir Issue of Harvard University on statistical process control will begin. And parallel at 2:30 p.m. onwards, there in the there is a competition on best paper research award. That best research paper award, like that. And we expect your presence and active participation in these sessions too. Thank you all. Let us conclude for the time being. Thank you.
Sir, good afternoon.
Good afternoon, sir. Good afternoon.
Good afternoon.
Good afternoon.
Professor, good afternoon. Good afternoon. How are you, Professor?
Yeah, fine. Now, yes. Hi. Okay. Good afternoon, everybody. Good afternoon. In fact, good morning, good afternoon, good evening.
Good afternoon, Professor.
Yeah, good afternoon. Now let us start the session. The special session, in fact, on septic process control, organized by Professor Kavya Restam of Bharatiyar University. Everyone are waiting for that. Sangeeta? Sangeeta, please introduce the chair and the organizer, Professor Kavya Restam, and then support him for the conduct of this session, please.
Okay, sir. A warm welcome to everyone. I hereby welcome you all to the technical session 31 with the session chair, Dr. V. Kaviyarasa. He is working as an assistant professor at Bharatiyar University, Coimbatore. His area of research include statistical quality control, data mining, data analysis, and analytics. He obtained his master's degree in statistics from PSG College of Arts and Science affiliated to Bharatiyar University in the year 2003. He completed his MPhil in statistics from Bharati Dasan University in 2004. He has several publications, including 2 international publications. He is serving as the co-principal investigator of the ongoing project Traffic-Related Air Pollution Hotspots in Coimbatore City and its adverse impact on human health. He is currently an EC member of Indian Society of Probability and Statistics and a lifetime member of Indian Bayesian Society. We are really lucky to have you, sir, with us today, organizing the session. Without delaying you further, I once again welcome you to the event on behalf of the organizing committee and kindly request you to take over the session. Over to you, Professor.
Welcome, Professor. Welcome, please.
Thank you, sir. I think the chair is by Vibiji sir, or it's not audible, sir. Can you unmute and talk, sir?
Professor, so as you are the organizer of this session, you have to chair also, to chair this session and introduce the speakers and coordinate the session in a smooth way.
Okay.
And make it a vibrant and active session.
Yes, sir. So first and foremost, I'd like to thank the organizer, Professor Satish, for giving an opportunity to to host a session in this conference. I really feel very happy and proud that the University of Kerala, the team, with under the leadership of Satish, is making a wonderful arrangements for every year with the 2 international conference. It shows the the love and affection what Satish has have with the Department of Statistics, specifically on statistics subject, and he really giving more importance to the researchers, specifically the budding researchers who are coming forward to share their thoughts and ideas in a forum like this. So I really congratulate to Satish and his team for organizing this conference, and also giving an opportunity to share my research areas in this platform.
Thank you, Prof. Thank you for your nice.
And also, in my session, there are totally 5 speakers, included me. The first topic is given by me, followed by one professor. Then another 4 professors are going to deliver the talk. I will come to their turn. I will introduce one by one of them once they have joined in this forum. So now my topic, what allotted to me is, first I share my screen.
Yeah, please.
My screen is visible?
Yeah, it is visible and fine, Professor.
Okay, sir, thank you.
Fine, sir. Fine.
Okay, so the topic what I took is Bayesian skip plot sampling plan for destructive testing under zero input Poisson distribution. So today, statistical quality control is a topic which widely used by the quality engineers, specifically in industries where they apply the statistical principles and they maintain the quality through various methods. But even we talk about Six Sigma quality, but when you go for small scale industries, specifically Coimbatore is a place where many small scale industries are available. So they are using the quality control techniques in their own concern. So SQC is a term used to describe the set of statistical tools used by the quality professionals, how they to improve the quality in day by day or year by year or the product by product what they are launching to the market. So it refers to the use of statistical methods in monitoring and maintaining the quality of products and services. So quality control is mainly used to monitor whether the production, when the engineering concept is concerned, they have manufactured a particular item. Before going to market, whether the quality is meeting the standards or not, and to maintain the quality to the people through the product and services. It tries to reduce the company's cost by reducing the losses due to defects and aimed achieving the interchangeability of the manufacturer's goods in large-scale production. So whenever we talk about the large-scale production, the companies are produce a huge amount of products, and when they want to export or when they want to distribute to the various vendors, they should ensure that they meet the standard quality or not. So it helps to produce optimal quality at a minimum price. It ensures customer satisfaction with products or services with high quality level. So to build customers' goodwill, confidence, reputation of manufacturers. So mainly when you think about the statistical quality control, it broadly classified into 2 broad headings called as process control and product control. So process control and product controls are 2 sides of a coin. One without another cannot be exist. Without process, there is no product. Without product, there is no process. So which are coincides one with the other. And here we ensure the focus on the product quality, how it going to meet the customers' requirements and also the manufacturers. So it here ensures the quality control at the proper stage with proper inspection to make sure that non-defective products are only produced and there is a judge. Judge may be the conformity of the process to the established standards and take a suitable action when there is a deviation. So we know that every product is alike, but still we can feel there are many differences. Specifically, when you want to buy a car, specifically a particular car of a particular model, for example, you consider Swift VDI. So all products look similar, but still there is a little deviations taken place, and the deviation to be reduced, and it should be met as a uniformity. The deviation means in the manufacturing process, the D is equal to S minus A, that is specification minus the actual limit. So when you come to the product control, that is when, according to Professor Dodge, has said that the major area of some sampling plan will be classified under the following 4 broad headings called by lot sampling plan by method of attributes, lot by lot sampling by method of variables, continuous sampling flow of units by method of attributes, special purpose plans including chain sampling plan, skip plot sampling plan, repeated group sampling plan, etc. So product control is a technique which may be obtained after the manufacturer, after the manufacturing of an item which is going to market. So here, the producer and consumer ought to be satisfied whether it meets the standards or not through the study of the acceptance sampling plan methods. So acceptance sampling plan methods is a technique in which a small part of the items is selected randomly from the lot, and these certain units are inspected to decide whether the lot should be accepted or rejected on the basis of the information provided by the sample inspection. From a lot, then we take a sample and we inspect and we come to a conclusion whether the lot is accepted or rejected. Why we want to go for some sampling plan? It is the middle of the road approach between no inspection and inspection. And there are 2 major classifications of some sampling plan called by method of attributes and method of variables. Anything which are measurable situations concerned, which are called as measure of variables, and non-measurables are called measure of attributes that we come studied in our postgraduate level. So when we go for acceptance sampling plan, so basically when the cost of the item is very high and destructive in nature, we are in a situation that we have to mandatorily go to for acceptance sampling procedures, specifically in the context of destructive testing. Destructive testing is a test method conducted to find the exact point of failure of a material or a component or a machines where the particular failure occurs. So during the process, the tested item undergoes stress that eventually deforms or destroys the material. So once the destructive testing is conducted, the items which we have tested, which destroys. So naturally, tested parts and materials cannot be reused in regular operations after undergoing destructive testing procedures as concerned. So the focusing on destructive testing is generally conducted before a component enters mass production. So here, this needs to know the limits of their products in order to give a proper maintenance and operation recommendations for their machines. For example, when you talk about the industrial boilers, are known for their ability to withstand larger pressure and high temperatures. The material chosen to build the boilers plays a huge role in determining the pressure of the temperature in the boiler. So failure of industrial boilers can cause some huge effect in their regular situation. So there are situations where the destructive testings are essential to study specifically on the product control is concerned. So whenever you talk about the destructive testing, which we talk about risk-based. So designing a sampling methodology in sampling plan can be broadly classified under these 4 broad headings called by non-Bayesian and Bayesian methodologies and risk-based and economically-based methods. So specifically, we have 4 types, and in this work, the designing methodology category 3, that is Bayesian-based, risk-based Bayesian methodology approach is considered according to the Hammaker 1960, what he said. So in sampling plan, we said there are many sampling plan like single sampling plan, double sampling plan, a sequential sampling plan, then repeated group sampling plan, etc. But skip lot sampling plan is one of the important plan which was introduced by Perry in 1972-73. A skip lot sampling inspection system of lot by lot sampling inspection plan, where here the methodology of attributes is mostly influential tool in real-time quality management system, which is more applicable specifically when we talk about bulk materials or finished products in the succession of consecutive lots, which an extension of continuous sampling plan. So this Perry introduced continuous sampling plan, and later he expanded the continuous sampling plan to SKSP2, SKSP3, and SKSP5, and SKSP, or like that. There are a lot of research works has been carried out, and many new forms are developed. So these plans provided with the skipping of some fraction of the lots submitted when the quality submitted lot is good, as demonstrated by the quality engineer. So in skipping inspection, the lots can be, the items which are tested can be inspected based on the performance of the item which is not defective in nature, which is good in the product convenient build. So the purpose of skip lot sampling plan is to reduce the ASN and ATI as well as the inspection cost is concerned. The skip lot concept is economically advantage to make a decision on the submitted lots. When the production is very large, it's a convenient build. There, we cannot able to go for 100% inspection, and we cannot go for we cannot accept any item without inspection. So when such situation occurs, the skip lot concepts which are economically advantage to make a decision about the submitted lot. So Bayesian acceptance sampling plan approach is associated with the utilization of prior process history, the selection of the distributions like gamma distribution, Poisson distribution, gamma Poisson or beta binomial, etc., to describe the random fluctuations involved in acceptance sampling plan methods. So Bayesian acceptance sampling approach is one of the vital area of quality control, specifically when we talk about skip lot sampling plan is concerned. So here, the user to specify explicitly whether the distribution of the item, the defective items from lot to lot has a prior information. That is, the prior distribution is the expected distribution of a lot quality on which the sampling plan is going to operate. So distribution is called a prior because it's formulated prior to taking of the samples. The combination of prior knowledge represented with the prior distribution and the empirical knowledge which a sample leads to the decision of the lot, where they need us to study about the Bayesian sampling plan. So in this Bayesian sampling plan, it consists of minimizing the average cost, that is expected cost, or including inspection cost and acceptance or rejection cost, all included in the minimizing the average cost through the Bayesian sampling plan. So Bayesian statistics is useful in random sampling, specifically when we talk on the reduction of the risk involved in the items which are considered for the study. So it takes into account the prior information in the sampling setup. It can update the information through the base formula to modify or adopt the sampling stringency according to the results which are available based on the corresponding probability distribution what we consider for our study. Bayesian sampling plan also removes the uncertainty on parameter of interest when decision making is concerned. So Bayesian single sampling plan can be a method where a single sampling plan is characterized by the sample size n and acceptance number c, sampling inspection in which the decision to accept or not to accept is based on the inspection of only one sample size, that is sample size n is considered. With acceptance number c, a decision can be taken which may be considered as a reference plan, specifically in single sampling plan, double sampling plan, STDS plan, RGS plan, a conditional RGS plan, all sampling plans are maybe considered as a reference plan, and skip plot plan, sampling plan can be considered the main plan. So here, in Bayesian sampling plan as considered, there are Hall introduced proposed a model to determine SSP employing polio and mixed polio distribution. Later, Hall discussed the Bayesian single sampling plan. And 1981, again, Bayesian single sampling plan minimizing the average cost sampling inspection was introduced to be called. Later, Brush 1986 has studied the producer risk under non-Bayesian and Bayesian plans are not to be same. Bayesian sampling plans have better, lesser sample size when compared to the non-Bayesian approach, that is traditional approach. Calvin 1990 has given some practical situations. The lot proportion non-conforming will vary over lots. Suresh and Latag has determined the Bayesian single sampling plan the condition of gamma Poisson distribution with a tangent at the inflection point. Lower in 2007 derived the OC function of single sampling by attribute under the condition of polio distribution and studied the behavior of OC curve with respect to the various set of parameters. And Vijayaraman 2007 et al. Analyzed the behavior of the OC curve of single sampling by attributes under the condition of gamma Poisson distribution. Various sets of plan parameters has been studied. Later, Muzira et al. In 2011 preferred the method of derive the OC function of single double multiple sampling plan for the statistical distribution under zero infinite Poisson gamma, in the study of carbonator as a powder infant formula method of application is concerned. They have given some results related to Bayesian skip plot sampling plan. Later, Kaviras and Sivakumar has developed Bayesian single sampling plan under the gamma Poisson gamma zip distribution, and repeating group sampling plan of the gamma zip distributions has been studied. So the distribution what we consider for this the proposed research study is considered a zero inflated Poisson distribution. In today's competitive world, every manufacturing company strictly follows the procedures at every stage of production to maintain the quality of items or strictly adheres. So in reality, the count data, when excess the number of zeros are present in, can hold a Poisson variable. So specifically when you consider the number of insurance claims received in two-wheeler insurance, the number of cigarettes smoked by students in a college, the number of defect items occurred in a container, continuous production of items, like that, the inflation of zeros are very high in nature. In such situation, the occurrence of defect items are rare phenomena, that is, the non-conformity in lots would be a major, be more in numbers with excess number of zeros are occurring. When manufacturing equipments are probably aligned in order, and the number of defects are impossible, say it is aligned with probability P, and the occurrence of defects follows the Poisson parameter lambda. Nowadays, every manufacturing industry follows strict procedures at every stage of productions for developing its own product quality. In manufacturing companies, they use the technological advancements and computer modeling or simulation to detect their product defects and handle them in initial stage of the production process. But a manufacturing item, a product of destructive or in nature, which is a combination of assembled of more components. So the technology advancements can always support to reduce the defective products at early stage and at every stage of the items which are assembled. However, due to the random fluctuations and some unavoidable reasons in the manufacturing process, there a situation may arise to lead a defective products within a batch of perfectly functioning production products may occur. In such circumstance, one can apply the zero inflated Poisson distribution to make an appropriate decision than the traditional Poisson distribution. So coming to this zip distribution, zero inflated Poisson distribution, these are the authors who have given some research work on the zip distribution. Lambert 1992 discussed the application of defects in manufacturing process through zero inflated Poisson distribution. Rideout et al. Discussed some models to count data with the occurrence of number of zeros. Boeing et al. Has discussed zip is better than the Poisson in dental epidemiology research. to measure the dental health. Rodgers have made discussion about zero inflated distribution Bayesian perspective. Naya et al. Established the comparison between the Poisson and zero inflated Poisson regression model with application to a number of black spots in the corridor sheet. Musida et al. 2030 reported the zip distribution is well performed to model the excess zero counts data and its OC curve. Lohner and Sholny developed a tables and procedure for single sampling by attributes under the conditions of zip model. Srinivasa Rao has designed the resubmitted laws with the attribute of single sampling and zip distribution. Kaviyarasu Asif and Kaviyash and Sivakumar have developed a few sampling plans with Bayesian and non-Bayesian perspective under the zero inflated Poisson distribution, which was developed with many authors. And Dodge proposed the skip plot sampling plan, and Perry given a system of skip plot sampling by lot inspection, and Parker and Kaiser 1981 given the modified skip plot sampling plan. Vijay Raghavan et al. Gives the selection of gamma Poisson distribution, and many authors has contributed for the skip plot sampling plan. According to Lambert, the distribution of the corresponding zero inflated Poisson model can be framed like this, with omega is the weighted parameter and lambda is the Poisson parameter, which can be operated with the operating procedure of SKSP2 is given with the operating procedure like with the 4 steps with I and F. When coming to the this research has given SKSP5, according to Perry, the operating characteristics of function SKSP5 has given with instead of Fi and also we include K, the number of lots, consecutive lots accepted under inspection, which was given in SKSP5. So SKSP5 has more parameter than SKSP2. SKSP5 plan has more parameter than SKSP2. The significant parameter of SKSP2 are I and F. That is I, the number of lots, consecutive lots accepted under normal inspection, and F, the lot fraction inspection, where SKSP5 has a new parameter called K. However, the result indicates that SKSP5 gives a better result in terms of ASN and in terms of ATI. SKSP5 was not statistically different in terms of product acceptance and AOQ, specifically for few situations. But the quantity from ASN, ATI, and cost of inspection based on at 5% level of significance were very much significant. SKSP5 significantly reduced the cost of inspection compared to SKSP2. So the SKSP5 plan has been studied. So in probability of acceptance, F, I, K are 3 parameters can be determined by a Markov chain technique with NR be the state where lot was rejected under normal inspection, and NJ be the state under normal inspection represents the number of considered lots, accepted lots called by J, and SA the state whether lots accepted during skipping inspection, state whether lots are rejected on the skipping inspection, SN be the state where lot is skipped, and P is the probability of acceptance of lot according to the reference plan. The properties of SKSP5 are given using these conditions 1, 2, and 3 for the various plan parameters according to the Perry. So the plot chart of SKSP5 is given like this. Start with the SKSP5. Specifically, when you start initially starting, you go with normal inspection. If if the I consecutive lots are accepted, yes, then go for skipping inspection. If it is no, then again go to normal inspection. If skipping inspection is instituted, then you take a random sample of lots and inspect whether it is acceptable condition or not. Yes, if it is acceptable condition, continue skipping inspection, or else you go for the how many lots have been accepted continuously with how many K lots. If K lots are yes, then you go with normal with reduced clearance number. Otherwise, you go for normal inspection. If it is normal reduced inspection number, then the items or continued lots are acceptable. Yes, then continue skipping inspection until all the lots are inspected, or else you go for normal inspection. So this is the continuous process where SKSP 5 has been instituted in the sampling inspection. So according to Holt, the simplest family of Fourier distribution in the acceptance sampling distribution of the number of non-component units X for the Z distribution is defined by the following way, with the number of defectives or considered as X is reduced with the gamma Z distribution. So basically, when you apply the Bayesian SKSP type 5 under the gamma 0 infinite Poisson distribution, a Markov chain technique can be introduced with the probability of acceptance of SKSP 2 or SKSP 5 plan. So a Markov process represents the observation of a system which satisfies the condition that the property of physical systems will given a state at time t2 will be detected from knowledge of its state at earlier time t1. So a Markov chain is a special case of Markov process in which a set of states or state space is discrete in nature. In this study, presents the concept of skip plan sampling plan 5 by attributes under Bayesian methodology can be studied with zero inflated Poisson scenario as concerned. So this is the selection procedure for the various planned parameter of operating process ratios of P2 by P1 has given. The sample size n can be obtained. The purpose of the study is to design a sampling plan which is useful to save the time and cost of the experiments for the producer and consumer. The product is to be inspected comprises a series of successive lots produced by an essentially continuing process. The size of the lot is taken sufficiently large under the normal condition. The lots are expected to be essentially the same quality, and the products comes from the source which is consumers with conferences are good in nature. The main goal is to be achieved if we find an optimum sample size n that satisfies either both the risk of producer and consumer. So the procedure of useful to minimize the sample size of the required sampling plan and increasing the production level at minimum cost. So here we can fix the sample size and we can find the corresponding acceptance, specifically the P1 and P2, and also we can fix the P1 and P2, we can find the sample size, which was explained with the numerical example for the SKSP 5. So if the quality engineer wants to determine the design parameters of AQL, LQL, beta, alpha, omega, and S, and they can develop the SKSP 5 plan, like with the sample size n is equal to 90, f is 1 by 4, I is equal to 2, omega is 0.1, S is 5, P1 and P2 are given with K equal to 2, alpha and beta are fixed here. So in the real-time applications where the SKSP 5 plans are really applied in industries. For example, many small-scale industries can execute this procedure. For instance, consider a brick manufacturing industries have the responsibility to produce the quality products to the consumer. Quality is not an one-time achievement, but it is necessary a part of planning, preparation, and execution, production of all days and all shifts. Any lack of consideration of quality can result in a serious threat to producer, specifically in their sales, and it affects the quality of the building. Suppose that a bricks manufacturer appoints a quality engineer, wants to run an experiment to make a decision on the product, either to accept or reject a lot, assuming the quality brick products follows gamma distribution with the prior process of S is equal to 5. So here we fix all the the parameters of the corresponding SKSP5, and we can find the sample size with 143, n is equal to 143. Suppose the brick manufacturer produces a lot of 3,000 bricks in a time, in that they have to consider 143 samples for inspection. In that the lots are accepted, then you continue the skipping inspection by fraction of the lots, or else you go for 100%, and you try to accept only one defective brick is accepted at the maximum level. So this study presents an optimal Bayesian skip lot sampling panel. Gamma's distribution is given for the various plant parameters. The proposed sampling plan is more appropriate when the production process is being well monitored and the prior knowledge available about the production process is known to us. The tables provides the OC values of the corresponding sample size for the producer and consumer risk compared with the SKSP5. The developed methods are provided with the handy tables, which can be very useful to the industrial lab floor conditions for minimizing the risk with better quality products are applied. These tables are useful specifically for both producer and consumer to obtain quality products with fewer cost of inspection. So here the needs are to consider all benefits may be given by applying SKSP2 plan or SKSP5 plan, but SKSP5 is better for the average total inspection and ASN, average sample number, but it involves more complications to control the process. While SKSP2 is an easier method to control, but when you have a larger production, then SKSP5 is more appropriate. And these are the references what I consider for my study. And now the forum is open for any discussions or queries related to my topic. Okay, if there's no queries, I thank the organizer and the participants for their patience listening within the stipulated time. I can able to give an overall idea of how the sampling plan can be instituted in industries. But when you go through, the person who are really interested to do research in this area can go through more research papers, and they can able to develop any new methodologies related to this area. So now we are having the second speaker, Professor Vikash B. Gude. Sir is working as a professor and head Department of Statistics at Punyashalak Agalya Devi Holapur Solapur University in Solapur, India. He has completed his PG and UG in PhD from Shivaji University, Kolhapur. He has a vast teaching experience of 32 years in UG and PG level. His research interest in statistical process control, statistical computing and non-parametric inference. He has published more than 40 research papers and worked as a reviewer in many international and national journals. He has delivered more than 50 invited talks in national and international conferences, seminars, and participated in many academic events. He is a life member of the Indian Society for International Indian Statistical Association and Indian Society for Property and Statistics, that is ISPS. So such experienced and a personality who come here to deliver his talk. We are very happy And on behalf of the organizing committee, I welcome our professor to give his talk on his allotted topic and take a time limit of 30 minutes for your talk, sir. Well, hand over session to you, sir. Thank you, sir.
Thank you, sir. Thanks for nice introduction.
Thank you, sir.
First, I would like to thank organizers of ICSTC 2022 for giving me opportunity to deliver invited talk in this conference. Good afternoon to all. The topic that I have selected for this talk is double moving average control charts for process parameters with auxiliary information. So, as we know, in statistical quality control or in statistical process control, control chart plays a very important role. While process is ongoing, the control charts are used to check whether the process is in control or out of control. Generally, two types of control charts are used for monitoring the production process. First one is the location chart, or we call it as the mean chart, and second one is the variability or dispersion chart. Now, in present situation, Chiohar type control chart, that is X bar chart, is used to monitor process mean, and Chiohar type R and S charts are used to monitor process variability. Now, some authors have suggested to use S square control chart, that is monitoring process variance, instead of Chiohar R and S chart. Now, when we use these type of charts, these are not efficient for detecting small process shifts in the parameters, because all these charts are based on the current information about the sample. Therefore, these are efficient only for large shift in process parameters, and for small shifts, these are not suitable. So, an alternative control charts to Chiohar type of control charts are the memory-based control charts, like Kusum control chart, EWMA control chart, or moving average control charts. All these control charts are incorporating the previous information from the sample as well as the current information, and therefore these charts becomes most efficient for detecting small shifts in process mean as well as process variability. So these charts are called memory type control charts and are efficient for detecting small shifts in process mean and process variability. Now, out of these three memory type control charts, here we focus on the moving average control chart. So, moving average control chart is used to monitor the process parameters of the production process. Now, this is a picture of control charts which considers upper control limit, lower control limit, and central line. And after some suitable time period, equivalent time period, samples are taken from the production process. Some statistic is calculated, and that statistic is plotted on the control chart. If all the points lie within the two control limits, then we say that the process is in control. And if any of the point lies outside the upper control limit or below the lower control limit, then we say that the process is out of control. So in literature, many authors have developed the moving average control charts. For example, Wong in 2005 developed combined moving average control chart, then Ko and Yap, Aditi, Bhutte and Rajmanye, and many other authors have also developed the moving average control charts for monitoring the process parameter, because this chart is suitable or efficient for detecting small shifts in the process parameter. So in process monitoring, when there is a shift in process mean or in process variance, then the performance of the process can be changed. That means in control process goes to out of control. Therefore, it is essential to detect change in the process parameter as early as possible. Otherwise, if we are unable to detect the change in the process parameter, then the produced items becomes defective and we say that the process is out of control. Therefore, it is more important to detect shift in process parameter as quickly as possible. Now, these traditional control charts like Shehar type control charts or Kusum type control charts, they are always popular control charts and widely used in production process to monitor process mean and process variability. But in order to increase sensitivity of these charts, to increase the sensitivity means to develop the control charts which can detect shift more earlier than the traditional control chart, then such type of control charts we call it as the sensitive control chart. So many authors have developed the different strategies to improve the performance of traditional control charts. Some of these strategies are use of runs rules or use of double sampling. Instead of taking single sampling, we take sample twice from the process and then take the decision about the process. So it is double sampling plan or synthetic control charts, use of run rules, use of adaptive control charts. All these are the different techniques. One such technique that is used in production processes auxiliary information based control charts. In short, we call it as the AIB control charts. So AIB control charts collects the information from study variable as well as information from some auxiliary variable. So in order to monitor the production process, if we collect the more information from study variable as well as auxiliary variable, definitely control chart will improve its performance. So this is the logic behind using the auxiliary information in the control chart techniques. Now, traditionally, when we use control charts, we consider X as the quality characteristics or variable under study. In auxiliary information control chart, we consider two variables. For example, in single variable, if we consider X as the measurement like length of the some produced item. So in order to monitor this length, we use X bar chart for monitoring the average, or we use R or S chart for monitoring the dispersion. But in auxiliary based control chart, auxiliary information based control chart, along with the quality of interest length, we consider one more quality characteristics. And that quality characteristic we call it as the auxiliary variable. So for auxiliary information based control charts, we collect the data from two variables. One variable is study variable, another variable is the auxiliary variable, and further we assume that there is a correlation between these two. That means these two variables should be correlated. For example, if we consider one example of study variable and auxiliary variable, that is in bottling operation. In bottling operation, important property is the net weight, which we call it as the study variable. Weight of that bottle, we call it as the study variable, and time for filling the bottle, it is called auxiliary variable. And we know both of these two variables are correlated. So in this paper, we consider auxiliary information to construct moving average control chart, and further we improve the performance of this moving average control chart by using double moving average technique. So in order to measure the performance of control chart, we use ARL, that is average run length, as the performance measure. Along with ARL, we also measure the standard deviation of run length, which we call it as the SDRL. So ARL and SDRL, these are the performance measures of the control charts. Now again, ARL can be divided into two parts. First one is in control ARL and second one is out of control ARL. So in control ARL means the number of points to be plotted on the control chart in order to get first out of control. So when the process is in control, so in control ARL should be as large as possible. And when process is out of control, the ARL should be small. That means once the process parameter change, we can detect it as early as possible. So out of control ARL should be small. So when we compare the performance of two different control charts, so in order to compare performance, first we have to same in control ARL for both of the chart, and the out of control ARL of the both control charts for given shift are compared, and chart which is having smaller out of control ARL, that control chart is called superior control chart. So smaller out of control ARL, it indicates the early detection of shift in the process parameter. So here first we use our traditional control chart. Instead of X bar, we call it as the Y bar control chart, because in our auxiliary information based control chart, I have considered Y as the study variable and X as the auxiliary variable. So study variable is the monitoring variable, and therefore Shewhart Y bar chart, it is based on the assumption that the sample observations or measurements are normally distributed with mean mu zero and variance sigma square. And that chart we plot the statistics Y bar on the control chart. And lower control limit and upper control limit of this chart are given as LCL is equal to mu zero minus K sigma, and UCL is equal to mu zero plus K sigma. So these are the control limits. And within these control limits, we can plot the points Y bar I. If all points lies within the control limits, then we say that the process is in control with respect to mean, otherwise it is out of control. Now similar, in order to monitor process variance, here we use S square control chart, where S square is nothing but sample variance 1 upon n minus 1 summation yi minus y bar bracket square. It is sample variance, and it is we have to monitor. And therefore the control limits for S square control charts are given by LCL and UCL, and central line is equal to sigma square. So within these two limits, UCL and LCL, we can plot the values of sample statistic SI square. If all lies within control, then we say that it is process is in control, otherwise process is out of control. So these are the traditional control charts which we use for monitoring the process. Now next is Shewhart type auxiliary information based control charts. As I have told earlier, auxiliary information control charts requires two variables, yi and xi. Yi we call it as the study variable, monitoring variable, and xi is called auxiliary variable. So here we consider yi, xi as a bivariate random sample from normal distribution with these parameters mu x, mu y, sigma y square, sigma x square, and rho, where rho is the correlation between study variable and auxiliary variable. Now, in order to monitor process mean, we use the statistics, auxiliary information based statistics M. It is called regression estimator of the population mean of study variable. It is also unbiased estimator of mean of study variable, and therefore this M is taken as the control charge statistic for our AIB chart. So in order to obtain the control limits, 3 sigma control limits of the control chart, we require mean and variance of this chart. So mean is given by expectation of M mu y, variance of M, and based on this mean and variance, the control limits of this chart are taken as LCM and UCL. So all these values are known, only K is unknown, and value of K is selected such that the in control area is some specified value like 200 or 370 or 500 and so on. So by selecting the appropriate value of K, it is based on in control area. So this is called auxiliary information based control chart for mean, and we call this chart as the M chart. Of course, the performance of this M chart is better than Shehart X bar chart because this auxiliary information control chart uses the information in two variables, study variable and auxiliary, and Shehart X bar chart uses the information only single variable, so it is superior to Shehart X bar chart. Now, similarly for monitoring variability, we use the auxiliary information based statistic V. So this is statistic V. It is also the regression estimator of population variance sigma y square, and it is unbiased estimator of sigma y square. Therefore, instead of using S square in traditional Shehart chart, we use this statistic, V statistic, as a control chart statistic for monitoring process variability. Mean and variance are given by these two equations, and based on this mean and variance, the control limits of auxiliary information based V chart, these are given by LCL of V and UCL of V. And by drawing the control chart with these control limits, we plot the different value of V statistics on the chart, and if all value lies in the control limits, specified control limits, then we say that the process is in control, otherwise it is out of control. So these are called simple auxiliary information based control charts. Now we use this AIB statistic, namely M and statistic V, to construct moving average control chart. So moving average control chart for monitoring process mean, it is simply moving average of these statistics, that is MAI. It is the sum of MI plus MI minus 1 plus MI minus W plus 1 for I greater than W, and for I less than W, we take the actual mean of the available samples. So this is called the moving average. Now our next job is to construct this moving average as a statistic for constructing the control chart, and that control chart we call it as the M chart, moving average M chart. Of course, for its construction, it requires control limits of the chart, and in order to obtain the control limits, we need mean and variance of this statistic, MA statistic. So mean and variance of this MA statistics are given here. Expectation of MA is mu y, variance of moving average statistic is this, and we use this mean and variance. We compute the upper control limit and lower control limits of the chart for different values of I greater than W and I less than W. So this is moving average chart. We call it as the EMA. Now, instead of this, these are the auxiliary information based statistics, and these are used to obtain moving average. In next step, that is DMA control chart, we consider this moving average statistic as the observation, and we obtain moving average of this moving average, so we will get the double moving average. So this is the statistic which we call it as the double moving average control chart statistic, we obtain its mean and variance, and we obtain control limits based on the mean and variance. So this is the double moving average control chart for monitoring the process mean. Now we have three type of charts for monitoring process mean. First chart we have seen is the Shehar Y-bar chart. Second chart that we have seen is the auxiliary information YUM chart. Third chart which we have seen is the moving average YUM chart, that is MA YUM chart, and fourth one is the DMA YUM chart, double moving average YUM chart. And in next evaluation section, we see that first chart is, second chart is superior to first, third is superior to second, fourth is superior to all of the earlier control charts. So all entire this derivation is for monitoring the process mean. For monitoring the process variability, we use the same procedure, that is double moving average control chart is based on twice of the subgroup moving averages, and moving average statistic for sequence, it is given by DMAI. This is mean, this is variance, and based on this mean and variance, we have obtained the control limits for monitoring the variability also. The procedure that we have explained earlier for moving average YUM chart and double moving average YUM chart, the same procedure is extended for moving average V chart and double moving average V chart, and we get these control limits. Now, after developing this theory of the moving average and double moving average control chart, in this section, we have considered the performance evaluation and comparison. So, we measure the performance of all these control charts by using simulation. Subgroup sample size, we have taken n equal to 10, 15, 25. Then correlation between study variable and auxiliary variable, we have considered three levels of correlation. 0.3 that is low correlation, 0.6 median correlation, and 0.9 as the high correlation between two variables. And first we consider the evaluation of moving average and double moving average control chart. So in order to compare the performance, we consider in control process as the bivariate normal process. That means observations are generated from normal distribution with mean 0, 0, variances 1, 1, and correlation is rho. So this is common for monitoring process mean as well as process variance of all considered chart, that is auxiliary chart, moving average charts, and double moving average charts. Now for mean control chart, the out of control procedure is considered as normal with shift of size delta in the mean of study variable y. Remaining values are same, but here we consider shift of size delta. And in our simulation study, we consider different shift size in the process mean. Initial process mean is 0. We consider the shift of size 0.1, 0.2, 0.3, 0.4 up to 0.2, and out of control ARL values for the moving average and double moving average control charts are obtained for different span periods, that is W is equal to 2, 3, and 4. And this performance is presented in this table. So this is ARL comparison of mean control chart, subgroup sample size n is 10, and in control ARL which we have considered is 200. So this is shift in process mean. Initial mean 0, that means there is no shift in the process. So in control ERL of all the charts is approximately 200. The values in the parenthesis, these are the SDRL, that is standard deviation run lengths. Now here in control ERLs are same. That means all the charts are now comparable. Now for first shift, suppose there is a shift of size 0.1 in the process mean. Then Shewhart type mean chart detects this shift after approximately 137 points. After 137 points. Auxiliary information based control chart detects that shift after 132 points. After plotting 132 points. That means chart detects shift earlier than the Shewhart. So chart is based on two variables, auxiliary variable and study variable. So it detects shift earlier than the Shewhart chart. If we consider, instead of chart, if we consider moving average chart, that is memory type control chart. So this control chart with span W equal to 2, it detects shift after plotting the points 104. That means again this chart detects shift earlier than this. For span of period W equal to 3, it detects after 87 points. For W equal to 4 after 77 points. That means this moving average chart detects shift in process parameter earlier than the traditional Shewhart chart as well as the simple auxiliary information based control chart. Now, instead of this moving average, if we further improve this by taking double moving average. So this double moving average chart with W equal to 2 again detects shift earlier than the other chart. So this chart require 137, this chart require 132, this chart require for W equal to 2 104, here W equal to 2 only 93. So after plotting 93 point, so DMA chart detects shift in process parameter. So this simulation study is conducted only for small correlation rho equal to 0.3 between the study variable and auxiliary variable. If we increase the sample size, increasing sample size means gather more information, or increasing the correlation, these out of control ARL values again become smaller. So out of control performance of the control chart improves when we increase the sample size as well as we increase the correlation. So this is for rho equal to 0.3, and shift we have considered are 0, 0.1, 0.3, 0.4, 0.5. Similarly, next 0.6 to 2. And K is the control limit constant, which is based on the in control ARL 2000. Now in next table, we consider n equal to 10. We have increased the level of correlation 0.6. So these ARL values are becoming smaller. Similarly for 0.9, that means as the correlation between study variable and auxiliary variable increases, the out of control ARL value again becomes smaller, and so the performance of the control chart gets better. So again, this is for improved n equal to 15, rho 0.3, 0.6, 0.9. So, and in next table, we can increase the sample size n equal to 30 for different levels of correlation. We get the improved performance of the moving average control chart as well as double moving average control chart. Now, same simulation study is applied for variance control charts, that is moving average V chart and double moving average V chart. Simulation constants are taken, only shift in process variance are taken as in control process. We call variance is equal to 1, and then we increase the variance by 0.1, 1.1, 1.2, 1.3, and up to 3. And we get the same performance. Or in control process, when there is no shift in variance, sigma y square equal to 1, S square charge, V charge, moving average V, double moving average V, in control ARL of all the charge is same. When there is a shift in process variance, S square charge detects it after 62 points, V charge detects it up to after 46 points, W charge 36, and double moving average charge 34. So out of these 4 charts, double moving average chart detect shift in process variable earlier than the remaining chart. So this study is conducted for different correlation levels, that is rho equal to 0.3, 0.6, 0.9, and also for different sample size n equal to 10, 15, and 20. And we get the improved result as we have seen for the moving average EM chart and moving average, double moving average EM chart. So final conclusion is, here we have proposed auxiliary information based control moving average and double moving average control charts to efficiently monitoring mean and variability of normally distributed process. The proposed control charts utilize the information on auxiliary characteristic for monitoring the process mean and process variance with respect to single quality characteristic Y. Using extensive Monte Carlo simulations, the run length characteristics like ARL and STRL of the proposed control charts are computed, and detection ability of proposed chart is compared with its existing counterparts, and it has found that the proposed chart performs better in detecting different mean and variance shift size. So these are some references which are used for preparation of this talk. Thank you. If any questions?
Thank you very much, Professor VB.
Hello, sir.
Yes, sir.
Nice talk. I think that's a question from Professor Sunday.
Simple question. How do you use in industrial environment this auxiliary variable data? How do you collect? Which situation? Do you have such situation where auxiliary variable data can be collected?
As I have given one example in bottle filling experiment. Okay, the net weight of the bottle, it is the study variable, and time required for filling that bottle. So we can take it as the auxiliary variable, and such type of information can be, in some cases, it can be easily available. The cases in which the information is not available, then we use our traditional control chart. Sometimes if we want to...
Can you use the auxiliary variable as a binary type, go, no go type?
Binary variable.
That means if you have a specification, for example, diameter or thickness, if it lies in if it passes go test, go and no go test, then it is okay. And in that case,
it will be the attribute data.
Yeah, that will be attribute data. X variable may be giving you attribute kind of data.
And in attribute data also, such work can be extended.
Yeah.
Yes.
So that is easily in the industrial environment case. X variable can be attribute data, and Y variable available only for restricted observation.
Yes, sure.
Okay. Good presentation, sir.
Thank you, sir.
So any more questions from the listeners?
Thank you, sir.
So if there's no questions,
Thank you.
we
Thank
thank
you, sir.
Professor
Thank you.
VBG sir for his nice talk.
Good.
Thank you very much, sir.
Okay.
So next we have the third speaker of this session, number 31. I call upon Dr. S. Jayalakshmi, Assistant Professor, Department of Statistics, Bhadyar University. Madam, are you there?
Yes, sir.
Yes.
Yes, sir.
So, Madam is working as Assistant Professor in the Department of Statistics, Bhadyar University for the past 6 years. And before that, she had a wider experience in teaching in statistics. Madam is working in statistical quality control research area. Its research area interest is in quality control, specifically on reliability sampling plan and the quick-switching system. So on behalf of the organizing committee, I welcome Dr. S. Jayalakshmi to present her research findings. Ma'am, over to you, ma'am.
Yes, sir. Thank you, sir. Very good afternoon to one and all present here in this forum. First of all, I would like to thank the organizing committee for providing this wonderful opportunity to deliver my talk. Now I am going to talk on designing on special type double sampling plan based on truncated light test using exponentiated generalized temperature distributions.
Madam, can you make it a bigger screen?
Yes, sir.
Can you make it a bigger screen?
Full screen is there.
I think it's not full screen.
Okay. Now it's okay, sir. Hello.
Please go to presentation mode.
Yes, ma'am. Yes, sir.
Use the slide presentation, this right hand side.
Yes. Or you press F5.
I think there is problem if you go to full screen, no? So it goes.
Now it's okay, sir.
No, it is not getting presented.
It's not shared.
Again, share and continue in the same mode. I think so.
Yes, ma'am. First you share it. Share the screen, ma'am.
Yes, sir.
Yes. Now you, in the bottom right, you can see a symbol called by like a cup. Just click it. Yes, ma'am. Come down.
Yes, sir.
Come down. Come down. In the bottom.
1 minute. 1 minute, sir. 1 minute, sir.
Right hand side.
Right side. No, it's got exit.
There is some problem.
Yes, sir. Yes, professor. There is some issues, I think so.
You may continue in this mode only, I think so.
So now it's okay, sir.
Okay, we will continue, but you have to move the screen. The screen will not be moved automatically.
Okay, sir. Yes, sir. So statistical quality control. So all of you know as statistics means data, a good amount of data, simply as a collaborative study of accumulation, analysis, interpretation, and presentation of massive value of data. Then quality control means quality is nothing but a characteristics of fitness for a purpose at lowest cost or degrees of perfection and that surveys to the customer requirement. Then quality control. Then statistical quality control can be simplified the defined as an economic and effective system of maintaining and improving the quality of output throughout the whole operating process of specification, production, and inspection based on the continuous testing with random samples. Then statistical tools and techniques in order to monitor and manage the product quality access various industries including food manufacturing unit. The process is named as statistical quality control. It mainly Statistical data reports to access the quality and is therefore an efficient means to evaluate the manufactured product. That SQC helps maintain the consistency of how a product is made. Then statistical quality control method can include cause and effect analysis, check sheet and tally sheet histogram, Pareto and scatter analysis, data stratification, defect map, event log, progress centers, and randomizations. The graphical charts and the graphs are the part of the statistical process control that monitoring the manufacturing process helps the statistics data from the quality control report. And then we go for the statistical quality control. The mainly in statistical quality control broadly divided into three categories, such as descriptive statistics. Descriptive statistics means to describe the quality characteristics and relationship. Then statistical process control. Then process control to inspect the random sample from the output of the process and decide whether the production process is in control or out of the control. And the statistical product control to inspect the random samples from the finished or semi-finished production and decide whether to accept or reject the entire lot based on the sample results. Then we go for the in product control. In acceptance sampling can be used when the decision must be made to accept or reject the group of a part or items based on the quality found in the sample. So mainly in this paper concerned with the product control, which aims in assuring a certain prescribed quality level of skipping or accepting salad. So generally, 100% inspection is neither possible nor economically sensible. Therefore, product control is performed by means of statistical procedures. So usually in acceptance sampling, there are only two decision admitters with respect to a lot in Gaussians, which are called acceptance and rejections. With different models of the performance of the statistical procedure cannot be as good as 100% inspection, and it should be improved with an increase in the sample sizes. So in the limiting case of each item of the populations is sampled, the statistical procedures should lead to the same decision as taken in the case of full information. Clearly, statistical procedures being not able to guarantee particular the last demand should be applied. Only the extreme case that there is a no better procedure is available. So, in that situation, the acceptance sampling technique is used to inspect the quality of batch of product. This quality product batches, it involves comparing the number of defective pieces and the preferred predefined acceptance number to accept or reject the batches. In sampling plans, there are many sampling plans are there. First, a single sampling plan, double sampling plan, special type double sampling plan. So for next we go for acceptance sampling basic procedures. First, the random sample is taken from the large quantity of the item and tested or measured relative to the quality characteristics of interest. If the sample passes the test, the entire quality called a lot of items is accepted. If the sample fails the test, two scenarios are possible. Either the entire quality of the item is subjected to 100% inspection and all defective items would be replaced with the or whole quantity is returned to the supplier. The main purpose of the acceptance sampling is to reduce the likelihood that defective part will be included in the final product. By using this method, companies can ensure that only high quality product are sold to consumers, which makes them more likely to make repeat purchase. Then acceptance sampling allow companies to determine if their product meet their standard before they begin mass production or distributions. If it does not meet their standards, they can reject that batch and start a new instead of continuing down the path towards producing something less than satisfactory quality wise. Then mainly use of acceptance sampling. Determine whether or not a batch of product should be manufactured. Testing the effectiveness of new manufacturing process and the equipment. Checking if there is any issues with the existing product. To determine whether a product conforms to specified and standards. And to check that an assembly process has been completed successfully. To test the samples of product before they are sold to the consumers. Then we go for the types of risk. Here in acceptance sampling, the type 1 error is probability of rejecting a good lot is denoted as alpha. Here are producer risk. 5% in producer risk, 5% is common. This producer risk means risk associated with a lot of acceptance quality. Is rejected. Then type 2 error, here probability of accepting a bad lot. Here denoted by beta, then consumer risk and also denoted by consumer risk. Here 10% typical value. Consumer risk mean accepting a lot at a rejectable quality level. Then advantages of acceptance sampling. Here acceptance sampling is mainly used for testing for samples from customers. Reduce the inspection cost by reducing the number of items is inspected. So increasing flexibility in production schedule and reduce the inspection time for each item due to less number of items being inspected at one time. You can use for almost any type of the productions or services. It does not require much training. It helps manufacturers determine whether their product meet certain minimum standard for quality. Then we go for the first sampling plan, in single sampling plan. In single sampling plan, sampling inspection scheme in which a decision to accept or reject the inspection lot is based on the inspection of single sampling plan. The operating procedure of the single sampling plan, draw a random sample of size n from the lot in capital N received from the supplier of the final assembly. Inspect and every unit of the samples and count the number of defective D. Then compare the number of defective units found in the sample with the acceptance number C. If D less than or equal to 0, then accept the lot. If D greater than or equal to 0, then reject the lot in single sampling plan. Then we go for the double sampling plan. Double sampling plan, mainly double sampling plan use, we reduce the average sample size and still have the same producer and consumer risk point. The double sampling plan consists of N1, C1 and R1, which are the sample size acceptance and rejections number of the first sample. Then N2, C2 and R2, which are the sample size acceptance number of the rejection for second sample. Here the operating procedures for double sampling plan. Select the first sample of size N1 and count the number of defective D1 during the time. Then D1 less than or equal to C1, first acceptance number C1, then accept the lot. Then D1 greater than or equal to C1, reject the lot. Then in between C1 and C2, if D1 is, select the second sample of size N2. Then count the number of defective D2. Then go for the D1 plus D2 less than or equal to C2 when accept the sample. Then D1 plus D2 greater than or equal to C2, reject the sample. Then the extension of double sampling plan is a special type double sampling plan, also known as the 0-1 double sampling plan. It is an extension approach of the double sampling plan. The operating characteristics the procedure of the special type double sampling plan under Exponentiated generalized Pritchard distribution is very simple as given below. A random sample of size n1 for first sample size units are taken from a lot and observe the number of defective D1. If D1 greater than or equal to 1, reject the entire lot. If D1 equal to 0, we select the second random sample of size n2 and observe the number of defective D2. If D1 less than or equal to 1, then accept the lot, otherwise reject the lot. In that situation, situations, we go for the reliability acceptance sampling plan. The experiment were carried out to verify whether the lifetime of the product may follow the life test experiment. A sampling technique used to sentence about the disposition of lot based on the product lifetime, such as sampling plan is called as reliability sampling plan. In reliability sampling plans are used in manufacturing industry to take decision on the disposition of lot based on the life testing of product. Such plans are developed taking into the consideration of relevant probability distributions of the lifetime of the product under testing. In the life testing, censoring scheme are adopted in order to save time and cost of the life test. Reliability is the probability of performing without failure specified function under the given conditions for the specified period of the time. Then reliability sampling plan consider obtaining the acceptability of an item at the for the point of view. It is includes some type life testing, whereas acceptance sampling plan are used on the lot by lot basis and a very beneficial approach to maximizing the quality at lowest level. Then acceptance sampling must be proposed in the usual way when the inspection preferred, and it is also primarily tools of the acceptance control. Then truncated life test. The technique behind the acceptance sampling first start by describing the minimum sample size required to maintain a specified mean life when the life test time is stopped at the predetermined time. These particular kind of the experiment are called truncated life test. The truncated life test used to save the time and cost inspection. Then we go for the exponentiator generalized Pritchard distributions. In the cumulative distribution functions and probability density functions for exponentiator generalized Pritchard distributions are given below. Here, alpha, beta, and gamma are the shape parameters, and the sigma is the scale parameters. And then first we consider the percentile estimator. Percentile estimator here probability of t less than or equal to tq. Here time t considers specified time. The specified time tq is calculated as the given formula. Then the cumulative distribution function of the exponential generalized Pritchard distribution is then special type double sampling plan for exponentiated generalized Pritchard distributions. To design the special type double sampling plan for the truncated life test, it is essential to first to determine the sample size, then operating characteristics value, and producer risk ratio between two lifetime and the specified lifetime. The submitted lot will be acceptable. The first test various confidence level, which 1 minus P star. Here P star is a producer risk. Then operating procedure. The following steps of the operating procedures for special type double sampling plan based on truncated life test. Draw a random sample of size n1 from the lot and put on the test for pre-assigned experimental time to observe the number of defective D1. If D1 greater than or equal to 1, then reject the lot. Then step 2, if D1 equal to 0, then draw a second random sample of size n2 and put on the test for time t0. and observe the number of defective D2. If D2 less than or equal to 1, accept the lot and otherwise reject the lot. Then first we consider the minimum sample size. The sample size are denoted by the parameter N1 and N2. First sample size, second sample size in special type double sampling plan. The probability of accepting in the probability of acceptance provided by the proposed sampling plan by probability of P, that is equal to P is denoted by distribution function. The equations used to determine by N1 N2 make his minimum sample size. The performance of the sampling plans in differentially the quality of the submitted product during the product inspection time is described by the operating value. The operating characteristics function is L of P, these expressions. Then producer risk ratio. Here the producer risk is the probability of rejecting the good lot. When TQ greater than or equal to TQ naught. Here TQ is actual percentile. Here actual percentile for fixed that value. Then TQ naught is a specified percentile value. And the ratio of the actual lifetime to the specified lifetime is TQ divided by TQ naught. Then probability of acceptance using these equations. Then alpha equal to 0.05%. Then DQ is a percentile ratio of the producer risk, that is equal to TQ divided by TQ naught. Then some numerical illustration. A quality inspector conducted an inspection of sewing machine needles of lifetime. Exponentiated generalized feature distribution was used to conduct the lifespan testing of this sewing machine needles. The shape parameter are alpha, like 366. Then inspector wants to conduct the test terminating a lifetime of 40 hours, but the inspector has conducted the actual time of the 50th percentile of, so T 0.50, that is equal to 25 hours. C1 equal to first acceptance number 0, then second acceptance number C2 equal to 1, then parameters alpha equal to 0.05, then consumer risk, then beta 0.10, producer risk. Then the probability is 1.074 is calculated from in the table. The inspection was conducting the lifetime of the test within the time limit is 25 hours. If D1 greater than or equal to 1, then reject the lot. Inspector used the special type double sampling plan operating procedure to make the following decision. If D1 equal to 0, then go to the randomly selected the second sample N2. If D2 less than or equal to 1, then accept the lot, and D2 greater than or equal to 1, then reject the lot. It remains that if the actual lifetime of 50th percentage near to approximately predetermined lifetime of T naught, here T naught is 0.50, then specified time TQ naught is 0.50, that is equal to 1.15. Then producer is nearly 0.9988. So the producer risk is approximately to be 0. Then the true lifetime of 50th percentile is greater than or equal to the 1.45 times the specified 50th percentile. Here the operating characteristics curves are there. Here x-axis is specified time corresponding probability of acceptance. The specific time increases, then probability of acceptance also increasing. Then construction of table. Here step 1 we calculate the value of probability of acceptance 1.704, then acceptance C1 equal to 0, C2 equal to 1, then parameters alpha equal to 3, beta equal to 6, then gamma equal to 6, then T divided by TQ, then set a value of N1 and N2 satisfy the conditions of this equation. Then step 2, introduce the constant value of TQ divided by TQ naught. That is a percentile ratio in the producer risk. And to find the value of probability of acceptance, applying the value of N, C and P, then using this probability of acceptance, these equations. Then step 3, for the minimum sample size of N1 and N2 value, we get the ratio DQ. The DQ means producer risk percentile ratio. Then we go for the conclusion. In this paper, we consider special type double sampling plan based on the truncated life test using exponentiated generalized Pritchard distribution. It is assumed that the shape parameter is known, and we have the presented the table for the minimum sample size required to guarantee a certain median life of the experimental unit. We have also presented the operating characteristics function value and the associated producer risk. Special type double sampling plan is more adaptable and less inspection cost on the time. As a result, it is highly advised that industry utilizes the proposed plan for the lifetime testing of electronic goods. This is for the table. Here in column P star is probability of acceptance, then time, actual time and specified time, N1 and is sample size. Then here producer risk ratio in table 2, ratio producer risk ratio corresponding acceptance number value. Then these are the references. Thank you.
Thank you, Dr. S. Jayalakshmi, for your presentation. Now the forum is open for any doubts or queries or discussions. If there is no queries, let me thank the speaker on behalf of the organizing committee and my personal behalf. I'd like to thank Dr. S. Jayalakshmi for his valuable time with us to share his research in this forum. Thank you very much, Jayalakshmi.
Thank you, sir.
And now I call upon the next person, Dr. S. Shivashankari.
Yes, sir.
Madam Shivashankari, are you there?
Yes, sir, I'm here.
Can you turn on the camera and because there's a comment given in the to turn on the camera. Yes. Yes, ma'am. Dr. S. Shivashankari is working as a guest faculty in the Department of Statistics, Bharatiya University for the past 1 year. And she got a vast experience of teaching experience in Krishna College, Sri Krishna College of Arts and Science, and Bharatiya University as a guest faculty for more than 7 years. Such experienced person has accepted our invitation, came up here to give a talk on a topic on reliability sampling plan. So I request Dr. Shivashankari to share her screen and present her research to the August gathering.
Thank you. Yes, good afternoon, honorable present here. Myself, Shankari, Guest Faculty, Department of Statistics, Bharati University. My topic is Group Acceptance Sampling Plan for Lifetime of Component based on Generalized Exponential Poisson Distribution. And this study includes statistical quality control, particularly reliability testing. Here introducing a new compound distribution generalized exponential Poisson based on a group acceptance sampling plan, and also designing procedure, and the example is also given. So we know that the statistical quality control consists of various statistical techniques. It can be employed to control, improve, and maintain the quality standards or to solve the quality problems. It broadly classified on three categories: process control, product control, and reliability. In process control, quality characteristic of the product inspected at the time of production process. And in product control, the finished products or semi-finished goods can be inspected. And in reliability sampling plan, the quality characteristics basically on a lifetime of the components, products, or items. So without quality control, we cannot assure or ensure any product is better than anything. So mainly the quality control aims to improve the profit of the producers by making the product more acceptable in the market, and always the quality control tries to fulfill the consumers' needs by providing the product a long life, long-lasting life, greater usability, aesthetic aspects, maintainability, etc. And it helps to produce optimum quality at minimum price, and it ensures satisfaction of customers with the products or services of high quality level to build consumers goodwill, confidence, and reputation of the manufacturers. So that's why we are always aiming at to improve the better quality of the products. The quality control plays a bigger role in industries and companies. So in acceptance sampling plans, a specific plan that clearly states that the rules for sampling inspection and its associated criteria towards acceptance or otherwise, rejecting the sampling plan or rejecting the lots. Acceptance sampling is the middle way approach between no inspection and 100% inspection. So it is not always possible with no inspection or 100% inspection for the descriptive items or not. So we are always preferring that most of the pioneers are inspecting the sampling plans based on the acceptance sampling plans. Acceptance sampling plans can be applied for inspection towards the end items, components, raw materials, operations, materials in process, supplies in storage, maintenance operations, data records, and administrative procedures in various government and private concerns towards governances of the manufactured product decisions. So, in particularly among the product process and reliability sampling plans, I have preferred this study based on reliability. Why we need reliability? It's the for the components to find out the long-lasting products. For testing the long-lasting products. Nowadays, most of the complex products are generated by the industries are mechatronic based. Now the trend, the products are based on mechatronic based items that definitely need reliability to find out the product is reliable or not. The reliable sampling plan is a tool to obtain the lifetime of an item, and the items are mainly mechatronic based. Based on the reliability sampling plan, one can reveal that a product is reliable or not. Of course, the reliability plays a vital role and inevitable role in the industries. For example, a television manufacturer company records the lifetime of the components connecting the parallel system in a television. So, and these records may constitute the database for the reliability analysis of the particular brand. So, actually, there are types of reliability testing, and reliability testing refers to the test conducted to verify that a product will work satisfactorily for a given time period or not. So, it is based on functional test, environmental test, and life testing. So, a functional test is nothing but it involves a test to determine if the product will function at a time zone. So, the environmental test consists of determining the expected environmental levels and then carrying carrying the functional test of the environments under which the product has to separate. The life of the component is the time period during which it retains its quality characteristics. So hence the life test aims to measure the time or period during which the product will remain the same or not. So that is the ultimate expectation by using reliability testing for finding out the lifetime of the product. So here I have taken a compound distribution, generalized exponential Poisson distribution. Murphy et al. 2002 indicates that the exponential distribution adequately fits the failure data of a wide variety of systems such as radar, aircraft and spacecraft, electronics and satellite constellations, communication equipment and computer networks. So if these kind of situations, the GEP distribution, generalized exponential Poisson distribution, can be well be suited distribution and it is good for such kind of situation occurs. So why I have taken a compound distribution? Because the exponential and the Poisson is well suited with the real life examples. Real life products while we are producing the mechatronic based items. The exponential distribution is the probability distribution of the time between the Poisson event occurs. Basically the exponential probability distribution is the we can apply only when the time between the failure occurs. The particular failure occurs between the Poisson event. So Poisson distribution is a discrete probability distribution that expresses the probability of a given number of events occurring in a fixed interval of time. The exponential distribution may be appropriate for modeling random failures. Random failures in the sense that it is caused by external shocks such as an unexpected change in load. External shocks usually can be modeled using the Poisson process. So if every shock causes a failure, a product life can be approximated using the exponential distribution. The exponential distribution is widely studied and especially popular in modeling the life of the product. For example, when some electronic components and systems are manufactured. So whenever the electronics and mechatronic based items are produced, we will face the sudden failure or over the long lasting period, we have certain failures. So to finding out and inspecting certain kind of systems or products or items or components, we can apply this lifetime components reliability we can apply. Particularly the GEP distributions can be applicable for these situations. Therefore, the GEP distributions can be used to model the maximum lifetime of random EP samples. Furthermore, the GEP distribution has a desirable physical interpretation. If there are n components in a parallel system, the lifetime of the components are independently and identically GEP distributed, then the whole system will follow the GEP law. So based on this law, I have taken the example that one particular component fail in a certain item, the whole that items are connected in a parallel system, the whole system will fail. So the failure of one component, the time between the failure of one component with the another component will follows the exponential distribution. The occurrence of failure is nothing but the Poisson event. So based on whenever we have taken the mechatronic based items, we can apply the GEP distributions. That is the life to obtain the lifetime of the components. So Kush in 2007 they have introduced exponential Poisson distribution. After that, in 2009, Wagner, Pareto, Sosa, and Francisco Cavarinato introduces the generalized exponential Poisson distribution. It is also known as the exponentiated exponential Poisson distribution. Actually, it's a component distribution of exponential Poisson with 3 parameters, and the failure rate of these distributions can be decreasing or increasing and also upside down bathtub shaped model. The cumulative distribution is this one, the 1 minus e power minus lambda plus lambda exponential of minus beta x divided by 1 minus e power minus lambda, and it is generalized by the parameter alpha. So whenever the Push 2007 introduced the exponential Poisson distribution, without the parameter alpha. So here it is generalized by the parameter alpha. Here alpha is the shape parameter and beta is the scale parameter of exponential distribution, and lambda is the Poisson parameter. So when alpha equal to 1, the generalized exponential Poisson reduces to exponential Poisson. When alpha equal to 1 and lambda tends to 0, the exponential Poisson reduces to exponential distribution with the scale parameter beta. So now we are moving to group acceptance sampling plan. Some flaws and disadvantages obtained in the classic approach single acceptance sampling plan. We cannot take more than n number of items to be inspected simultaneously in a single sampling plan. To overcome these flaws obtained in single acceptance sampling plan, we can go for the group acceptance sampling plan for the to trying to reduce the cost and time. So in this group acceptance sampling plan, we can select the number of groups G and allocate predefined OR items to each group so that the sample size for a lot will be n equal to G R. So G is nothing but number of groups, R is nothing but group size. So G into R can be the sample size of the plan. Select the acceptance number C for a group and specify the experiment time T0. So we can observe the number of failures until the time T0. If the number of failures is greater than C for each group, we can perform the experiment for the G group simultaneously and observe the number of defective failures for each group. If the within the specified time period T0, we can accept the lot only if the C number of failures before that reaching the time T0. We cannot accept the lot only when the maximum number of C failures is more than C failures obtained in the time period T0. So Muhammad Aslam and June introduced in 2009 a group acceptance sampling plan for truncated libraries based on inverse Rayleigh and log-logistic distributions. And Rosaya and Rao developed in 2016 a group acceptance sampling plan based on truncated libraries for type 2 generalized log-logistic distribution. And Srinivas Rao in 2009 studied a group acceptance sampling plan for lifetimes following a generalized exponential distribution. And Wagner Barreto and Kubari Neto in 2009 introduced generalization of exponential Poisson distribution. And Kavievza and Provas 2017 studied for variable Poisson distribution. These are the few reviews here is given. And the group acceptance sampling plan is developed here based on minimum angle method to finding out the number of groups. Actually, the minimum angle method is based on 2 points on the OC curve. Whenever we are considering inspecting the lot, there will be the 2 types of errors can be occur. One is type 1 error, the other one is type 2 error. Type 1 error is nothing but rejecting the good lot, and type 2 error is accepting the bad lot. So based on these 2 errors and the incoming quality P1 and P2, so from this picture we can refer that the P1 is always the good quality, the P2 is nothing but the limiting reliability level, it's a bad one. So here it is, we are assuming that we are always consider the ideal OC curve gives a better plan to reducing the producers and the consumers risk. So rejecting the good lot is a producer risk, accepting the bad lot is nothing but the consumers risk. So we are always here trying to minimizing or reducing the type 1 error and the type 2 error. So we are always trying to taking the OC curve, we are bringing to the ideal OC curve. So at that point, the L of P1, 1 minus alpha and beta to be reduced to finding out the better plan. So based on this concept, the minimum angle method, one can find out the sample size, which gives a better plan to bring the OC curve to the ideal OC curve. So both the risks have to be kept minimum for producing the reliable product. Hence, it is considering the 2 levels, acceptable reliability level and the limiting reliability level, to minimize the risks which are attained through the producer's confidence level, that is nothing but 1 minus alpha, and the consumer's levels beta. So thus the probability of acceptance can be obtained for the incoming inequality using the following inequality. That is, probability of acceptance at the point P1 is should be greater than or equal to 1 minus alpha, because alpha is nothing but the type 1 error. So that should be greater than when it is 1 minus alpha. Then probability of acceptance at P2 level should be less than or equal to beta. So we are here trying to minimize both the risks alpha and beta. At that point, inequality at that point, we are trying to find out the minimum number of groups or minimum sample size. So this is the minimum angle method, which shows that angle between the point bad quality and the good quality. So based on that, we are trying to minimize. We are bringing the OC curve to the ideal OC curve. The theta should be minimum. So whenever the theta is minimum, we can find out the ideal OC curve, which reducing the producers and the consumers risk. So at that point, we can find out the number of groups or number of sample size. So here the group acceptance sampling plan can be exemplified by the three parameters R, G, C and T by beta naught. R is nothing but group size, G is the number of groups, C is the acceptance number, and T by beta naught is nothing but the test termination ratio, which T is nothing but a specified time period till then we can connect the test, and beta naught is nothing but the specified mean lifetime. So the problem is to obtain the minimum group size, which is least for the known p value, p star. That is, we are always keeping that p star is minimum, like 0.01, 0.05, 0.10, something like that. So beta naught and C, based on these three values, for the given these three values, one can find out the minimum positive integer n, which is a R into G, should satisfy the condition that L of P1 that is equal to, this inequality should be less than or equal to 1 minus P star. So P star is nothing but the minimum level at which we can find out the number of groups. So here the probability of acceptance for the given level of P1 and P2, L of P is equal to summation of RG, within that we can find only I number of defectives, P power I, 1 minus P power RG minus I. So for the given level of T by beta naught, different values of percentiles, and that's different values of test termination ratio and the acceptance number C, one can obtain the L of P values. So the minimum angle method, actually the discriminating performance of any sampling plan is generally revealed through its operating characteristic curve. It is developed by the Norman Bush et al. In 1953 to find out the ideal OC curve to be made to pass closely through AQL 1 minus alpha and AQL beta. So the tangent, in the minimum angle method, the tangent of angle is considered between the lines joining the points AQL 1 minus alpha, AQL beta, and the LQL 1 minus alpha, LQL beta. So the AQL is nothing but acceptable quality level, then LQL is nothing but the limiting quality level. So applying this method, one can get a better plan which has an OC curve approaching to the ideal OC curve. So the formula for tan theta, of course, we know opposite side by adjacent side. So tan theta is equal to P2 minus P1. So based on only these two qualities, P2 and P1 divided by the probability of acceptance at the level P1 minus probability of acceptance at the level P2. So here the construction of group acceptance sampling plan using minimum angle method is let the mean ratio D1 is equal to beta by beta naught. The beta is nothing but the actual mean lifetime of the components. Beta naught is nothing but specified mean lifetime. So with the acceptable reliability level. So at D1 we have taken at P1 level. So because of that it is called as acceptable reliability level at the producer's risk, and D2 is nothing but beta by beta naught. So it should not be greater than greater than 1. So that's why we are always keep it as 1 with the limiting reliability level at the consumer's risk. So the parameter N, or it can be G, can be obtained for the given D1 and D2. It is at the level of P1 and P2 when the following inequalities must be satisfied. So based on these two inequalities, one can obtain the minimum number of groups, L of P1 and L of P2. That should be L of P1 should be less than or equal to alpha, in the sense that it should be greater than or equal to 1 minus alpha, and L of P2 less than or equal to beta. So the here the incoming quality at P1 and P2 can be obtained through the function of T by beta naught into 1 by D. The D is nothing but beta by beta naught. So here we have given values for beta by beta naught. It can be 0.5, 0.6, something like that at the level of P1, and at P2 level it can be 1. So through the application of tangent, one can compute the angle theta by using the formula P2 minus P1 divided by L of P1 minus L of P2. So theta is nothing but here tan inverse of tan theta. So by making the by reducing the P2 level and P1 level, we are obtaining this theta level. At this theta, one can obtain the minimum number of groups. So the example for this generalized exponential Poisson distribution, suppose an experimenter wants to find the minimum sample size when the experiment is studied to obtain lifetime of the smartphones. So here each component is assumed to follow the exponential probability distribution, the time taken to failure at Poisson process. Here the components are connected in a parallel system, so as failure of one component will affect the whole system. So hence the lifetime of the smartphones can be assumed to follow generalized exponential Poisson distribution. So here the values are obtained, the theta values are obtained for the given levels of dissemination ratio 0.5, 0.6, 0.7 and 0.8, and also we fix the beta by beta naught level 6, 7 and C values 1, 2, 3, and the number of groups we have from the minimum angle methods at the dissemination ratio level of 0.5 is 4674, and at level of 0.6 is 3563, at the level of 0.7 3453, at the level of 0.8 is 234. So when we are finding value, minimum theta value for this number of groups at 0.5 dissemination ratios nearer to 22. It is 25 if it is dissemination ratio is 0.6. Here 28 we have got the theta value at T by beta naught is 0.7, and theta value is 31 nearer to 30 at the dissemination level is 0.8. So whenever we are the dissemination ratio is getting increased, the theta value is also getting increasing. So we are trying to find out the minimum theta level. It's better to keep the dissemination ratios in the minimum level. So minimum from this table one can obtain that the minimum angle fan is applied when the disseminating at time 800 hours, but the experimenter truly believe that the specific mean lifetime at least 1000 hours. So he wants to prove that the product's actual mean lifetime would be 6000 hours. It is required to know that the minimum angle of the plan is studied under the dissemination ratio is 0.8, and the ratio of actual and specific mean lifetime is 6. So based on this 0.8 and 6 level, at the confidence level is 0.95, one can obtain the group experiment sample plan is G equal to 3 and R equal to 2. And also here I have fixed that R equal to 2. So for we have testing the 3 number of groups each with 2 sample sizes simultaneously, and if you are obtaining 2 number of defectives, we can allow before the time period occur. If we are getting more than 2 defectives, we can reject the lot. So for this plan, the minimum angle is 30.757 with the lot acceptance at the P1 is 0.9920 and the lot acceptance at P2 is 0.1. So here we can see that the lot acceptance for the good quality level is 0.99 and the bad quality level is 0.1. So it's a better plan to be can be implemented for the electronic based items whenever the items is assumed to follow generalized exponential Poisson distribution. So the conclusion is the minimum angle of the OC curve for the proposed plan are provided with suitable illustrations. In accordance with designing of plan, only interested in reducing the risk factors can go with the minimum angle approach. The work can be extended to designing the truncated life test plan for various other sampling plans available in the research studies. Here are the few references given here. Thank you.
Okay, thank you very much, Dr. Sivashankari, for a nice presentation. The forum is open for any clarification or discussion. Yes, someone has raised. Please raise your question.
Good afternoon, sir.
Good afternoon. Good afternoon.
Good afternoon, ma'am. Myself, Nagarajan. I'm a research scholar in Bardhan University under the guidance of Dr. V. Kaviyadas, sir. Ma'am, I have one doubt.
Yes.
Am I audible, ma'am?
Yes, please. Go ahead.
In group acceptance sampling plan, for defining a group, is there any criteria for defining a group size? For example, 100 units contains one group, like that, ma'am.
Actually, based on this minimum annual method, we are trying to find out the groups, number of groups. So based on number of groups, we can fix that the number of sample sizes. Sample sizes in each groups. So there is no any particular concept to fix the group size. Based on after fixing the group size only, we are finding out the number of groups. So that is the criteria. There is no particular criteria to fix the sample size in each group.
Okay, ma'am.
So any more questions? So if there is no question, we thank. I think another person has raised a question.
Yes, sir. I have no doubt, sir.
You tell me, ask me, ask doubt.
Ma'am, I'm Karthik, ma'am, from Baba University, ma'am.
Yes.
I have no doubt, ma'am. In this distribution, 3 parameters, ma'am.
Yes.
Which are the fixed parameters, ma'am?
I think Karthik, your voice is not audible. Can you ask once again?
Ma'am, in this distribution, ma'am, 3 parameters, ma'am.
Yes.
3 parameters, ma'am. Which parameter is fixed parameters, ma'am?
Yes, there are 3 parameters in the GEP distributions, and I have fixed because when alpha equal to 1, the generally exponential Poisson distribution tends to exponential Poisson. So that's why I have keep it as alpha equal to 2. I have fixed the parameter alpha and lambda, because lambda is also Poisson event here. So I have fixed the event and the generalization. So alpha and lambda is fixed here, and I am trying to find out the beta value. Based on the beta is nothing but scale parameter. So based on scale parameter, the group, the number of sample sizes or groups can be obtained. So here the fixed parameters are alpha and lambda.
Okay, ma'am. Thank you, ma'am.
Okay, thank you, Dr. Shivashankari. Next, we call upon the next speaker, Dr. P. Sivakumar. Sivakumar, are you there?
Yes, sir, I'm here.
Please turn on your camera. So now we have the last speaker of the session 31, Dr. P. Sivakumar, faculty in statistics in CMR University. So now he's going to present his research under the topic he opted. So now I request P. Sivakumar to take the session and share for 20 to 25 minutes. Okay.
Yes. Is it visible, sir?
Yes, but visible and audible.
Yes. Thank you so much, sir. First of all, I would like to thank Dr. V. Kavieras, sir, as a research supervisor and mentor. You have given your good support to me, sir. Thank you a lot for that. And I would like to thank Professor C. Satish Kumar, sir, for providing this good opportunity to me to presenting my research title as an invited talk in this great occasion. Thank you so much, both of you. And once again, good evening to honorable present here. So today I'm going to presenting the topic as a selection of Bayesian sampling plan in modern manufacturing process for risk reduction. So I'm going to talk about some methodology, designing methodology for this towards the acceptance sampling plan to controlling the risk reduction. So these all are the outline of my presentation. First is I'm going to talk about some introduction about the basic terms which we are using in acceptance sampling plan. And second chapter is focused on review of literature. I have given some significant review of literature which is related to my research topic. And next is the basic framework of Bayesian single sampling plan under the conditions of zero integrated Poisson distribution. And next forwarded to that topic, the minimum sum of risk method, which is the designing method methodology we are using for the acceptance sampling plan that we are going to discuss about this in this session. And next is we are going to discuss about some numerical illustration for our contribution, and next is finally conclusions. So first is the introduction. So statistical quality control. Earlier, all the professors have given the very good explanation about the statistical quality control. So I'm going to talk about, I'm going to give a very basic introduction, little introduction about the statistical quality control. So in our day-to-day life, we are using more different kind of products and services from the time wake up until to get back to the bed. For example, for different kind of products like a soap, toothpaste, and electronic devices, freezer and fan, like that. So these kind of products, and if you're taking the services, we can say as the water supply, electricity, and healthcare, education. So these kind of services are there. So all of us wish that these kind of products and services should be fulfill our specifications. So when it is fails to get fulfill our requirements or specifications, we can call it as this poor quality products or services. When it is fulfill our specifications, we can say it as this good quality products or services. So all the manufacturers and producers wish to produce their products as a good quality products, then only they can survive in competitive marketing situations. They want to be, if they wish to be a brand in the whole marketing, they want to be producing the good quality products. They want to improve their customer loyalty. Then only they can be a survey in this. Nowadays, there are so many competitive marketing. And the SQC is one of the best statistical technique to controlling and measuring and improving the product quality in the manufacturing industries. So SQC is one of the most important application of statistical technique used in industry, and it is worked based on the probability and mathematical concepts in engineering methods. And it could be a very much helpful statistical technique to controlling all the things during the production and final and finished and semi-finished products. So SQC is broadly categorized as follows: the process control and product control. Process control is nothing when we are doing some modification to monitoring the product's quality during the production, that we can call it as the process control. We are using for example, we can use the control chart. We are using the control chart techniques, and some other techniques are there to control the product quality during the manufacturing process. And next is the product control. Once we done the production, then we want to ensure the products are being a quality or not. That situation, we want to go for the offline quality control technique, that is the product control. So my research topic is only focusing on the product control. So next is the benefits of quality control. We know well there are so many benefits are there for the quality control. First one is the improved the safety. So we can improve the safety of the productions and improve the market position. Definitely, if you want to be a number one position in market, you must be produce the quality products. You must be sales. You have to increase your product sales when it is being the quality. And next is a reduced liability risk. So we should reduce the liability risk by using this quality control. And the customer referrals, definitely if you are providing the good quality products in marketing, you can get a more customer referrals. You can increase your sales and profits. And repeat business, definitely we can get the repeated business from all the different kind of merchandise. And next is the customer loyalty. Definitely we can get the customer loyalty, then it could be helpful to increase our profit. So these all are the basic benefits to getting by using the quality control. So next is the acceptance sampling. What is the acceptance sampling? So before talking about the acceptance sampling, if you have the big production, mass production, how we can ensure whether it is quality or not. That is a big task in nowadays. So acceptance sampling techniques could be helpful to ensure the quality of the big production based on the sampling inspection. So acceptance sampling is a technique in which a small part of the items we are going to select it from the entire mass production randomly. And based on that lot, we are going to select some units, and we are going to make the inspection on that lots, and finally we are going to make the decision whether it is accepted or rejected based on the information provided by the sample inspection. So that is the acceptance sampling. And in acceptance sampling, there are two major classification of types are there. One is the acceptance sampling of attributes, and one more is the acceptance sampling of variables. So in my research is only focusing on acceptance sampling of attributes. I didn't consider about the variable aspect. So this is the designing methodology in sampling plan. There are four different designings are there to doing the acceptance sampling inspection. According to Professor Case and Keats, 1982, categorized the evaluation of sampling methodology of attribute acceptance sampling plan as follows. There are four different methodologies are there. One is the non-Bayesian risk-based sampling plans, and non-Bayesian economic-based sampling plans. Risk-based sampling plans only focusing on to reducing the consumer and producer risk, and economic-based sampling plans only focusing on to reducing the cost of the inspection. So here there are two different methodologies are there. One is the Bayesian and non-Bayesian. My research study is only focusing on the Bayesian sampling plan, to developing the Bayesian sampling plan towards the risk-based. So that is my contribution. So that there are two different approaches are there. One is the unity value approach. One more is a search procedure. In my study, we are going to talk about the unity value approach, based on the unity value approach. So before study about the risk, producer risk and consumer risk, you must know what is the risk in quality. The risk is very simply we can define as when we are facing the lack of quality, or else we can say it as the potential failure. The potential failure towards the specification, we can call it as the risk. So we should reduce the risk during the manufacturing production of as well as the after the production. We should reduce the risk to getting the defective items during the productions, and as well as we should control the risk, and we should improve the quality. That is the ultimate task when we are using the statistical quality control techniques. So this is the decision in quality, risk decision in quality. There are two types of errors out there, probability of type 1 error and probability of type 2 error. As a statistician, you all people are well known about the type 1 error and type 2 error. And as per under the statistical quality control, type 1 error we can call it as producer risk, and type 2 error we can call it as consumer risk. See here, actually here H0 is true, which means the product is in good quality. When you are rejecting the good quality products, that is producer risk. If you are rejecting as a consumer, if you are rejecting the good quality products, it will comes under the producer risk. It's a risk of the producer. And if you are accepting the good quality products, there is no problem. Definitely, it is a right decision. So there is no problem in that. And next is, if you are rejecting the good quality products, that is also the correct decision. There is no issues in that all. But the type 2 error, when we are talking about the type 2 error, that is a consumer risk. That is nothing. If you are accepting the bad quality products, it will be the risk for the consumer. Of course, if you are accepting the bad quality apple, it will lead to getting the more serious health issues. So accepting the bad quality products, that will be comes under the consumer risk. So there are two risk over there. One is the producer risk, one more is the consumer risk. Producer risk we can denote as the alpha, and the consumer risk we can denote as beta. So producer risk and consumer risk. I have given one example to understand about the producer risk alpha and consumer risk beta. Producer risk is 5% for an equivalent of 0.02. So if you want to describe this word, this will give the means batches that are 2% of non-conforming are good, and prepare to reject these no more than 5% of the time. So that is the meaning we are using the producer risk as a 5% when the equivalent is 0.02. And next is the consumer risk. Usually we are used to keep the producer risk as a 5% and consumer risk is 10%. So I have made the example based on the basic quality levels. So next is, if you are considering LQL is 0.08, with the respective, the consumer risk is 10%, which means the batches that are 88% of non-conformings are bad and prepared to accept these only 10% of the time. So that is the meaning we can say it as consumer risk is 10% for an LQL of 0.08. So here I have given the definition for AQL and LQL. AQL is nothing maximum acceptable percentage of defectives defined by the producer. It should be defined by the producer, and the LQL is nothing maximum allowable percentage of defective items defined by the consumer. The LQL is will be defined by the consumer. AQL values will be defined by the producer. So next is the Bayesian acceptance sampling plan. So we know well, usually we are using the traditional sampling plans, that is a single sampling plan, double sampling plan, and the RGS plan like that. But when you are talking about the Bayesian aspect of sampling plans, it could be advanced statistic. I mean, acceptance sampling plan. It could be helpful to getting overall idea about the overall production. That's why we are using the Bayesian acceptance sampling plan. I will explain you how it will be work to you. So first is the Bayesian concept will work based on the prior knowledge about the production. So we must have some prior knowledge about the whole production. Based on that knowledge only, we are going to work with the Bayesian under the Bayesian methodology of sampling plan. We can develop the sampling plan under the Bayesian concept. So the prior knowledges will play the important role in Bayesian sampling plans. And next is why we should have the prior knowledge about the production process. If you have some prior knowledge about the production process, definitely we can have the overall idea about the production process. Based on that knowledge, definitely we can make the decision as it precise. We can attain the good results, a good decision based on our results. So generally, acceptance sampling plans are designed under an assumption that will not error occur in sampling inspection. For example, if I'm doing the single sampling plan for the sampling inspection, I'm going to consider only one lot. I'm going to draw on 50 samples. For example, if I'm going to draw on 50 samples from that lot. Based on that, if I've got 2 defectives in that lot, I'm going to make entire decision based on that 2 defectives. That is a traditional sampling plan. But in Bayesian sampling plan, it will consider the previous all the lots and the forwarding all the lots. It will not take it as only the 2 defectives for entire lots. If you are using the Poisson distribution, definitely it will consider as mean and median is, mean and variance are equal. So it will consider as all the lot is having the 2 defectives in previous and for further lots. So it will we are going to make the decision based on the 2 defectives. But if you are using the Bayesian acceptance sampling plan, it will helpful to measure all the variation in between the lots. That is the advantage of Bayesian acceptance sampling. Maybe we have chance to get 3 defectives in previous lots. There are chances to be getting the 8 defectives in one lot. So there are so many in real-time situation we have chance to getting the more variation in between the lots. So the Bayesian sampling plan will be helpful to getting all the idea about the overall all the lots. So it will consider overall the performance. So it could be helpful to make the precise decision in the industry environment. So that is the advantage of Bayesian acceptance sampling plan. So here I have given some reasons why we need to use the Bayesian acceptance sampling plans. The variation in the lots are categorized into normally within lot variation, between lot variation. I'm already told you, if you are considering only the within lot variation, that is a traditional sampling plan, because we are going to make we are going to draw on the samples from the only one lot, and based on that lot, we are going to make the decision whether it is acceptable or rejectable by using the sampling distribution. But in Bayesian, when you are talking about the Bayesian acceptance sampling plan, it will consider the within lot variation as well as the between lot variation. It will consider the entire whole production, because we have some prior knowledge, so we can work we can consider the 2 kind of variations. That is the advantage of Bayesian acceptance sampling plan. When the between lot variation is more than the within lot variation, the proportion of non-conforming units in the lots will vary continuously. Of course, if you have the between lot variation is more than within lot variation, it will lead to getting the more false results based on the traditional when you are using the traditional sampling plan. So if you have the 2 kind of variation in production process, definitely we have to preferably we can go for the Bayesian acceptance sampling plan. In such case, the decision on the submitted lot should be made with the consideration of the between lot variation, and hence the conventional sampling schemes cannot be employed. Yes, of course, the convenient sampling plan, that is traditional sampling plans, will not employ the consideration of between lot variation, but Bayesian acceptance sampling will be considered the between lot variation. And next is the alternatively Bayesian sampling plans can be applied, which use the knowledge on the process variation in making a decision on the disposition of the lot. So that is the very good advantage for the Bayesian acceptance sampling plan. Definitely, by using Bayesian acceptance sampling plan, we can make the precise results and we can make the decision as a meaningful in the during the production on the products. And next is, I'm going to talk about the zero inflated Poisson model, because we have used zero inflated Poisson model. We have taken some specific situations and we have fitted the distribution for that situations. So you know very well in acceptance sampling, we are very generally we are using the Poisson distribution to make the decision whether it accept or reject. But the zero inflated distribution will be involved when you are having the very good well monitoring production process. Because I will explain the situation when we want to go for the zero inflated Poisson model. Nowadays, every manufacturing industry follows the strict procedure at every stage of production for developing their quality. Of course, nowadays, every manufacturers and producers, they are concentrating on during the production to maintaining the quality. For most manufacturing companies, they are using the technical advancement and computer modeling and simulation to detect product defects and handle them in the initial stage of the production process. So this is a regular procedure the manufacturer, as a manufacturer and producer, they are using during the manufacturing production process. Using such technology can reduce the defective products earlier. Definitely, it could be helpful to reduce the defective products earlier. However, due to random fluctuation, yes, of course, the random fluctuation, there are some unavoidable reasons in the manufacturing process. There are so many reasons are there to lead some defective products during that production. So for example, the unskilled workers, employers, or fatigue procedures and lack of machines, improper machines, due to some reasons, we have chance to getting some defective items in the production process. In this circumstance, one can apply zero inflated Poisson distribution to make an appropriate decision than the traditional Poisson distribution, because you know well, the Poisson, the basic assumption is mean and variance are equal. So that is we are using in traditional sampling plan. But when you are using the zero inflated Poisson distribution, definitely if you have the very good well monitoring production process, we are going to have very few defectives in some specific lots. So we don't want to go for the Poisson distribution. Instead of that, if you are using the zero inflated Poisson distribution, it could be helpful to make the precise results decision in the sampling inspection. Next is this is the model for zip distribution. According to Lampert 1992, the probability mass function of this model as follows. See, when the x value, that is a random variable, x is equal to 0, we want to consider the as a probability function, we want to consider this one, that is omega plus 1 minus omega multiply e power minus lambda. Here omega is the zero inflation parameter. So if you have more number of zeros in your data set, if it is in count data, we want to go for the zero inflated Poisson distribution. Definitely, if you are using normal Poisson distribution, it will get a more problem, more error to making the decision. But if you are using the zero inflated Poisson distribution, the omega parameter omega will take care of the influence of zeros in that data set, and lambda is the Poisson parameter. So it will take care of zero inflation as well as the count data set. So it is a perfect appropriate distribution model for when you are having more number of zeros in the data set. So, and next is the random variable x, when it is having the numbers like 1, 2, 3. So we want to go for this probability function, that is 1 minus omega e power minus lambda, lambda power x divided by x factorial. So in zero inflated Poisson distribution, we have two parameters. One is omega and lambda. Omega is the zero inflation parameter and lambda is the Poisson parameter. So the limit of omega is 0 to 1. So if you have the omega value equal to 0, which means it will tends to normal Poisson distribution. If you have omega value is equal to 0, it will tends to normal Poisson distribution. If you have omega value equal to 1, which means the whole data is having only the 0 value is 0. So entire data we have only the 0 value. So that is the meaning of omega values. So the omega is the zero inflation parameter and lambda is the Poisson parameter. When omega is equal to 0, this model will reduce by the Poisson model. And next is the Bayesian framework of gamma zero inflated Poisson distribution. So in this section, the derivation of zip distribution under the Bayesian approach is adopted for the determination of the OC function. First, we consider the Bayesian approach in a general framework. We should frame the non-conform. We should frame the prior distribution for the each parameters. Here we have two parameters. One is lambda and omega. So first is the gamma prior distribution. We are going to consider as a prior distribution of a gamma distribution for the parameter p, that is the fraction of non-conformities. So the probability density function of gamma prior distribution of p is defined as follows the gamma distribution with the parameters t and s. Here t is the scale parameter and s is the shape parameter. So I have given the probability function for gamma distribution here. And next is the uniform prior distribution that could be followed for the parameter omega, that is a zero inflation parameter, going to follows the uniform prior distribution with the parameters a and b. So here we are going to consider the limitation of the parameters as a is equal to 0 and b is equal to 1. So finally it will tends to the uniform prior distribution, that is with the value 0 and 1. So finally we are going to consider two prior distribution for the two different parameters, that is omega and lambda. And based on these assumptions, we are going to find the derivation of gamma zero inflated Poisson distribution. That is, we have given here according to Holt 1981, we have derived this distribution gamma zero inflated Poisson distribution by using his Holt approach to model. And so finally, this is the final PDF probability, PMF probability mass function. So when x is equal to 0, we want to consider this probability function as a gamma zero inflated Poisson distribution. And next is when the x is having some rounded numbers, we want to consider as this is the probability function under the gamma zip distributions. So next is the review of literature. I have given the significance review of literature for the Bayesian single sampling plan and others related to the work for the Bayesian sampling plans. So here Holt is 1960 and Holt is 1968, Holt is 1968B and 1981. Holt is proposed the Bayesian sampling plans based on the hypergeometrical distribution and gamma Poisson distribution. And next is the very recent paper is the Shivakumar and Kaviya has published the gamma zero inflated Poisson distribution for the single sampling plan, RGS plan, and as well as the skip plot sampling plan type 2. So that could be helpful to understand about the Bayesian sampling framework to making the framework for Bayesian acceptance sampling plan. And next is these all are the significance review of literature for zero inflated Poisson distribution. And next is the single sampling plan. You know very well about the single sampling plan. Is the very basic sampling plan in acceptance sampling. A single sampling plan is nothing which we are going to make the decision based on the single lot, whether it is we are going to make the decision about the acceptance or rejection of a lot based on the only one sample that has been inspected is known as a single sampling plan. So there are three parameters will involve in single sampling plan. One is capital N, that is a lot size, and small n is the sample size, and acceptance number is C. That is we are going to consider as a C. So this is the operating procedure. We all are well known about the operating procedure for single sampling plan. So I'm going to skip it. And I'm going to explain the framework of Bayesian single sampling plan, BSSP. So the OC function of single sampling plan under gamma zero inflated Poisson distribution, I have given the model here, the probability distribution I have given here. And with the help of gamma zero inflated Poisson distribution, I have made the OC function for single sampling plan here. So you know very well the single sampling plan probability function of single sampling plan I have given here based on the gamma zero inflated Poisson distribution. Here P bar is the process average And when C is equal to 0, the lot acceptance probability will become as the given distribution probability function is here. So when the C is equal to 0, we have to consider this probability function. When we are having the C is equal to 1, 2, etc., we should go for the this probability function to finding the single sampling plan values. And next is minimum risk method. Of course, by using this method, we are going to reduce the risk of producer as well as the consumer comparatively other existing models. Actually, the minimum risk of method is as proposed by Govindaraju and Professor Govindaraju and Subramani in 1990. So they have proposed this new designing methodology towards the sampling plans. It could be helpful to reducing the producer risk as well as the consumer risk simultaneously, better than the other existing models like a unity value approach and such procedure. So here, the procedure for selection of the plan. So how to select the sampling plan by using the minimum sum of risk, that I'm going to explain to you. First step is we should compute the operating ratio. We should make the assumption values first of all, that is P1, P2, that is AQL, LQL, and alpha and beta. We should fix the values of P1, P2, and alpha and beta. Based on that, we should find the operating ratio value, that is P2 divided by P1. Next step is the compute the values of P2, P1 with the given values of omega and S, and enter the corresponding table. We have developed some tables for the designing of minimum sum of risk that I will show you later. The next slides, towards the numerical examples, I will show that table to you. So I did this table. By using this table, we can find the sample size by using this procedure that I will explain you with the numerical examples. For example, if you're fixing the equivalent is 0.03%, which means the 0.03, and the LQL is 5%, alpha is 0.05, and beta is 0.10, with the value of omega is equal to 0.05 and S is equal to 5. Here S is the safe parameter, that is a Bayesian parameter, and omega is the zero inflation parameter, that is 0.05. So now we want to obtain the we want to select the sampling plan, that is a N and C. We should select it based on this minimum sum of risk methodology, and at the same time we should reduce the producer risk as well as the consumer risk. That is the ultimate goal for us by using when you are using this methodology. So first we are going to follow the procedure which we have given for the minimum sum of risk methodology. First is we are going to compute the operating ratio that we have computed here, that is a 17 is our operating ratio value. And next is we want to enter the table to finding the corresponding C and R value. C is the acceptance number and R is the rejection number. And at the same time, we can find the alpha and beta value from the, I will show the table. It could be helpful to getting an idea about that. See, this is a developed table based on the operating ratio. At the same time, we are going to consider about the NP1, that is N is the sample size, P1 is the AQL value. So we have find the table by using this procedure. So if you want to select any sampling plan, we should fix the values of AQL, LQL, alpha and beta, and based on that values, by using minimum sum of risk methodology procedure, we can find the optimum sampling plan. So from this table, I could find the alpha value as 1.2% and beta is 9.3% against the desired value of alpha is equal to 0.05 and 0.10. So actual our fixed value of alpha and beta is the total sum of risk. We can take it as 0.15%. But finally, we got it only the 10.5% of risk from this methodology. By using this methodology, we are reduced to more than 3.7% of risk by using this methodology. So that's why we are using the minimum sum of risk methodology to reducing the sampling risk, producer and consumer risk. So here the optimum sampling plan is, say it is going to be a value 3 and the sample size is 250. So if you are taking the 250 samples from the lot with the fixed acceptance number is 3, you can get it the alpha value is 1.2% and beta value is 9.3%. Actually, our desired risk value is alpha is 0.05 and beta is 0.10. But against this, we got it. We maximum reduced more than 3.7% of risk by using this methodology. So at the same time, we are obtained the selection of sampling plans, that is N and C. So final conclusion is, in the required Bayesian sampling plan under the gamma 0 infinity Poisson distribution for the specified quality levels, we can obtain the N value as 250 and C is 3. So if you are going through these values of sampling inspection, definitely we can reduce the producer and consumer risk against the desired value of alpha and beta. So this is one more method to finding the alpha and beta values. Here, selection of the plan for fixed sample size. Once you fix the sample size, how to find the alpha and beta value by using this methodology. That is the procedure I have given here. Table, I have developed so many tables for the minimum sum of risk method, and we are going to finding the sample. We are going to finding the risk values by using the fixed sample size. Here, I have fixed N is equal to 100 and P1 is 0.5 and P2 is 7%. And S is 5 and omega is 0.01. Here S, we can take it as a fixed value, or else we can find the we can estimate the value of S and omega by using if you have the past data, definitely we can estimate the value of S and omega, or else we can, based on our assumption, based on our prior knowledge, based on our own knowledge as an engineer, as a quality engineer, we can fix the value of S and omega. So based on these all the fixed values, we could find the value of NP1 is 0.50 and P2 by P1 is 20. And based on this, definitely we can find the alpha and beta. That is alpha here 2%, beta is 5.5%. So here also we are getting very low low quantity of risk, sum of risk we are getting by using this methodology. So finally, these are the tables for minimum sum of risk. And these all are the reference to getting idea about the minimum sum of risk. The most important paper is the Govindaraju and Subramani. Professor Govindaraju and Subramani has proposed the minimum sum of risk in 1990. So that is a basic paper for this research work. So thank you. Thank you, sir.
Thank you very much, Dr. Shivakumar, for your nice presentation on zip distribution. So the forum is open for any questions or queries or clarifications. Any one or two can be raised now. So if there is no queries, let me thank the speaker, Dr. P. Shivakumar, and all other speakers who shared their valuable time with us. I think there is one comment come from somebody. A nice presentation explanation. Okay, thanks to all the participants for their patient listening. On behalf of the organizing committee and my personal behalf, I'd like to thank all the contributory papers presented here. And also I thank Professor Satish Kumar sir for their wonderful opportunity for the young researchers. Thank you very much, sir. Thank you.
Thank you, Professor for organizing a session on in this way and chairing the session also, and managing the timing, everything did in a very excellent way. Also, all the speakers are also very have given excellent talks. In fact, we are very much grateful to you, Professor, for your
Thank you, sir. Thank you so much, Professor Satish Kumar, sir, to providing this wonderful opportunity to me. Thank you, sir. Thank you so much. And I would like to thank Dr. V. Kaviyarasu, sir, for your continuous support to me. Thank you, sir. Thank you so much.
Thank you, sir.
Thank you so much. Once again, thank you, closers. All the closers in the group.
Thank you.
Organized involvement.
Yes, sir. Yes. So you are the inspiration for all of us, sir. You are the inspiration for all of us. How to organizing a session, not only the conference for the entire 4-day, yearly twice. We're really very happy and to participate in this conference, specifically in online. For many researchers are really getting benefited through your. Thank you very much.
Support and engagement. Thanks a lot. We'll move to the next session. Once again, thanking you all. Thank you.
Thank you, sir. Thank you.
Let us move to the next session. Again, please introduce the chair and for the further.
Yes, sir.
Hello everyone. Now we have the technical session 32 of ICSTC 2022, which is an invited session chaired by Dr. K.S. Banu. Dr. K.S. Banu is a former professor and head of the Department of Statistics of Institute of Science, Nagpur. He has a vast teaching experience of over 37 years. Her research areas include reliability theory and probability theory. He has published more than 60 papers in international and national journals and has also proposed a lot of problems. Dr. Banu has worked as a referee for various journals like Journal of Indian Statistical Association, BMMS, etc. She was a chairperson of Board of Studies and a member of Academic Council, RTM Nagpur University. She has held the post of Integrated Curriculum Director of Institute of Science, besides being the academic head and coordinator of National Assessment and Accreditation Council. We are indeed fortunate to have such an eminent person with us sharing the session today. So with great pleasure and honor, I invite you, Dr. Banu ma'am, for sharing the session today. Over to you, ma'am.
Thank you very much. I'm very happy to be here. Good afternoon, everyone. At the outset, I would like to greet Dr. Satish Kumar and thank him for inviting me to chair this session. Thank you very much, sir. It's a pleasure meeting you again. This session has got two speakers, Dr. Sarojama and Dr. Rohtash Bharadwaj. So I think we have got 1 hour, approximately 1 hour for this session. So the first speaker, Dr. Sarojama, are you there, ma'am?
Yes, madam.
Okay.
This is audible, madam?
Yeah, invite you to deliver your lecture on an empirical analysis of Indian banks' spatial efficiency based on performance and production approaches. I take this opportunity to introduce Dr. Sarojama to all of you, sir. Dr. Sarojama has obtained her MSc with the first rank and distinction in the year 2000 from Venkateshwara University, Tirupati, India. Later, she received PhD degree on data envelopment analysis from SV University in 2006. She was appointed as assistant professor in the Department of Statistics, SV University, in 2007. She has taught various subjects, various topics like time series and forecasting, operations research, advanced operations research, distribution theory, design of experiments, multivariate analysis, statistical computing, biostatistics, etc. She worked as head She worked as head of the Department of Statistics and is presently working as head and chairperson BOS in statistics. She was elevated as associate professor in the year 2019. 8 students have been awarded PhD under her guidance. 2 have submitted and 8 are working. 8 are still working under her guidance. She has delivered lectures in national and international conferences as a resource person. She has also delivered lectures in Sri Venkateswara Institute of Medical Sciences, Tirupati. She is a life member of many professional bodies. She is a Board of Studies member in various colleges and universities. She has published around 99 research papers in internationally reputed journals and presented her work in more than 130 papers. She has presented more than 130 papers in national and international conferences. With such a beautiful academic background, we are lucky, and it's a good opportunity for all the participants to listen to Dr. Sorajama. I invite you, madam, to present your work.
Thank you, madam. Thank you for introducing me, Banu Madam Garu.
Yeah, thank you.
Now, I am going to my research paper. This is an empirical analysis of Indian bank special efficiency is based on performance and production approach. The brief review about our program data is we have taken 17 years of data and 3 types of banks. They are public sector banks, private sector banks, and foreign sector banks. Among these 3 banks, 12 are from public sector, and private sector banks we are taken is 17, and foreign sector banks is 23. And 6 models are performed in this paper. They are 4 are for banking performing efficiency and 2 are for banking production efficiency. These 6 models are data development analysis, intermediate efficiency, and fund conversion efficiency, and deposit mobilization efficiency, and production approach efficiency, cost efficiency, revenue management efficiency, and off-balance sheet active efficiency models are we are performed in this paper. Here, as compared with public sector banks, private sector banks are going very highly efficient. Why? Because they are giving loans for farmers or anything by basing on their properties only. Whereas public sector banks are using some limitations for the loans purpose, and they are not retained and they will be sold out. And due to COVID in the year 19, 20 and 21, there will be an high depreciation in loans and credits becoming from farmers and all this. And why? Because they don't have the enough amount and the income for payment of loans, and for that purpose, public sector banks are affected. And session 1 is introduction. Indian banks plays a vital role in sustaining the economic stability of the India, and banks provide financial services including personal savings, loans, payments, and all these. And in this paper, a bridge is to take gaps, and to fulfill that, we are taken 2005 to 2021 data using traditional DEA and window-based DEA. Traditional DEA, all we know that, but what is a window-based DEA mean?
Madam,
A window-based DEA is a moving average model DEA method. Madam?
Your paper is not very visible to me. I do not
Madam,
know about
tell
the
me,
others.
madam.
Your paper is not very clear to me,
Madam.
but I do not know about the others. Is it visible to everyone?
Madam, in presentation it is visible. I don't have PPT, madam, because my system is logging off my PPT, madam. That's why I am presenting the full paper, madam.
Okay.
In Word
Please increase the percentage. That is 105%. No,
sir.
now you increase to 120.
Okay, sir. I will increase, sir.
Left hand side, right hand side corner.
Okay, sir.
Right hand side corner. In Word file.
One second.
You present again.
Yes, sir. I am presenting. Is it visible now, sir?
No.
No, you have to present it. Okay. Yes.
Sir, already presented, sir. Is it visible, sir?
Yeah. This is better.
This is slightly better.
Okay, sir. Okay, sir. Thank you.
Go down.
And we are converted the variables into inputs, outputs, efficiency scores are calculated by using these formulas, where capital is calculated with capital plus reserves and supplies, and total business is addition of advances and deposits, and interest income and non-interest income is equal to the total income. Like that, we have calculated 11 input and output variables. And in literature review, we have so many DEA models, that is data envelopment models, in calculating the relative efficiency based on the decision-making unit. And several papers have been published on the technical and cost efficiency of Indian banking in the Indian context using DEA. Das et al. Evaluated the efficiency of Indian banking from 1997 to 2007 regarding cost, revenue, and profit. During this period, the results and input-output oriented and cost efficiency measures were similar, but the results of the review and profit efficiency measures differed greatly. And Das and Gersh in 2009 have given importance of inefficiency on the revenue side of banking activity is reflected by high levels of efficiency in costs and low levels of profits. In addition, the decomposition of profit efficiency indicates that a significant portion of outlay is due to allocation inefficiency. In their study of Indian banks and DEA during the past reform period, Roy and Doss in year 2010 found that public sector banks are more efficient than private sector banks in terms of cost and profit efficiency, and small banks operate below the efficiency frontier. According to Ober and Sanjeev Bansal, the post the post-reform era, Indian public, private, and foreign sector banks perform similarly based on the efficiency of production, intermediation, and value addition based on input-output specification by banks based on overall pure and scale technical efficiency compared to the CRS, that is, constant return to scale and variable to return to scale assumptions. And other sector DEA efficiency and analysis view. N.K. Wall et al. 2001 attempted to measure the performance efficiency of railway systems alongside bootstrapping DEA analysis and concluded that models should be analyzed and evaluated in terms of their relative operational performance efficiency in order to provide valuable information for the decision making of an organization. An analysis and a comparison of the efficiency scores of public and private sector banks in Turkey was conducted by Kishan et al. Using the DEA BCC model and the weighted input and output DEA model. And in conclusion, they said that weighted models can be used to predict airport operational efficiency due to the more accurate information available to airport operations and airport authority management. Dual and network multi-stage DEA recent views. In recent views, there are so many DEA models where arise. Singh and Cow has given several inefficiencies in the bank as well as efficient ones were identified by comparing public banks with private banks such as State Bank of India, Canara, United Banks of India, and State Bank of Hyderabad and the Central Bank of India. And an interval-based models on the lower and upper bounds efficiency for each DMU is calculated by Puri and Yadav in the year 2017. And multi-stage DEA model was given by Paranta et al. In 2018. They have given about a multidimensional three-stage approach was developed and they measured the efficiency of the performance of the Italian regional banks as a part of step 1. The efficiency of bank branch is calculated using the ratio method. As part of step 2, polarity analysis is used to reduce unnecessary information, and step 3 includes the clustering is used to categorize the bank branch into efficiency classes. A multidimensional approach appears to be more efficient than an individual approach. A DEA is extended to measure relative efficiency and benchmarking. It may be sensitive to stochastic variations since it does not include such variations clearly. Various research efforts has been undertaken to incorporate these variations into the DEA model. These effects are categorized into two distinct approaches. Bootstrapping in DEA provides the empirical distribution of a DEA efficiency estimator. And the basic models in DEA are CCR and BCC. They are Chan, Cooper, and Rhodes, and Banker, Chance, and Cooper models. They are established in 1978 and 1984. It having the most basic models in DEA, data envelopment analysis. And after that, they are contrast to output-oriented model, which seeks to maximize output while minimizing inputs, and input model seeks to maximize output while maintaining constant inputs. A response to the fact that banks are not always be able to control the level of service that their customers require. The decision-making process would be influenced by 3 parties of members of employees of a bank were reduced as opposite then increasing the number of loans. Traditional and advanced DEA model is window-based bootstrap. DEA can be applied to evaluate banking efficiency in various dimensions based on specific factors. Organizational units are measured using these models for the performance efficiency of decision-making units, which are similarly categorized into similar organizational units. In order to select DMUs for a study, two factors must be considered. DMUs must be homogeneous units performing identical functions with similar objectives, and the number of DMUs should be equal in inputs and outputs. A benchmark programming formulation used in the DEA process. Here, in this paper, we are used bank performing efficiency models. They are deposit mobilization efficiency. In this model, inputs used are fixed assets, employee cost, interest expenses on deposits, and outputs is deposits. Whereas fund converging efficiency having inputs, fixed assets, employee cost, and loanable fund, and outputs we are coming is earning assets. And next efficiency model is off balance sheet activities efficiency. Here we are using only two inputs. They are fixed assets and employee cost, and output we get is total non-interest income. And fourth model for bank performing efficiency is cost revenue management efficiency. Inputs here is total interest expense, total and non-total interest expense. Here we producing two outputs. They are net total income and profit after tax, PAT. And production based approach efficiency models are intermediation approach efficiency and production approach efficiency. In this intermediation approach efficiency, inputs are loanable funds and operating expenses, and the outputs are earning assets and total income and profit after tax assets. And second model is production approach efficiency. Inputs are fixed assets, employee cost, and outputs we are getting is deposits and earning assets. These are the six models we are using. And model one we have is according to BCC output oriented model. The mathematical representation of DEA is based on the traditional method is here, which is DEAP is equal to maximize beta pay. And here the inputs are fixed assets of the bank in the year 2005, 2000 up to 2021, that is 17 years. And the X2 is total employee cost of the bank in the year, and the X3 is interest expenses on deposits of the bank in the year. And the output we get is Y1 is deposits of the bank in the year 2005 to 2021. And here is the eta P is the efficiency scores, and this efficiency scores is always from 0 to 1 only. If you have high efficient, then it becomes 1. If it is low efficient, it may ranges from 0.5 to 0.5 to 0.8 and all. And if it is very less efficient, it may come close to the 0. And lambda J's are DM suits, each bank among ownerships. Using the above formulation of each year, we are estimated the efficiency of each bank using the benchmark by using R programming. Next method we are using is DEA window definitions. In a similar fashion, year's data was converted to a window with moving averages, and relative efficiencies were calculated by bootstrapping a BCC output-oriented model and non-parametric Sterco tests were performed to determine the normality. In this situation, for each and every year, we are adding the next year, and finally we will add the new years up to this. For year 1, it is from 2005 to 18. For year 2, it is 2006 to 19, and so on up to. For year 4, it is 2008 to 2021. And window model is defined as follows. It is similar to the above model, but for each and every 14 windows, we are giving the equations. And this is a mathematical representation of bootstrap BCC DEA model. Here, in this situation, we have weighted inputs and weighted outputs. X1, W1 is the fixed assets of the bank in window 1, and X2, W1 is the total employee cost of the bank in the window 1, and X3, W1 is the interest expenses on deposits of the bank in window 1, and output Y1, W1 is the deposits of the bank in window 1. And as usual, lambda j's are decision-making units. Next session is BCC DEA program execution using R programming. Here, charts are prepared using the Excel sheet, and we are analyzed the total paper using R programming. And the final conclusion of the paper is, in this paper, what we performed based on the traditional DEA and window-based DEA, assessed the comprehensive efficiency analysis of the Indian banking sector in 2005 up to 2021 using a comprehensive and detailed relative efficiency analysis. This study compares the existing literature with some studies. In this study, the difference in efficiency of the banks are analyzed by constructing frontiers based on ownership. Firstly, descriptive statistics of the performance and production efficiency was presented year-wise and window-based using 6 different models: DME, FCE, OBAE, CRME, PAE, and IAE. The part of analysis of public sector banks, private sector banks, and foreign sector banks, all 6 efficiency types are examined, and public sector banks dispersion between 2 groups is very low in both types of methods, reflecting that the government has one ownership and is unified in its policy and practice. Even though the overall average efficiency of public sector banks has been high, the rationalization for the cost of employees and branch business has been reviewed based on the population size, government support for agriculture loans, and resources for relief crops. Private and foreign sector banks, on the other hand, have similar functionality, but the primary focus is on employee performance, institutional support loans, corporate fund mobilization, and corporate interlinkage banking. Major industry-specific bank business support, iterative validation with regulations, expansions of branches business into rural and semi-urban landscapes, and forex transactions. Thus, the year-wise and window-based and semi-urban landscape and forex transactions, window-based DE efficiency was shown in the table. Thus, we have a small number of PSBs and PVTs and foreign sector banks must improve their output efficiency using the inputs provided. These are the tables we are listed out for the descriptive statistics of public sector banks, private sector banks, and foreign sector banks using all these 6 models. And the efficiency scores of the banks looks like this. Here, dark green appears the most efficient bank for the model, whereas dark red appears the less efficiency for the model. Here, we are taken the bank names and the 6 models and their average efficiency. And among all the banks using these 6 models, State Bank of India is performing well as compared with all other banks in India. Whereas the EF performance and production cost approaches efficiency for private sector banks is, in private sector banks, ICICI Bank gives high efficient among these private sector banks. In foreign sector banks, high efficient bank is Pragthai Bank Public Company Limited has given the high efficiency of value of 0.8034. And these are the different efficiency measures for different performing efficiencies for public and private sector banks. And their graphs for performance is also see here. These are some of the review of literature we are collected for this paper. Thank you for giving the opportunity. Thank you, madam.
Just a minute, sir. Thank you, ma'am. I was just on the phone with Satish Kumar.
Thank you, Satish Kumar sir and all for giving the opportunity.
And thank you, madam, for your exhaustive presentation. Are there any questions for madam from the participants? If there are any questions from the audience, from the participants. Madam, you have used different models on different banks also.
Yes, sir. Yes, madam.
Yeah, so can you name the top 3 banks in terms of efficiency which you found out?
Madam, in public sector banks, State Bank of India is top 1 bank, madam.
Okay.
Whereas in private sector banks, ICICI Bank
is
the first bank for private sector banks, whereas for foreign sector banks, the most efficient bank is Pragthai Bank Public Company Limited.
Okay. So it's an interesting study with real life data.
Actually, my student is in RBI, madam.
Okay, so you could manage
the data, and I given only suggestions for DEA improvement, madam.
Okay, you have given suggestions. Yeah, that's good.
Yes.
Yeah. Okay, I congratulate you, and on behalf of the organizing committee and on my personal behalf, thank you for this exhaustive presentation. It was a new thing to all of us. Thank you.
Thank you.
Now I invite.
Thank you, Satish Kumar, sir.
invite Dr. Bharadwaj. He is the next speaker. Dr. Bharadwaj is here.
Yes, good evening, ma'am.
Good evening, sir. I invite you on behalf of the organizing committee to present your work. Let me just introduce you to the participants. Dr. Rohtaj Bharadwaj is presently working as Assistant Professor in the Department of Statistics at Punjabi University, Patiala. Prior to joining this university, he served at the Delhi College of Engineering, Gurgaon as a faculty. He received his bachelor's degree in electronics and then did his master's and MPhil degree in statistics. He has earned a doctorate degree in statistics from MD University in the year 2007. He has been engaged in various research assignments and consultancies. He has supervised students for their doctoral research work. He has worked as principal investigator on major research projects funded by the Government of India. Many of his papers have been published in the research journals of national and international repute. He is actively associated with known national and international academic bodies and researchers working in different areas of statistics. His expertise includes stochastic models, reliability theory, failure impact analysis, and high-dimensional data analysis. Dr. Bharadwaj's current research interest includes computing systems, specifically cloud-based systems working in virtual environment. And he'll be speaking today on the performance of a computing system working in the virtual environment. I invite you, sir, to present your work. We'll be getting around 25 minutes with maybe a 5 minute for winding up and question answer session. I think we are a bit behind schedule, but 5:25, I think you can start.
Okay, thank you, ma'am. Thank you so much for your kind words. Am I audible to all of you?
Yes.
Yeah, I'm very thankful to Professor Satish Kumar and his team for inviting me and giving me an opportunity to deliver my talk on the topic performance analysis of a computing system working in virtual environment. Okay, the screen is visible, ma'am?
Yes, it's visible.
Okay, thank you. So the title of today's talk is on performance of a computing system working in the virtual environment. So this is the basic outline of the today's talk.
Not very clear, sir. I think the slides are not very clear, at least at my end. I do not know about the others.
Yeah, yes. Anybody else, please respond. Is it clear to all of you? Yes. Is it visible?
Yes, sir, it's visible.
Okay, thank you. Thank you. There might be some connectivity issue, ma'am. Please check.
Yeah, maybe at my end.
Yes, okay. In these days, we use virtualization. Virtualization technology is gaining, the popularity in these days. Virtualization, actually, what is the meaning of virtualization? Actually, with the help of some software tools, the hardwares are simulated. Their functionality is simulated. So in case of virtualization, virtualization means we are, creating virtual instead of the actual of something. So the functionality of some hardware machine is simulated with the help of some available software, so that without actually using the hardware machine, we can make use of a single machine to utilize the functionality of diverse different hardware machines. So this is the basic concept behind the virtualization. So to create the virtual environment, various types of the softwares are used. And for creating virtualization, the basic software is the virtual machine monitor. That is the name of the software that is generally used to create virtualization. And with the help of this machine, virtual machine monitor, virtual machines are generated in a single machine, so that the hardware functionality can be utilized. So it basically requires 2-3 important things. First is the host machine, It is the physical hardware upon which the virtualization take place. Second is the virtual machine that are used to replace the functionality of physical machines. And another is the hypervisor that I told you is the software that is used to create virtual machines. So this is the basic architecture of the system that is used for the virtualization. Here you can see we have the hardware, the memory arrangement, and in the hardware there is coupled with the software termed here as the VMM, virtual machine monitor. And with the help of this virtual machine monitor, we create the virtual machines. The virtual machines, they have either the similar functionality or they may have the different functionalities. They may run on the same operating system or maybe on the different operating systems, and then they create applications, and the end users use these applications through this environment. So, the virtualization relies on software. Every software has a tendency to fail or cause a system failure after running for a longer period of time. Here it is, I would like to share with you that the failure in case of hardware as well as the failure occurs in case of software, they are of different natures. Software failures, if I say the software fails because of the aging effect, then we cannot justify the aging as far as the software is compared with the hardware. But certain factors come into play, like the memory leakage, storage space fragmentation, crash, hang failure, data corruption, etc. These are some of the causes due to which we can say if these factors occurs, then we say the software ages and the aging effect arise. So the aging cannot be prevented because the memory leakage is the problem. We observe that while the programmer, they prepare some program for developing certain softwares, then the codes they left behind in the heap, they develop while constructing the software, and they if they remains there, then there is the problem of memory leaking. Memory leaking means we are not able to utilize the memory space efficiently. The same is the storage space fragmentation problem. In the storage space fragmentation problem, when we allocate certain storage space to certain application, then if the storage space is divided, the vertical blocks, then the amount of memory space required to run a particular application, we use that application, and if certain memory space remains, then that remains unutilized. So that causes certain problems, and we are not able to use efficiently the storage space available for such programs. So this problem is caused due to storage space fragmentation. Similarly, the crash and the hang failure, data corruptions are some other reasons due to which we can say the software age and the aging come into play. So we are not able to prevent the aging effects at all completely. It is not possible. But we can utilize, you can, understand the failure patterns. We can understand these uncertainty. We can develop the probabilistic models for these uncertainties prevailing in the virtual environment so that we can mitigate the effects due to these failures. So the software rejuvenation is one of the techniques that deal with software aging. After some, after prolonged use, if we feel such type of problems as I described here, the memory leakage or storage space fragmentation types of problem occurs, then we can rejuvenate the software so that the software that we used initially at the starting point and now at this point after passing of certain time, we can enjoy the software as a new. So it occasionally stops running the software, clean its internal state, and restart it. These are the stages in the software rejuvenation. So this is generally used to increase the aging time of a system. The time taken by the system for aging, we can increase that time. So it will take longer time for the system to age. So that is definitely beneficial to the system. So it is proved cost effective and time effective method to delay the failure of a system. Now there are some related studies. These are some of the related studies. Many researchers in the past, they focused on the concept of virtualization. Among these, some are cited here, like Khajehi in 2014. They discussed the importance of virtualization in cloud computing and different techniques through which it can be achieved. Sukur in 2020 discussed the role of virtualization and its significant impact on enhancing network performance to satisfy the requirements of the customer. Some causes of aging and its impact on the system had been studied in the literature. Like Machida et al. In 2012, they investigated bugs related to the softwares, the resources type of affected by aging, and time to fix the issues in cloud computing. Then in 2014, Mohan and Reddy, they established aging trend in server virtualization system that suffers from performance degradation due to resource shrinking. Abdullah in 2017 explored the concept of software aging and discussed various maintenance techniques to counteract the aging effect. To deal with the software aging, different strategies had been discussed in the past studies. Some studies are highlighted here, like Hang et al. In 1995. They proposed a technique to counteract the aging effect in software system, that is the rejuvenation. Trivedi et al. In 2000 discussed stochastic modeling approach to evaluate the effectiveness of proactive fault management in software systems and to determine the optimal time for rejuvenation. Umesh in 2017 proposed a rejuvenation model that enhanced the availability and performance of the cloud computing system, as well as application software that runs on a virtual environment. Arjo et al. In 2021 proposed a methodology to deal with software aging and different types of issues that encountered in the virtual system. Also, different types of redundant systems are extensively studied in the literature. When we go through the reliability literature, we find different types of redundant systems are proposed by different authors. Bhardwaj et al. In 2017, they proposed a redundant cold standby system in which standby is subjected to the failure after specified amount of time. Roy and Gupta in 2020, they studied coherent system with the 2-unit cold standby system to optimize the reliability of the system. J et al. In 2021 obtained a reliability index for a cold standby repairable system using supplementary variable technique. So these are some of the references or the related studies that highlighted the redundant system. So now we here develop the stochastic model. In this particular proposed model, the system consists of 2 hosts. One is operating, and that is in the active state, and the other host is backup host, which is in passive state or cold standby state. No doubt, if we keep some unit or some host in the cold standby mode, then the question of the finance arise here, but we cannot compromise with the reliability of the system. Therefore, there are so many systems that require high reliability. Therefore, despite of this fact that it cause increase in the cost, we have to keep some host in the standby mode. Single server or the repairman or maintenance engineer is there in the system that cannot fail while performing the task. All the virtual machine monitor, rejuvenations and repairs are taken as perfect. It means if we perform any rejuvenation activity or if we perform any repair, then the unit on which the rejuvenation is performed or repair is performed, that acts as new as it was initially. There is a perfect network connection between both the host. It is must that the connection between both the host must be perfect. So instant migration is considered when we migrate. Actually, the migration of virtual machine is required as and when our virtual machine monitor control the operation and it needs rejuvenation, then we have to migrate the virtual machines from one host to the another host. And we considered here that this kind of migration is instant. Failure of the shared memory is considered only at the initial operating state. All the random variables are statistically independent and follow general distributions here. For a particular case, we assumed only the exponential distribution just to show the applications of the study. These are some of the notations that are used to develop the model and solve the problem. These are different probability density function or cumulative distributions functions of the different random variables that are encountered in the study. So here we observed that in the virtualization system, certain random failures might occur while migration or when the virtual machine monitor goes into failure probable zone. Similarly, the failures of shared memory and direct failure of the VMM are random. These are random failures. In other words, we can say that system works in random environment. Therefore, to understand the operating cycle of such a system, it is the need of R to develop a conceptual model under the probabilistic rules. Actually, the stochastic processes provide us an efficient tool with the help of which we can model uncertainty prevail in the systems. So that's why we used here the semi-Markov process and regenerative point technique to develop the probabilistic model of a computing system working in the uncertain virtualized environment. This is the conceptual model of the system. These are different states, actually, possible states. Started from state A. Here we have the two hosts, one active, another in the standby. So here we have different possibilities. The shared memory can fail. If it fails, then state E occurs. From here, it can get repaired. From A, the aging of the VMM can be there. If VMM is, then we are at state B. At state B, because we know the aging effect is there, so there are two possibilities. Either the VMM fail. If it fails, then we are at state D. Another is, we know this is the failure probable zone, so we have to migrate the VMMs. We have to migrate the virtual machines to the standby host. And after that, we complete the rejuvenation. So the completion of rejuvenation, then we back to the state A. From state D, where the VMM failures occurs, if it VMM failure, then we are at state here. And from VMM failure, it's required repair, and repair is done. Then after repair, we again rejuvenate the virtual machine monitor, and we are at state C again. And from here, again, if the rejuvenation completes, then we move to the state S. So this is the conceptual model of the system that we considered here in this study. These are the different states that are mentioned here in the conceptual diagram also. So these are 4 states that are mentioned here. These are the H1A, 1, 2P. These represent actually the host in active and passive state, and shared memory. VMM reg represent the virtual machine monitor under the rejuvenation and shared memory. And likewise, SHMF, this shows that the shared memory is failed. So these are some of the notations and different states. So this is the state transition diagram, actual diagram. So keeping in view the conceptual model, we develop this model using the semi-Markov process and regenerative points, and different, the regeneration points are identified here. These are denoted by the dots, dark dots in the diagram. So here you see this S naught represent the initial state, and we move from here to either to S1. If S1, then
slides are not moving.
Excuse me?
Dr. Darge, the slides are not moving. Is it the right correct slide you are talking? Yeah.
Yes, slides are not moving.
Now it is moving.
Earlier it was, whether it is the problem here, I don't know.
That is what I was wondering, whether it's problem at my end. That's why I put a message. But somebody said yes, they are visible. So
sorry, I'm not getting. Slides are not moving, sir.
Now they are
not moving earlier, just before.
Yeah, but I thought it was a problem at my end only.
Now I'm showing actually the state transition diagram.
Yes,
Is it
yes,
visible?
Yeah, it's visible.
Okay. Now I'm showing the conceptual model diagram. Is it visible?
Oh yes, yes, it's visible.
Okay, okay. So should I proceed now?
Yes, yes.
Okay, thank you. So this is the state transition diagram I was describing about. And here S0 represent the initial state, and using different possibilities that are described here in the conceptual models, we transit from one state to another state with some elapsed time following different probability distributions denoted by these notations. So after that, we try to solve this problem using the probabilistic laws. So we first find out the transition probabilities, and equation 1 represent, these are the transition probabilities that are calculated from this state transition diagram. After that, the mean Saunders times, the general expressions are drawn for the mean Saunders times. And then the system performance measures are discussed here. First is the mean time to system failure. So here the expressions for the CDF of passes time from regenerative state I to failed state are considered, and the expressions are derived here. And then using the concept of Laplace transformation just to solve the equations, we obtained the result in the form of MTSF in steady state. When t approaches to infinity, we get this one. The values of N21 and D21, these are given here. After that, the expressions for steady state availability are obtained. So here actually AIT represent the probability that the system is in up state at instant t, given that the system entered regenerative state at time t is 0. So we obtain these recursive relations, and again using the concept of Laplace transformation, we solve these problems and we obtain the expressions for the steady state availability. So the expression is given here, the values of N22 and D22, these are given here. And further, the expected number of repairs of the virtual machine monitors are obtained, where NIT represents the expected number of repairs of VMM in 0 to t interval, such that the system entered the regenerative state at initial state. So the recursive relations are here, and using the Laplace-Curtis transform, we obtain the expressions. And it is given by N0 in steady state, that is equal to N23 divided by D22. D22 already defined, and N23 is P0 to T. Actually, all these expressions are defined in terms of the transition probabilities and mean Saunders times. So these are the key constituents of this modeling. So now the expected number of repairs of shared memories are calculated. These are the expressions. Similarly, the expected number of rejuvenations of VMM, they are calculated, and the result is given in the form of C0, that is N25 divided by D22. D22 is already defined as previously, and N25 is P01 plus P02 transition probabilities. So finally, the profit incurred to the system model is also tried to calculate it here with the help of considering different costs. This represents the revenue per unit of times, and these are the different costs incurred for some remedial activities of the system, rejuvenations or repairs. After that, just to show the importance of the model, we here consider the exponential distribution. Though we cannot justify here, the frequent use of exponential in case of software failures, but just to show the graphical trend for some set of data, we use this distribution here. So we obtain the transition probabilities and all these performance indices. These are the expressions for the performance index. And finally, the numerical results. These are stated in the form of graphs. So these are some of the observations. This is actually the graph, the mean time to system failure with respect to the failure rate, different parameters. This line shows the reference lines, and these two lines are compared with the reference lines. The green line, this shows the value of A. This is the value of A, that is the migration rate. So as the migration rate of this blue line, this A is 0.1 and the migration rate for this is 0.4. So as quickly we migrate the VM for the resolution, we see the mean time to system failure increases and thereby the reliability of the system. Another parameter shown here is gamma. Another parameter is gamma here, that is failure rate of the shared memory. So this shows, so as the failure rate increases, we show there is declining trend of the mean time to system failure. We have less mean time to system failure, so declining reliability. These are the trends for the availability. So different trends are of the availability are here. How sensitive this index is for different values of different parameters. These are shown here. Again, this line, actually these some are superimposed line, not clearly. Yes. This line shows here the trend line, the basic line or the reference line. After that, we use different values of different parameters. We change A, then gamma, then delta and beta. Here the delta, the repair rate, and gamma, the failure rate of shared memory, and lambda, the failure rate of VMM, beta, the repair rate of the VMM. So what is the change in the availability? We observe these trends. So the same trend persists in case of the profit with the different change in the values of different parameters. We obtain the type of trend that we obtained in case of availability analysis. In the profit also, we obtain the same kind of trends. So these trends are described here. So the same trends are described here. We see that the MTSF increases with the increase in the rate of resolution rate A and decreases with the increase in failure rate of the virtual machine monitor and the failure rate of the shared memory gamma as well. So the mean time to system failure improves with increase in the rate of resolutions from A 0.1 to 0.4, and similarly the MTSF also improves with the the small low values of the failure rate of the shared memory. So similarly, we have the results for the availability and the profit. These are shown in the form of graphs. So these are some of the references of this study. Thank you.
Thank you, Dr. Bharadwaj, for your excellent presentation. And it's a new topic again, because it deals with computing system, which is in a virtual environment, which is the thing nowadays. So any questions from the participants? Dr. Bharadwaj? Are there any questions for Dr. Bharadwaj from the participants? Sir, you said that the migration from one host to another you assume to be instantaneous.
Yes.
Just to develop the model?
Sorry?
That was just to develop the model?
Yeah, just to develop the model. Actually, I'm sorry. No. Okay. Yes. Am I audible now?
Yeah, you're audible.
Madam, actually, in some cases, we can observe such type of things, the instant migration. But always it is not practically viable.
That's
so just to develop the model here, we consider this, take as the assumption.
Have you thought of the other thing also, when the migration may not be instantaneous? Which is
yes, you are very right. Migration is not instant always, and it definitely elapses some amount of time.
Yeah,
and
there is
the
some,
elapsed time again is the random variable. And for that, we have to assume another probability distribution.
That's right.
So
And maybe
we can
all
model
the
that
measures of
concept also.
system performance will also change then accordingly.
Yes, of course.
Very interesting talk, sir. I think if there are no questions, then let me thank you, sir, on behalf of the organizing committee for your excellent presentation.
Okay, ma'am. Thank you. Thank you very much. Thank you, Professor Satish Kumar. Thank you very much for giving me the opportunity to present this topic. Thank you, ma'am, for chairing the session. And thank you, all the patient listeners. Thank you very much. Thank
We
you.
thank all the participants also for their patient hearing.
Okay,
thank you very much, sir. We wind up this session then. Thank you.
Thank you, Professor Gani, for showing the session in a very excellent way. And also, Professor Bharadwaj and Professor Sarojamma for their excellent presentation.
Yeah,
thank you so much.
Thank the speakers and thank you all. Thank you, sir, for organizing such a wonderful conference year after year.
Yes, thank you a lot, madam. In fact, all these are because of you people. Now let us move to the, because we are now 2-3 minutes running late, so that we can move to the next session.
We can move to the next session.
Yeah. Thank you, Professor, for the support. Now the Neha Gandhi is to chair and our Professor Kajan Jain is to speak in the next session. Everyone are waiting for her deliberations. Or anyway, let us go. Neha, please introduce the chair.
Yeah, thank you so much. Thank you so much, sir. A very good evening to all. First of all, I would like to thank Professor Satish Kumar, sir, for giving me this opportunity. Now, let me take this privilege to introduce our special invited speaker of this session.
Just a minute. My MSc student is here in the group to introduce you the chair.
Okay.
After you have to invite. Just a minute. 1 minute. Neha is here in the group?
Yes, sir, I'm here. Okay, sir.
So she is also Neha.
Dr. Neha Gar to chair this session. It's very interesting talk we are expecting from Professor Kajanji. Yeah, please.
Thank you. Thank you.
Yeah, please.
Good evening to all. We move on to technical session number 33. This is a special invited session to be chaired by Professor Neha Garg, Assistant Professor, Indira Gandhi National Open University. She completed PhD from Department of Statistics, ISS, Dr. B.R. Ambedkar University, Agra, and PGDE from Indira Gandhi National Open University, New Delhi. Her main areas of research include estimation and sampling techniques, statistical inference, and biostatistics. She had played a major role in designing and developing courses of new programs at different levels of degrees, diplomas, and certificates in statistics. She has published several books and monographs. Professor Neha Garg is a life member of Indian Society of Agricultural Statistics, Society of Statistics, Computer and Application, Indian Society of Probability and Statistics. We're truly fortunate to have you here, ma'am, to chair in this session. Without any further ado, I once again extend a warm welcome to Professor Neha Garg on behalf of organizing committee and kindly request you to take over the session. Over to you, ma'am.
Thank you so much for your kind words. Now, let me take this privilege to introduce our special invited speaker of this session. Today, we have with us Professor Kanchan Jain Madam from Department of Statistics, Punjab University, Chandigarh. She is a former chairperson and head of the Department of Statistics, Punjab University. She has won Excellence in Research Award by Indian Association for Reliability and Statistics and selected as a Distinguished Women Researcher in Statistics by Venus International Foundation, Chennai. She has more than 42 years of teaching and research experience. Her research area includes reliability, actuarial statistics, survival analysis, biostatistics, etc. She has also qualified for many examinations in actuarial education. She has been an adaptation author for the book Shyam's Outline in Probability, published by Tata McGraw-Hill, and she is an editorial board member of the Journal of Indian Society of Probability and Statistics, Journal of Graphic Error University, Advances in Reliability USA, and Interstat. Beside these, she is a Fellow of Royal Statistical Society, London, an elected member of International Statistical Institute, Netherlands, National Academy of Sciences, Calcutta Statistical Association, International Indian Statistical Association, ISPS, and many more. She has supervised 13 PhD students and 4 ongoing research students. She has published more than 63 research papers in reputed national and international journals, delivered many talks in national and international conferences, as well as organized and coordinated many conferences, workshops, and training programs. We are very fortunate to have such an experienced speaker here. Now, on behalf of organizing committee, as well as on my personal behalf, I welcome Professor Kanchanjan Madam for this special invited session. We are very eager to hear you, ma'am.
Thank you, Dr. Neha, for your kind introduction. And I wish to thank Dr. Satish Kumar also. Actually, I was not, I was too engrossed in some other things, but he kept on sending me messages so that I could participate in this conference. And today also I'm not too well because of cold weather. So, but, and this talk that I'm going to deliver today, okay, just a minute, I'll present first. Ma'am, can you see?
Yes, ma'am.
Okay, thank you. So my talk is on meta-analysis for fixed, random, and mixed effects. And in the beginning only, I wish to admit that this paper doesn't have too much of theoretical research. I'll be just introducing few concepts and then an application for some medical data. So that's what I'm planning to do in this talk. And you see, what is meta? Actually, why am I seeing 2 slides? Just a minute. So what is meta-analysis actually? Meta-analysis provides the statistical analysis of large collection of analysis results from individual studies for the purpose of integration of the findings. It's a scientific method to accomplish this goal by applying sound statistical procedures, and it produces a stronger conclusion than provided by any individual study. And its analysis of analyses, an objective and quantitative methodology for synthesizing previous studies and research on a particular topic into an overall finding. It also allows to collect, code, compare, or combine results from different studies and interpret using statistical methods, helping in decisions about the strength of observed effects and reliability of the results across a range of studies. Now, objectives are to test the homogeneity of the existing findings, draw some general conclusions, estimate an average effect size, where effect size we know is the size of the relation between 2 variables, 2 intervention groups also we can say, and it tests potential moderators if the studies are homogeneous, and provides methods to meaningfully combine the results from component studies. Why do we need it? You see, because often we have a lot of information from many studies, which are sometimes contradictory. So by using meta-analysis, we get a tool for investigating this study, and it increases the statistical power, resolves uncertainty, and improves estimate of the effect size. It can answer the questions which are not posed by individual studies, and many studies on a research topic are carried out rather than a single study to strengthen the overall conclusion about a certain hypothesis. For literature review, these are the references which one can look into for applications of meta-analysis. Hedges and Alkan, Cooper and Hedges, Hasselblad and Hedges, Irving, all, Sutton and all, Egger and all, Schulz and all, Krasonsky and Hand. Actually, the last one is quite a good reference for study of meta-analysis. Now, what is the protocol? Protocol is defining research objectives. For example, one wishes to assess the overall evidence of effectiveness of calcium channel blocker, CCB, which is abbreviated as, in the treatment of mild to moderate hypertension. This mild to moderate hypertension definition can vary from study to study. So there is need to specify what is meant by mild to moderate, which has changed over the years, effectiveness measure or outcome, since BP varies with position, for example, sitting, standing or supine, then some studies may report mean arterial pressure, rather systolic blood pressure or diastolic blood pressure. But there is a need for some same outcome for each study. And type of control group, it can be a matching placebo or it could be another standard drug. Type of design can be parallel, crossover, balanced, unbalanced, single, or double blind. And type of patient will depend upon the age range, race, ethnicity, gender, etc. Then there is an inclusion or exclusion criteria for patients, length of study, which can vary from 1 month to 1 year. It can be 6 months as well. And when we have to search studies for doing or for performing meta-analysis, these are the few sites, you can say, or few places where we can get studies where we can perform meta-analysis: PubMed, Embase, Web of Science, clinicaltrial.gov, and NCBI, and many more. Now you see, because my talk is titled as meta-analysis or for 3 types of models. So first is fixed effects model. So this will be a quick introduction to this fixed effects model, though it's not a everybody knows what is a fixed effect model. So major assumption is that all studies, they share a common overall effect size with the same impacts from all other risk factors. So this is a fixed effect model. And we assume that treatment effect is estimated by theta IF cap and its variability estimated by VIF cap for each study, ith study, where we have capital N studies in the process. In our study, we have capital N groups. Each theta IF cap, this is an estimate of the global overall true effect, theta F across all studies. And basic assumption is that all factors that influence the effect size are same across all the studies. Then weighted estimator of theta f is given by 1, where theta f cap, we attach some weights, and because for ith study, we have this WIF weight, and this is the estimator, and then we sum over all the studies. And where WF, which is the sum of all the weights, will be 1. Moreover, for n independent studies, variance of theta f cap is given by WIF square, these are the weights again, and estimate of the variability. There can be different choices for WIF. Either simply it's 1 over capital N, where capital N is the fixed number of studies, or it can be small ni over n. Ni is the number of subjects in the ith study, and small n is the total number of subjects in all the studies. Or I can take WIF to be this NID, NIP, where NID and NIP are the number of patients in the treatment group D or placebo group P. Or another form of this weight is 1 over estimate of the variability. And what is an unweighted estimator? It is just average of these estimators. Theta IF corresponds to ith study, and we divide it by capital N, the number of studies. Variance of this theta cap is given by this, because we had 1 over n. So now we have 1 over n square and sigma, estimate of the variability. And confidence interval 95% is given by this. So this is the standard way of writing the confidence interval, where estimate of theta f and its variance depends upon weighted or unweighted estimate of the treatment effect. And if we wish to test that theta f is 0, the treatment effect is 0, versus that it's non-zero, the test statistic, it should be statistic, is theta f cap minus theta f over this. We are standardizing actually in a way, and this follows T distribution with capital N minus 1. If the number of studies is too high, then it will be approximated by normal distribution. Then a random effects model can be described as an extension of the fixed effects model. This assumes that treatment effect theta IR. Now, because of random effect, we are denoting it by R. From each study is an estimate of its own true treatment effect theta IR with variance VIR. And this can incorporate both within study and between study variabilities, which are important source of heterogeneity in a number of studies, in multiple studies when you have more than one study. And random effects model provides an unconditional inference about a large set of studies from which only capital N studies are included in the meta-analysis. So here this estimator follows normal theta IR, VIR, where again this is the variability, and theta IR, this will, the original theta I, this will follow normal with theta R and delta square R, where this represents between study variability around the global treatment effect theta R. So, random effect model is written as this theta IR is theta R, ith group effect can be split into these three parts: theta UIR plus EIR. EIRs are the errors. They follow normal with 0 and VIR, variability, and UIR follows normal with 0 and lambda square R, where I told you that lambda square R is the between study variability. So they describe the within center and between center variations. These are assumed to be independent, UIR and EIR, and so we can rewrite this as normal theta IR cap to be normal theta R VIR plus del square, R. And weighted, if we use weights, then again this is the weighted mean of theta IR caps. Standard error is given by 1 over the weights, and the weights are given by this variability, and this is again testing the heterogeneity. And 95% confidence interval for theta R is, again in the standard form we write the confidence interval. This is how we write confidence intervals. 1.96 is corresponding to 95% confidence interval. So there are various methods for estimation of delta R square. And most commonly used estimate is from der Simonian and Lade. And this is derived using the method of moments. Estimate of this is given by Q minus n minus 1 over V, where this Q is the squared difference between these two estimates into the weights, and this follows chi-square with n minus 1 degrees of freedom. And capital V is defined in this manner. And this Q statistic is used for testing the significance of heterogeneity across studies. It should be statistic again, actually. Then what is a mixed effect model? It contains both fixed effects and random effects. They are useful in a variety of disciplines in physical, biological, and social sciences, particularly useful in settings where repeated measurements are made on the same statistical units. That means we have a longitudinal study, or measurements are made on clusters of related statistical units. And because they are advantageous in dealing with missing values, mixed effect models are often preferred over more traditional approaches such as repeated measures ANOVA. And we can include one or more moderators in the model. Moderators actually affect the strength or direction of the relationship. So, which may account for at least part of the heterogeneity in the true effects. So this is the model given by 10. We write the model in this manner. This UIM is normal, 0, del square m. So theta im is the true effect of ith study. Yij is the value of the jth moderator variable for the ith study. Beta naught is the expected effect size. In case Yij is 0, beta j shows how the jth moderator influences the size of the true effect for 1 unit increase in Yij. This is how we define regression coefficients actually. Here it's influencing the size of the true effect. And del square m is the amount of residual heterogeneity among the true effects because we are taking these residuals following normal 0 del square m. Now, as I said, my talk is mainly on a practical application. So we consider this age-related macular degeneration, which is an eye disease, AMD, it's abbreviated as AMD. It's a common degenerative disease among the elderly population, leading to distorted central vision in the early stage and severe visual loss in the advanced stage. It's a complex disease with multiple genetic and environmental factors. Analysis of data has been carried out using fixed, random, and mixed effects meta-analysis models. We have details of studies conducted by 20 authors during these years, along with frequencies of treatment, positive and negative, and control groups, which are mentioned in the table on the next slide. So this is the data. We have 20 trials. These are the authors. These are the years. Here, positive treatment, negative treatment, positive control, negative control, and some weights are assigned to these trials. So we have weights as well, and we have other information. So when we analyze this data for fixed effects model, we get an estimate of theta f, standard error, p-value for testing the null hypothesis, the treatment effect is not significant, and the limits, confidence limits. And here, these are the values that we have obtained. Estimate of theta f is coming out to be minus this. Standard error is 0.054. Z value is coming out to be minus 1.961. P-value is this. P-value actually is not very far away from 0.05, but still it is smaller than alpha 0.05. And lower confidence interval limit and upper confidence interval limits are these two. So, for this model, the estimated average log relative risk, actually now my theta f is my average log relative risk. This is equal to this 95% confidence interval we have seen there. Z is this, p-value is smaller than 0.05. So null hypothesis is rejected at 5% level of significance. So this means the average log relative risk is significant. And these results are represented in terms of forest plot. I'll show the forest plot and let you know how we read it. And figure shows the relative risk of AMD in the treated versus control group with corresponding 95% confidence interval in individual studies based on a fixed effects model. You see, this is what is called as forest plot. Here we have authors and year, treatment, plus minus, control, plus minus. Here we have 95% confidence interval and the relative risk. So these values are given for all 20 studies, and this model, FE model, shows the overall relative risk as 0.90. So this last line row gives me the overall relative risk. And this is the corresponding confidence interval for this relative risk. So these forest plots actually show the relative risk for each study like 0.95 is for first study. If I look at 0.99, it is for this study corresponding to G and 2009, and T last one is having this relative risk. So this is how we read this forest plot. Then we have radial plots. These are also known as Galbraith plots. They assess the consistency of the observed outcomes which have differing precisions. Why do they have differing precisions? Because of heteroscedastic sampling variances. For a fixed effect model, the radial plot shows the inverse of the standard errors on horizontal axis, 1 by root Vi, against individual observed outcomes, which are standardized by their corresponding errors, standard errors on the vertical axis. So we have Yi over root Vi on the vertical axis, and on the horizontal axis we have 1 by root Vi. On the right hand side of the plot, an arc is drawn, and a line projected from 0, 0 through a particular point within the plot onto this arc indicates the value of the observed outcome for that point. And this actually, this is the plot, radial plot. So we have 1 by root Vi on horizontal, Yi over root Vi on the vertical axis. You see, actually this is a band now. All the studies here have been put as dots. So if I look at this arc, right side arc, this band is between some value here and here, not exactly minus 0.02, but it is somewhere above this value. Then we start looking at these points from right to left. When we look at these points, this is my first study, this is my second study, this is third study, then fourth, fifth, sixth, seventh, there is an overlap. Then we go on like this for all studies, and this is my last study. So what is happening? Third and last study, those dots are not inside this band. So that's why we had said here, third and last study estimates of the average log relative risk of AMD from the right end of the arc are outliers. And most of the other points are consistent with the radial line, which corresponds to minus 0.12 log relative risk of AMD disease. So we have looked at the outliers by looking at the points which are outside this band, and the middle point, average here is here, this central line. So that is how we read this radial plot. Then for random effects model, when we used, actually all these calculations have been done in R using meta package or meta R package. There is one other metaphor. So those packages have been used, and here this estimate of theta comes out to be this standard error, Z value, P value, and these are my lower and upper confidence interval limits. So if I apply test for heterogeneity.
Excuse me, ma'am.
Yes, ma'am.
Sorry to interrupt you in between. I think we are running short on time.
Okay, ma'am. I'll be
extremely
fast.
sorry. Yeah.
Okay, ma'am. Thank you. So this Q we get, which tests for heterogeneity, and P value is coming out to be this. So So this is the estimate, 95% confidence interval, and estimated relative risk through exponentiation, because we have been writing log. So this will be 0.87. This is my confidence interval, and p-value is smaller, hence the null hypothesis that theta is rejected. Then this table shows the estimates for del squared. This is actually just square root, then I square, h square, and these are estimates of heterogeneity and variability. So this IR square here estimates, ma'am, I don't have 60 slides, I have 40 something. How much of total variability in the effect size estimates can be attributed to heterogeneity. HR square is the ratio of the total amount of variability to the amount of sampling variability. If this is 0, IR square will be 0. And if del R square is 0 estimate, then HR square will be 1. And heterogeneity here, P greater than 0.05, so this will imply homogeneity. Forest plot is again shown in similar way. Total relative overall is 0.88 with this confidence interval. Then we have funnel plots also. They are useful for diagnosing the presence of heterogeneity and certain forms of publication bias. For models without moderators, figure 4 shows the observed outcomes. I'll show you the figure actually. And this confidence interval is again plus minus 1.96 standard error. And we draw it around the value. And in absence of publication bias, studies with high precision get plotted near the average. And studies with low precision, they spread evenly on both sides of the average. So creating a roughly funnel-shaped plot. So in the absence of heterogeneity, 95% of the studies should lie within the funnel. This is the funnel plot. Here, most of the studies are inside this funnel. Only 2 are outside. So this shows no publication bias. Studies with high precision are plotted near the average, and studies with low precision are spreading evenly, and no heterogeneity, as 95% of the studies are lying within the funnel plot. And radial plot, again for the random effect model, is shown here. Then we have QQ normal plots also. I think I'll show this plot. So this is a QQ plot for random effects model. So we have this diagonal line. This is the band actually. So it should lie within, the points should lie within this band, and so no heterogeneity. Then for mixed effect model, we have the estimate, standard error, Z value, P value, lower limit, upper limit, and estimates of heterogeneity and variability are given here. So testing for moderators, we get this Q value, P value is this. So total amount of heterogeneity can be accounted for by including 2 moderators in the model is 100%. So although this is rejected, as for QM test, our P value is smaller, but this is not rejected, beta 1 equal to 0. And this beta 2 equal to 0 is also rejected. So this means that only one moderator is having a significant influence on the effectiveness of the treatment, not both. So again, we have this funnel plot for mixed effects model. Here one study is outside, most of them are inside the funnel. So we say that there is no heterogeneity in the study. And this is the QQ norm plot. Here again points are inside the band, so no heterogeneity is displayed when we are using mixed effects model. So A data set from 20 studies has been analyzed. Treatment effect is statistically significant for fixed and random effect models. For mixed effect, only year moderator appears to have a significant influence. But based on QM test, both moderators have significant influence. And various models plots have been plotted. And we can talk of meta regression also. And these are the libraries: Meta, RMeta, Metaphor, and there are other packages also. And we have done work on 4 papers. Actually, this is also published, last one. So there are 4 publications by our team of Dr. Savita Jain and Professor Sharma. So we have been working together on this. So thanks.
Thank you so much,
Sorry,
ma'am.
ma'am, I had to rush.
Yeah.
at the
It was indeed a very good and informative session. Now this
Thank you.
forum is open for any query or discussion. Any question from the participant? Okay. Since there is no question, then now let me thank Professor Kanchan Madam for sparing her valuable time and for such a wonderful talk on meta-analysis. Thank you so much, ma'am.
Thank you, ma'am,
also
Dr.
like
Neha,
to
and
thank
thank you, Professor Satish.
I would also like to thank all the participants for their patience and attentive listening. And a very big thanks to Professor Satish sir and all organizing team for organizing such a wonderful event every time. Thank you so much.
I'm sorry that I had to rush at the last. Okay, thank you.
Thank you so much, Professor Kanjan Jain, for your wonderful talk.
Thank you.
I just like to say hello to Kanchan.
Meet again. Hello, sir.
Kanchan,
Yeah.
this is Hira Kaul.
Yes, sir. Yes, sir. Nice to see you, sir.
Nice to see you too.
Professor Satish keeps giving us opportunities to see each other.
Next time in Trivandrum.
Yeah, yes. Yes, sir.
Once again, thank you, Professor Kanjan, for your nice talk. And also, Professor Neha, Dr. Neha, for your very attractive and excellent managing of the session. And yeah, thank you so much. And now we have let us jump to the next sessions, which are in fact concentrating the direction of the biostatistics and related concepts from the world-renowned figures like Professor J.S. Thogoban is here, the organizing to the sessions, where several are waiting for watching and hearing those talks. In fact, I utilize this occasion to invite each one of you, especially Professor Jaya, for your support. And now, Gogol is here in the group.
Yes, sir.
Gogol, please introduce the chair and thereby support her to run both sessions in a smooth way. Please, Professor Jaya to chair the sessions as the organizer as well as the chair of the sessions. Please take care of.
A warm welcome to everyone. I hereby welcome you all to the technical session 34 with the session chair and organizer, Dr. Jaya Shadagopan, on the title Recent Advances in Statistical Methods and Their Applications. She is currently working as professor at Department of Biostatistics and Epidemiology at Rutgers School of Public Health. Dr. Jaya received her PhD in statistics from the University of Wisconsin-Madison. Her research focuses on statistical genetics or genomics with application in cancer epidemiology and tumor biology studies. Her research topic includes cost-effective study, designs for genome-wide studies, and dimension reduction, among others. She established the Center for South Asian Quantitative Health and Education at Rutgers, which studies cancer and allied diseases and aims at promoting cancer prevention in these communities. We are really fortunate and honored to have you, Professor Chandragopan, chairing this session with us today. So with great joy, I welcome you, ma'am, to chair the session. Over to you, ma'am.
Thank you, Gokul. Good evening, everyone in India, and good morning to my colleagues from the United States and anywhere else. It is morning right now. My name is Jaya Sadagopan, and thank you, Gokul, once again. And thank you, Dr. Satish, for putting together a very successful and wonderful conference once again. Before I begin the session, I just want to mention very quickly that I am traveling with my family where it is pouring outside. So I hope I do not have any internet connectivity. But just in case, I want to let my colleagues, Liang Yuan, Pam Strickland, and Xuan Lu, that please pick up and organize yourself. I don't want to put you in the spot, but it's just pouring cats and dogs outside.
Hi, Jaya, this is Showen. I'm sorry to interrupt. I seem to have a problem with my camera.
Okay.
If you don't mind, maybe I could just, double check with my video audio equipment and then and jump into the, join the talk when ready.
Sounds good. Yeah, please.
Thank you so much.
Thanks. And so this is, we have 3 speakers in this session. All 3 are my colleagues from Rutgers University's Department of Biostatistics. So let me introduce all 3 speakers just in case I have internet connectivity, and I will invite one speaker at a time. The first speaker in this session is Dr. Liang Yuan Hu. Dr. Liang Yuan received her PhD from Brown University, and she was an assistant professor of biostatistics at Mount Sinai's Icahn School of Medicine in New York City, and joined Rutgers University last year as an associate professor of biostatistics. Dr. Liang Yuan's research work is in the areas of causal inference, missing data, and Bayesian inference methods and their applications in cancer. Our second speaker is Dr. Pamela Oman Strickland, who is an associate professor at Rutgers University. And Dr. Strickland received her PhD from Cornell University and she spent some time in University of Florida and has been with Rutgers for several years now. Dr. Strickland's research works and interests are in small sample analyses and methods for small sample data, and also working with categorical data, and in particular applications in environmental exposure data and cancer. Our third and last speaker in this session will be Dr. Xuan Lu, who is an associate professor of biostatistics at Rutgers University. Dr. Lu received her PhD in biostatistics from Johns Hopkins University and subsequently joined Rutgers. And Dr. Lu's expertise are in and interests are in case control design, analysis of related data, and also analyses of survival, that is time to failure or time to event data. So I want to thank all my colleagues who are here for agreeing to present their works in this session. And this session is about 1 hour and a half long. So each speaker has about 25 minutes time. And I'm hoping that we can have a talk for length 20 minutes and time for question and answer for 5 minutes is approximately what we have in mind, but we can work with how it goes. So with that, I invite our first speaker, Dr. Liang Yuan Hu. Liang Yuan, please share your screen and begin your presentation.
Sure. Thank you, Jaya, for the kind invite. Should I press the button that says present now?
Yeah, there is an arrow. Yes, present now. That's the button you press. And then click on the small window that appears. And then I think you will say share, or you will say present your entire screen, actually. That's what works best for me.
Okay.
So click on that, say your entire screen.
A small upward arrow in the bottom. Click on that. A small box, pop-up box.
Yes.
And you can choose the entire screen.
Yeah. If you choose a window or tab, it doesn't work well for me. So please choose your entire screen.
Okay.
Now,
and then click on the
Click on that box
what you see there.
in the middle part. The share button will be active. Share will be active in blue color.
So when I click it, it says
Yeah,
I cannot share my screen. I have to go to System Preferences.
Oh.
Click in the middle part. The share will be active.
So can you email me your talk, Liang Yuan?
Yeah, sure.
Okay, I can share it for you.
Open System. Let me just try it one more time. Is there some problem with Google Chrome?
Once again, just try. If it is not difficult for you, just click on that upward arrow, then choose the entire screen, then
I think we lost Liang Yuan here. We are unable to hear you, Liang Yuan. I think you are on.
Sorry about that. Yeah. Let me just email you my slides.
If you can email me and Shuan as well, or Pam, just in case I lose connectivity.
Okay.
If that's okay with you, Shuan. Sorry to put you on the spot.
Okay. I just emailed you my slides.
Yeah, it should. I am waiting to receive it. So. Have you received it, Shuan?
Not yet. I'm still waiting to.
Okay. So in that case, if that's okay, Liang Yuan, while we are waiting to receive your slides, Pam, would it be okay? Would you feel comfortable starting your presentation? And then when Pam finishes, we can come to Liang Yuan. Is that okay?
Sure. Yeah.
Okay. So yeah, let's begin with Dr. Pam Oman-Strickland's presentation.
I am working on it. There we go. Can you see my screen?
Yes, I can.
So, yes,
yeah, it
perfectly.
shows discussion.
Whoops. Let me go to the beginning.
Yeah. Great. Thanks, Pam.
Yeah. So this is kind of outside of my typical area of expertise, but it is actually a really good example of kind of propensity score use in the presence of missing data in assessing the effectiveness of COVID treatment. So kind of more in the area of causal inference. And it's just a really good illustrative example of propensity scores. So I'll give some basic background on the COVID-19 treatment and then go through the analysis and results. We're using propensity scores because the treatment was there were guidelines for the use of the treatment but they were inaccurately followed. And the treatment was given in the early stages of the pandemic, and it was used under emergency use authorization. So there weren't really sufficient evidence concerning the efficacy of the treatment. And of course, in the process, there was a reasonable amount of missing data, which could potentially have affected the results. So early in the pandemic, the only treatment available for COVID, particularly for mild to moderate COVID, was this monoclonal antibody treatment. And it was intended for patients with mild to moderate COVID in non-hospitalized settings and for adults who were 18 years of age or older. What these antibodies did was they targeted the spike protein in the COVID molecule, and then in order to prevent it from attaching and entering the body's cells and then replicating within the body's cells, which is the way that COVID kind of infects the human body. I would, just as a side note, now there's alternative treatment for COVID. Generally, the treatment is remdesivir, which is widely used due to its better efficacy among the newer variants of COVID. But I'm focusing purely on MAB treatment. So MAB was approved by the U.S. Food and Drug Administration under emergency use authorization. And it's given as a single infusion in an outpatient setting. It's recommended for patients that are high risk of progressing to severe disease. And so what puts patients at high risk of progressing are they're at least 65 years of age, or they have immune disease, or they have they're on immunosuppressive medications, or they have chronic kidney disease, diabetes mellitus, or they are at least 85 years of age, and they have one of the three listed chronic conditions. Let's see. So the research question is whether MAB is effective at treating COVID in the general population, and how effective is it? The data was collected from the emergency department at a major hospital in central New Jersey that serves a very diverse population. So it's diverse with respect to race, ethnicity, and also socioeconomic status. As we stated, this is not a randomized clinical trial. It is an observational study, and hence there's a need to kind of try and sort out what the treatment effect is in the presence of quite a bit of noise. And I would note one of the things that makes this study possible, interesting, but also necessary, is that some of the patients that arrived at the ED with COVID who were not eligible for treatment actually did receive the treatment, and vice versa. Some that were eligible upon arrival at the ED did not receive the treatment. And so there's a lot of overlap in terms of who should and who did receive the treatment. So in our analysis, the explanatory variable is the administration of MAB via infusion. We're actually using some intermediate outcomes just because mortality was such a low occurring event. So we use return to the ED due to COVID-related reasons. And then third was whether they returned to the ED and were hospitalized. And then fourth, whether they returned to the ED and were hospitalized due to COVID-related reasons. So in terms of the methodology, we use the basic propensity scores based on a causal effect model. So this is kind of useful for adjusting for confounding, particularly with respect to whether people receive treatment or not. So the propensity scores are based on a number of variables. And so one of the questions is, which variables should we use? And there are a couple of options here. We can either empirically determine which covariates predict treatment assignment and use those covariates, or we can select covariates that are determined by expert knowledge. In this case, the guidelines for using MAB treatment. I would note there that Paterno et al. Just complementing the expert knowledge with empirical evidence to reduce the bias in the estimates. So we're going to end up looking at both. Here's a picture of the data that we had. Overall, we had 1,774 subjects presenting at the emergency department with COVID, with 62 meeting recommendations for MAB. I did restrict the analysis to those that were at least 35 years of age, just because the younger individuals did not receive the treatment at all. So in order to create matches of treated and untreated, I needed to look at this slightly older age group. Among those 1,511 subjects in the smaller sample, 71% met the recommendations for receiving the MAB treatment. However, despite the recommendations, despite our guidelines, of those not meeting the recommendations, 31% actually did receive treatment. And of those who did meet the recommendations, 19% did not receive the treatment. In terms of the outcomes, around 13% returned to the ED, and around 7% who returned to the ED were also admitted to the hospital. So fairly low occurrence of our outcomes. So just for illustrative purposes, here are the naive estimates where I ignore the bias in treatment assignment, or I ignore the covariates that determine whether somebody was given the treatment or not. And so what's presented is the odds of a negative outcome given that the person did not receive treatment versus that they were given treatment. So these odds ratios are between 1.23 and 1.38. So if I look at the first one, I would interpret that as the odds of returning to the ED are 23% higher for those who didn't receive treatment versus those that did receive treatment. Of course, our confidence interval includes 1, so it's not, we would say that it wasn't a significant effect of treatment. Of course, there's some bias here because the more severe the COVID, or if people have some of the risk factors for worse outcomes, they're actually more likely to be treated. And this actually biases our odds ratios towards the null value of 1. So we want to do some adjustment, and we're going to do that using the propensity scores. So as I said, we're going to identify our covariates using propensity scores, and I can do that either by empirically selecting which covariates determine whether somebody received treatment or not. And I did that just using a basic stepwise regression. And then secondly, I can select the covariates that reflect the risk factors identified in the guidelines. Once I have these propensity scores, I'm going to match the treated and the untreated. And that's going to mimic kind of a random treatment assignment within kind of matched groups of subjects. And then I'm also, in addition to using the propensity scores to match the subjects, I'm also reweighting with respect to the propensity scores, which fine tunes the estimates a little bit more, and also makes the results, the inference appropriate to the target population, which is the entire population of COVID positive arrivals at the emergency department. One of the obstacles here is that when we looked at our data, there were 18% of our observations were missing a value for at least one of the variables that were selected for use in creating propensity scores. And so we used some multiple imputation to deal with that issue. So once we did the multiple imputation, we went back to the stage of creating propensity scores based on the covariates and kind of redoing our matches, and then kind of going through the whole analysis and combining the odds ratios estimates from the multiply imputed data. Note that in order to do this, we did assume that kind of any missing values were missing at random. So here are just some results. On the left, there are two columns here. One is the covariates that were selected for propensity score matching based on kind of the empirical results, the stepwise regression, looking at which covariates determined whether somebody was actually given the treatment or not. And so there's a lot of covariates in here, including things like race, ethnicity, some physiological measurements, temperature, oxygen saturation, which we know was an indicator of severe COVID, as well as weight, diabetes, etc. On the right-hand side, we had the risk factors identified by the guidelines. And as you can see, there's some overlap, but it's not a perfect overlap. So in doing our propensity scores, we allowed up to 5 treated patients per non-treated. We had a larger population of treated than non-treated patients. Although on average, it was closer to 2 treated per non-treated. Propensity scores were determined using the covariates from the previous slide. And we use greedy nearest neighbor matching in order to create the matched patients. And we did this because it was the least computationally intensive approach. With as many covariates as we had in the empirical derivation of covariates, the other approaches for matching just were too computationally intensive. I played with the caliper, which is the allowable distance between the log propensity scores, between the treated and untreated in a matched set of observations. And I started with a larger caliper and then kind of reduced it until I was kind of within the recommended distance. And I ended up having to use a caliper of 0.35. And the idea here is that I want to match my observations as closely as possible, but still use as many patients as I can in the analysis. If I try to match too closely, I lose more observations, but if I use more observations, then they're not matched quite as well, and it doesn't mimic the randomized clinical trial quite as well. And so that so there's a balance there. For the complete case, so I did one analysis, which was kind of just using complete cases, so without the multiple imputation. And there was 84% of the data, as I said, had complete cases, After matching, the analysis was based on only 951 observations out of the 1,511 that might have been available for analysis. And this was with an average of 2.3 treated patients per non-treated patient. Once I did the imputation, kind of on average, I was actually able to use, after matching, I was able to include around 1,176 observations in the analysis. So it increased my sample size quite a bit, with an average of 2.3 treated per non-treated patient. So here are the results from the analysis. There are 3 columns of results. The first is the naive results that I've already presented. In the second column of results, that's the complete case analysis, where I use the propensity scores. So that's kind of deleting any observations where there's missing values. And you can see that the odds ratios actually do move away from 1. So instead of odds ratio of 1.23 for returning to the ED for non-treated versus treated, I have an odds ratio of 1.62. In addition, I now have significance of my treatment effect. The confidence interval doesn't include 1. After multiple imputation, which is the third column, my odds ratios are about the same, but I do gain some more precision. So my confidence intervals are substantially narrower. So it gives me a little bit better handle on the actual effect of treatment. And you can see that for admission to the hospital, I can be pretty confident that my odds ratio is at least 2. Whereas for the returning to the ED, my odds ratios are at least 1.4. So there's a pretty good effect of treatment. And I just wanted to also give the results for the a priori use of covariates, i.e. using the covariates that are specified in the guidelines for application of treatment. So this using these covariates, I actually had close to the full data set to use. And so I didn't do multiple imputation. After matching, the analysis included 1,192 of the observations, with an average of 2.5 treated patients per non-treated. And again, this chart is comparing, in the first column of results is, again, the naive unadjusted results. The second column is the results from the a priori selected covariates for creating propensity scores. So what I just talked about on the previous slide. And then the final column is the results from before with the covariates that were empirically selected and the analyses using multiple imputation. So it's interesting using the a priori selected covariates for the assignment of treatment. The effect of treatment on returning to the ED increases a little bit, but the effect on admission to the hospital actually decreases when I use the a priori selected covariates. So the truth is probably corresponding to the effect of treatment is probably somewhere in between. So as we see here, the propensity score is critical for accounting for the bias in the treatment assignment and estimating the actual effect of treatment. what I'd like to do kind of next is kind of look at some variable selection techniques that would actually give some preference towards the covariates that are indicated by the guidelines as risk factors for serious disease and therefore receiving treatment. I would note that our sample size is small enough that I was not able to do kind of a split sample and kind of estimate, do a selection of covariates and then look at the effect of treatment on the confirmation data set, just with the small number of potential outcomes. So that is what I have.
Thanks a lot, Pam, for your excellent exposition. So I think you can stop sharing the slide so that everybody can be on the screen. Yeah. Let's please join me in thanking Dr. Pam Strickland on an excellent talk. We have time for maybe a couple of questions. Is anyone in the audience, does anyone in the audience have any questions for Dr. Strickland? There are several students from the University of Kerala in the audience. I'm sure you're all learning about categorical data analyses and missing data and so on. I hope you found this as an excellent opportunity to see how these are applied. And if you have any questions or any others have any questions, please unmute yourself and speak now.
Mm-hmm.
And Pam, I have a quick question for you.
Yes.
If nobody else has any questions. So you partly addressed it in the final slide. And Liang Yuan, I think you're presenting. I think you can stop sharing for a moment. Thank you. Sorry to interrupt you. So Pam, I think you addressed it towards the end, the issue of empirically selecting covariates for propensity score. Is there like a concern of overfitting? Is that why you need a split sample?
Yeah, there's definitely, I did worry about the overfitting, and some of the other reason to try and draw a balance between selection of covariates between expert advice and the empirical is there was certainly some multicollinearity between some of the variables. So I think some of the variables that were empirically selected were potentially correlated with the risk factors that were identified by guidelines. So I would have liked to have kind of weighed it in favor of the guidelines for that reason.
Okay, well, thanks a lot. I appreciate it.
Yeah.
So once again, let's thank Dr. Strickland.
Thank you, Jaya, for this opportunity. It actually kind of pushed me to put this all together.
Great, thank you. And now let me invite Dr. Liang Yuan Hu to begin her presentation. Liang Yuan, please share your screen. And
Sure. Somehow I figured it out, so let me try again. Okay.
I was able to see your. Oh wow!
Oh wow! What is this?
Just open your PDF file of your presentation.
Yeah.
Yeah, I was able to just share my presentation window if that makes a difference.
Okay,
Yeah.
so
Can you
I
stop?
need to stop sharing now.
Yeah.
Okay. So should I share entire screen?
Yeah.
Okay.
You can share your entire screen and open your presentation. Is that how you shared, Pam?
I actually just shared the window with my presentation.
Okay.
Okay.
A window. Okay. All right. Can you see this window?
Now it is coming and fine. Now we can make it full screen if needed. Now it is clear.
Thank you, Dr. Satish. Yeah, Liang Yuan, we are able to see your presentation now.
Yeah.
Okay, sure.
You won't be able to see us, but we are all here.
See you and presentation also. You can.
Yeah. So please begin your presentation, Liang Yuan.
But can you see it's moving?
Yes, it is.
Okay, but all right.
It's fine. Moving.
Okay. Well, thank you, Jaya, for this kind invitation. So I'm happy to talk about one of my recent projects that develops machine learning-based methods to estimate the treatment effects of multiple treatment options on patient survival using sort of clustered survival data. So I'd like to thank my student and co-authors on this project. Also, this work was supported by several methods grants. So this project was actually motivated by a comparative effectiveness research question in cancer research. During my collaboration with oncologists, they oftentimes ask me, so how do we properly simultaneously compare the effects of multiple treatments on patient survival, right? Because in cancer research, to treat solid tumors like prostate cancer, gastric, breast, and liver cancer, there are oftentimes multiple treatment options, including, for example, radiation, surgery, chemotherapy, immunotherapy, or even the combinations of them. So it's very hard, difficult to conduct a large-scale randomized controlled trials to simultaneously compare these treatments all together. So now researchers are more heavily relying on real-world evidence from data on a large representative population that are typically collected from multiple care centers. And because they are collected from multiple care centers, so we would also have to take into account of the multi-level data structure. So, and there are two reasons why we should do that. Because one is that if we just conduct the conventional analysis ignoring the institution, then if there is substantial institutional variation, the inferences from this analysis may not be valid. And then your conclusions about the treatment effects will also not be valid. And also because the second reason is that the institutions are not selected at random, nor the patients. So if there is substantial institutional variation, it wouldn't be very clear exactly what effects would be seen in the general population, in the sense that whether it would be more like that seen in the institutions with good outcomes or that seen in the bad outcomes. So we'll have to take into account of the multi-level data structure and think about the implications of that for causal analysis. Another challenge is that when we draw causal inferences about treatment effects using non-experimental data, we'll have to make some standard assumptions. And one key assumption is called no unmeasured confounding. Sometimes it's also referred to as the ignorability assumption. So how do we properly address this assumption in the presence of cluster survival data? So these methodological issues motivated our project. So the overall goal is to develop a flexible causal inference approach that allows us to accurately estimate the causal effects of multiple treatments from cluster survival data. So in our approach, we'll be leveraging this Bayesian machine learning technique that is called Bayesian additive regression trees, or BART. So this technique has gained popularity in the statistical and computer science fields for its high performance. So BART is a sum of trees ensemble learning technique relying on a fully Bayesian probabilistic model. And it uses regularizing priors to keep the fit of each individual tree small so that we can prevent overfitting. And because it's based on the Bayesian model, probabilistic model, so we'll be able to leverage the posterior draws to provide proper representations of uncertainty intervals about the treatment effect estimates. Unlike other propensity score-based methods like stratification or matching, even now there's still debate about what is the most proper way to calculate the variance. So, and another reason why we want to adopt this technique is because in recent literature, it has been shown that methods using BART are able to provide more accurate estimate of the treatment effects in very complex data settings. So then we'll further develop a sensitivity analysis strategy for unmeasured confounding to address the no unmeasured confounding issue. So suppose we want to estimate the effect of treatment A that can take multiple values, right? So multiple treatment options on failure time T. And then for individual I in cluster K, there is a vector of pretreatment measured covariance xik. And then we use VK to denote clusters. So, and then we can define the average treatment effect based on potential outcomes. So now T of AJ, this is a very causal notation. It means the potential death time or failure time under treatment AJ. Right. Similarly, T AJ prime is the potential failure time under treatment AJ prime. So we can define the average treatment effect as the difference in the expected log failure time had everyone in the population received AJ, and the expected log failure time had everyone in the population received another treatment. Right? By contrasting the two expectations, we get the causal effect. So this is so we can also define the treatment effect or causal treatment effect by using survival probability. And then for simplicity, I'll be illustrating our method using 3 treatments. So we'll be interested in estimating 3 pairwise treatment effects. So notice that we define the causal treatment effect based on potential outcomes. But we'll have to estimate the treatment effect using observed data. So how do we do that? We'll have to make some identifying assumptions, and these are standard causal identifying assumptions. The first one says consistency. Essentially, it says that the observed failure time is in fact the potential failure time under the treatment that is actually received by the patient. Right? Similar assumption goes for the censoring time. And another assumption is a weak ignorability or the no unmeasured confounding assumption. Essentially, it says that the covariance and cluster indicator that are observed in the data are sufficient to predict both treatment assignment and outcome. The positivity assumption essentially says that there's always a positive probability for each patient to receive one of the multiple treatments. And then for survival analysis, we'll assume covariate dependent censoring. So we propose a random intercept accelerated failure time model that uses BART. So we relate log failure time to treatment assignment A and covariance X using the unknown F function. And BKs here are our random intercepts for cluster-specific main effects. Epsilon's IKs here are the errors. So for now, we assume both BK and epsilon IKs are normally distributed and they are independent of each other. And so F function, this is unknown function, unspecified function. So we'll use BART to flexibly model this function. And this is in Bayesian framework. So we'll center the observed outcome first. So little YIK here is the observed event time, right? So if the event occurred, it's the death time or failure time. If the event is censored, it's a censoring time. So we'll first center the observed event time. And these are just regularizing priors we put for on the parameters of our proposed model, so that the fit of each tree is small, the impact of each tree is small, and we'll be able to prevent overfitting. And again, we'll use the observed data and we'll fit some rudimentary parametric models to make reasonable choices about the initial values for several parameters of our Bayesian model, like for the random intercepts and for the standard deviation of the residuals. And then because we're dealing with survival data, so there is right censoring. The technique we used to deal with that is data augmentation. So essentially, we'll impute unobserved survival times. This is a latent variable ZIK from a truncated normal distribution, right? So at the end of the day, we'll be dealing with complete data survival times. So if the event is observed, then we'll use the observed centered event time. If the event is censored and censoring occurred, then we'll be using the latent variable ZIK or the imputed survival times. So our sampling algorithm will first draw the Gibbs sample of the several parameters in our model, and then we'll subtract the random intercepts from the log centered and complete survival times, and then we regress this quantity to on treatment assignment and pre-treatment covariates using BART model. And then from the fitted model, we'll be able to update parameters associated with the BART model. Right? Then for each individual NK cluster, and each cluster will update the latent variable ZIK or the imputed survival times by sampling from the truncated normal distribution. And because we centered the observed outcome, we'll add the term back to our posterior draws. Now, after the sampling algorithm, after we fit our model, we'll be able to obtain posterior draws of the F function. And under identifying causal assumptions, we'll be able to use this F function to estimate the causal effect. So we'll obtain posterior draws of F under AJ, and then obtain posterior draws of F under another treatment AJ prime. We'll take the difference and then average the differences across all individuals in the sample population. And here we obtain the causal effect estimates. So this is in fact a Bayesian implementation of the so-called parametric G formula that was initially proposed in Robbins' 1986 paper. So we completely take a Bayesian perspective, and also we use Bayesian machine learning. So we're able to offer a substantial level of modeling flexibility. So then we compare our method with 3 alternative methods that are popular in current literature. One is the inverse probability weighting with random intercept Cox regression model. In the spirit of using machine learning, we'll use superlearner to estimate the weights. And then we'll also compare to the doubly robust weighted estimator with random intercept additive hazards model. And then we'll compare our method to another outcome modeling based method called piecewise exponential additive mixed model. And because not all methods directly model the failure times, so for fail comparisons, we can calculate the counterfactual survival curves from each method. And then we use the counterfactual survival curves to estimate the average treatment effect on the basis of, for example, the survival probability at a target measurement time, or on the basis of a summary of the survival curve, for example, root mean squared, restricted mean survival time. Performance metrics we use to compare these methods are relative biases, root mean squared errors, and the frequentist coverage probability. So we simulated a bunch of data sets to mimic the data structure that are observed in our real-world data set. We considered both non-proportional hazards and proportional hazards, light censoring and heavier censoring. So this shows the box plots of relative biases across 250 data replications. And you can see that our proposed method, RI-AFT-BART, provided the smallest biases in all of the treatment effect estimates across all data configurations. By comparison, the IPW random interceptor Cox regression model produced the largest bias across all data configurations. Another observation we can make is that the violation of the proportional hazard assumption seemed to have little impact on our proposed method. However, it seemed to have much bigger impact on the other three methods. So now turning to the frequentist coverage probability, we see that the proposed method provided close to nominal coverage probability in all three pairwise treatment effect estimates across all data configurations. By comparison, the other three methods provided less satisfactory coverage probabilities. So that sort of provided the empirical evidence that our proposed model or proposed method worked pretty well in complex data settings. So now we can further elaborate this model to deal with this no unmeasured confounding assumption. We'll be developing a sensitivity analysis approach because it is useful in helping us to gauge how our causal conclusions will be changed in response to different magnitude of departure from this assumption. So we'll develop our sensitivity analysis method based on the concept of confounding function. Right? And the benefit of this approach is that we'll be able to do away with all the concerns about the underlying structure of the unmeasured confounding. And
this is Jaya. You have 5 minutes more.
Okay, sure. And it's good that to help us understand the entirety of the effect of unmeasured confounding. So again, we'll embed this approach within the Bayesian framework. So we'll be able to integrate two sources of uncertainties. One is about the values of the sensitivity parameters, and the other is the usual statistical uncertainty due to sampling. Okay, so we'll just first define the confounding function as the difference in the expected log failure time under treatment AJ, right? But between those who actually received the AJ and those who didn't receive AJ but received another treatment, but who have similar covariates in the same cluster. So if the assumption holds, these two groups of patients are conditionally exchangeable. So all the C functions will be 0. But if the assumption is violated, the C functions will not be 0. And then there will be bias in your estimated treatment effects. And then mathematically, we can derive the exact form of the bias. We don't know the C functions, but we can specify the form of the C functions to represent our prior belief about the impact of unmeasured confounding. So for example, we can specify the signs of the C function to assume that unhealthier individuals are treated with certain treatment, right? Or healthier individuals are treated with certain treatment. And then we can further assume a bound for the C function by assuming that it will explain no more than certain units of remaining standard deviation that is unexplained by measured covariates. So you can ignore the technical detail of the proposed Monte Carlo sensitivity analysis algorithm. But the key idea is that we can adjust the observed survival times using this formula and fit our just proposed model to the adjusted outcome and to obtain the adjusted effect estimates. In the adjusted effect estimates, the bias due to unmeasured confounding will be effectively removed. So very simple illustrative simulation that illustrates that our method worked. We simulated binary measured covariates and binary unmeasured covariates. And we know, because we simulated the data, we know the true C functions. And then we'll estimate the treatment effects in 3 ways. In the first way, we pretend that we had access to the unmeasured confounder U. In the second way, we conduct our sensitivity analysis. And then in the third way, we completely ignore the U. So we see that assuming the correct form of the C functions, our sensitivity analysis produced the effect estimates that are essentially the same with the true effect estimates if we had access to U. But if we completely ignore U, the effect estimates will be very different. So that sort of provided another set of empirical evidence to show that our method worked. Then finally, we applied the methods to a large high-risk localized prostate cancer patients. More than half of the population received the radical prostatectomy. About 30% of patients received external beam radiotherapy with androgen deprivation. Less than 20% of patients received another radiotherapy. We considered 9 clusters, geographical clusters, ranging from New England to East South Central. Confounders include demographic information as well as disease-specific informations, but there are possible other confounders that are unmeasured in the data set, so we'll conduct a sensitivity analysis. So essentially, we'll estimate the treatment effect based on the difference in the log failure time or survival time. We also want to examine the institutional effects. And we conduct our sensitivity analysis assuming that those who received the surgery were the most healthy patients, and those who received the third radiotherapy were the least healthy patients. So the results, this is the posterior draws of the random intercept. It shows that there is a substantial institutional variation. Hospitals in the New England areas are doing much better than hospitals in East South Central area. So after teasing out this institutional variation, we evaluate the treatment effects. Assuming that there's no unmeasured confounding, the results suggest that there's significant treatment benefit associated with surgery compared to the 2 radiotherapy-based methods. However, after conducting our sensitivity analysis, when we assume those who received the surgery were the most healthy ones to start with, then the treatment benefit were negated when we compare to the third radiotherapy group. But the treatment benefit was pretty robust when we compare to the second radiotherapy group. So that's sort of the clinical insights we can draw by applying our methods to this large-scale prostate cancer data. For the future, we can elaborate our model to accommodate random slopes and conduct a sensitivity analysis for cluster-level unmeasured confounding. And we also want to extend this method to accommodate competing risks. So I'll stop here. So this project was just published recently in Stats in Medicine. We also have our free R package. It's called RRAFT BART, available on Chrome. So if you are interested in this paper or using this tool, feel free to download the package, and happy to talk to you more about the details. Thank you. I'll stop here.
Thank you. Stop sharing the screen now.
Yep.
Great. Well, please join me in congratulating and thanking Dr. Liang Yuan for a very nice detailed talk. Is there any one quick question for Dr. Hu, and then we will move on to the next speaker? Anything for Dr. Hu? Maybe come back to it after the next talk, Liang Yuan. Thank you.
Thank you.
Dr. Xuan Lu to begin her presentation.
Okay, thank you. Let me share. Hey, wait a minute. I'm sorry. I'm not sure if I'm experiencing the same issue as well. It looks like I'm unable to share. Let me try again. Should I do?
Joanne, are you trying to share your whole screen or the window?
Yes, I'm trying, but it doesn't allow me to share.
Are you using Mac? You're using Mac, right?
I'm using a PC laptop.
Oh.
I couldn't click the button for share the whole screen, but when I shared just the window and I selected...
Oh, just the window. Okay, let me see.
I was able to do it.
Yeah, presentation.
Oh, I see. Got it. Excellent. Thank you, Pam. Now, can everybody see my screen?
Yeah, now it is coming. Yeah, it is.
Okay, excellent. Thank you so much. Let me see if I can put a full screen presentation. Okay.
Great. Thank you.
All right, fine. Thank you so much, and thank you for the patience. Thank you, Jaya, for the invitation. It's a great pleasure to present my recent work with my colleagues, Dr. Sina Kim, Jerry Chen, Chanfa Lin, and Sama Jabor at Rutgers, Bristol Myers Squibb, New York Institute of Technology, and Deloitte. My work is, I think I forgot to talk about the title of my talk. The title of my talk is The Joint Effects Selection in Generalized Linear Mixed Model Analysis. The generalized linear mixed model analysis actually are pretty commonly used class of models in biomedical research. And it is often applied in situations where the outcomes are correlated and people wanted to relate or describe the relationship between the correlated responses and covariates. And the researchers often want to determine the fixed effects and or the random effects of the outcome variables from a pool of covariates using the variable selection approach. And our study is motivated by a longitudinal cancer study that aims to relate a set of covariates to the incidence of common mammographic sequelae after breast conserving surgery and radiation therapy. And a total of 605 mammograms from 89 breast cancer patients were evaluated with a median follow-up of 48 months. This study actually has been published previously. And then more than 10 demographic and clinical covariates were considered. And the investigators wanted to identify important covariates as fixed effects. They also wanted to determine the random effects to assess if some covariates exhibit heterogeneous effect. To achieve the variable selection in generalized linear mixed models, several approaches have been proposed. For instance, the method of selection using the information criterion such as the AIC or BIC to determine the final models after a set of candidate models has been frequently used. There is also another method regarding the regularized variable selection method. it has become pretty popular recently and has achieved much success. And the regularized variable selection approach is the focus of today's talk. And in the past, there were several methods have been proposed, for instance, for linear mixed models and as well as for generalized linear mixed models. For linear mixed models, some proposed to use the adaptive lasso to select both fixed and random effects, and some proposed two-stage methods to separately select the fixed and random effects. And for generalized linear mixed models, some proposed to use the Monte Carlo EM algorithm to perform the regularized estimation, and some focused on the computational algorithm for fixed effect selection only or the random effect selection only. And recently, we and colleagues proposed the penalized quasi-likelihood method estimation with penalties imposed on both fixed and random coefficients, and they have demonstrated improved computational efficiency. And in this talk, in the simulation studies as well as some data analysis examples, we will use the Hui method as a comparator due to its better performance compared to the other existing methods. In general, these methods are computationally extensive and complicated, primarily due to the complexity in optimizing the objective function constructed from the marginal likelihood function of the observed data, which involves the integration with respect to the distribution of the random effects. So in this paper, we propose a regularized estimation procedure using the confidence distribution approach that can be implemented using existing standard software packages. And in the simulation study, I will also demonstrate some computational efficiency of our method. The seed idea of the confidence distribution can be traced back to Bayes and Fisher. The concept of confidence distribution and its applications have been developed extensively in recent years. In short, a confidence distribution can be viewed as a sample-dependent distribution function that can be used to estimate and provide all aspects of statistical inference for a parameter of interest. This useful feature has been applied under the context for meta-analysis and joint inference about a set of constraint parameters in survival analysis. Okay, so some notation in the model that we're considering. So consider a sample of n independent clusters, and we're using yi to denote the mi variate response vector. And xi denotes a vector of pf covariates. Pf represents the number of covariates, including the intercept. Okay. So xij represent a vector of pf covariates corresponding to the fixed effects. And zij is a vector of PR covariates corresponding to the random effects. Typically, zij is a subset of xij. And conditional on the random effects bi, we assume that yij's are following a distribution of exponential family with conditional mean mu ij depending on bi through a link function g, okay, that takes this form. And beta is the fixed effect correlation coefficient. And BI is assumed to follow the multivariate normal distribution with mean 0. And the variance covariance at this point is represented as an identity matrix of dimension PR by PR. And gamma, this capital gamma is important. It is a PR by PR Cholesky decomposition lower triangular matrix, depending on the parameter gamma, a small gamma, such that the big gamma times BI follows multivariate normal distribution with mean 0. And variance covariance matrix D. And the beta and the gamma are the parameters of interest in our proposed regularized estimation procedure. And consider finite dimensions of beta and gamma, and we use theta to denote the parameters involved in the model. We have beta, we have for fixed effects, gamma for the random effects, and some nuisance parameters as well. And typically, the model parameters theta can be estimated by maximizing the marginal likelihood of y by integrating out the random effects bi with respect to the distribution of bi. And the MOE denoted by theta hat can be shown that under some mild regularity conditions, the MLE theta hat is consistent and asymptotically normal. And this variance-covariance matrix can be consistently estimated by the inverse of the information. In the variable selection using the regularized approach, the objective functions constructed, typically constructed from the observed data likelihood function, okay, like this, plus some penalty terms. However, the challenges lies in the integral in the likelihood function generally does not have a closed form solution. So in typical GLM estimation, this casts some computational challenges. Now, under the penalized or the regularized estimation approach, with the addition of penalty terms, the computation in deriving the estimates as well as, for instance, the variance estimates can be much more challenging as well. So to ease the computation, we are motivated to take some advantage of the existing methods, software packages, and by making use of the asymptotic distribution of the MLE. And we applied the method of Sin et al. With regard to the confidence distribution to propose the objective function. Specifically, we're able to write down the confidence density for the parameter theta by this h of theta function. And note that the h of theta is a multivariate normal density, and it is a function, it is a quadratic function of theta. And then consider the following approximation. It can be shown that the log likelihood function can be approximated by the log h of theta, which is a quadratic function of theta. So as a result, we propose to construct the objective function as the quadratic function of the log confidence density plus the penalty terms, say n times k rho of beta associated for the fixed effects. And this is the penalty term for the random effects. And we define the proposed regularized estimator as, say, theta hat rho tau as the minimizer of this objective function q of theta. And then to facilitate statistical inference, such as the construction of 95% confidence intervals, we consider the adaptive lasso. For fixed effect selection, we considered the typical adaptive lasso penalty. For random effect selection, then we consider the group adaptive lasso to select the row vector of this big gamma matrix, such that if the row vector, say gamma m of this big gamma is not selected, the corresponding covariate will not be selected into the model. And for this methodology, we actually are following the rationale of Wen and colleagues, which was proposed in 2010. All right, and obviously our objective function is strictly convex. So under some mild regularity conditions, we're able to show that the proposed regularized estimator, say theta hat rho tau, satisfies the following statistical properties when the sample size n or the number of clusters n goes to infinity. And these properties are the estimation consistency, selection consistency, and the oracle property. And recall that the objective function, say Q, was built by the confidence distribution according to the joint asymptotic distribution of the MLE theta hat. We also proposed an alternative estimation based on the marginal asymptotic distributions of the MLE, say beta hat and gamma hat, according to the principle of confidence distribution to separately estimate beta and gamma. And specifically, we proposed the following separate objective functions, say QF of beta for fixed effect selection and QR of gamma for the random effect selections. And we defined the regularized estimators as, say, beta hat S rho as the minimizer for the QF of beta for fixed effect, and gamma hat as tau as the minimizer for the objective function QR of gamma for random effect selection. And similarly, it can be shown that the proposed estimators of each of those would have the properties of estimation consistency, selection consistency, and oracle properties. And this slide shows the properties for the beta estimator. And the next one shows the properties for the gamma estimator for the random effect selection. And to implement, especially to perform the optimization, to optimize the objective function, we propose to follow the method of Jan and Liu by rewriting the objective function, for instance, the Q function into this quadratic form in terms of theta. Okay. And this is turning the objective function into a typical convex optimization problem so that we are able to implement the standard software packages, for instance, the R package, GLMNet, GLIMNet, or the gglasso for group adaptive variable selection approach. And then to determine the tuning parameter rho and tau, we consider to minimize the BIC defined in this way. And a similar principle of the optimization and determination of tuning parameters for the separation approach using QF of beta and QR of gamma can be similarly derived and applied. All right, and then due to the time sake, I'll jump right off to the simulation studies. And in here, I only included the results for linear mixed models and random effects logistic regression models. We actually have some results for random effects Poisson models. And in both scenarios, the true value for beta 0, the true values for the fixed effects covariates include, say, 6 ones and 0 and 10 zeros. In other words, we included 15 covariates plus the intercept. And 5 of the covariates are quote unquote the true covariates, and the remaining are the nuisance or the noise variables. And for Cholesky decomposition lower triangular matrix for the big gamma, for the true random effect covariance matrix is given by these two choices, one for the linear mixed model and the other for the random effects logistic regression model. And under our specification or the choices for this gamma, it means that we have 2 true covariates and 1 random intercept with regard to the random effects specification. And for all elements of Xij, except for the intercept, they're generated from standard normal. And the first 4 elements of Zij equal the first 4 elements of Xij, including the intercept. And we're using the notation CDJ represent the confidence distribution joint estimation approach, and CDS represents the proposed confidence distribution separate estimation method. And we listed the results from our PQL methods proposed by Hui et al. For its better performance than the other existing proposed methods. And in terms of the assessment, we are assessing the bias, empirical variance, coverage probability of the 95% confidence intervals, as well as the percentage of selection based on 1,000 simulation rounds in each scenario. This is the result for the linear mixed model, especially for the fixed effect selection. So basically for the CDJ and CDS, for the proposed methods, when the number of clusters is 60 and the cluster size is 10, generally the estimators are pretty close to the true values, except for the intercept, as well as the 2 covariate, the coefficients of the 2 covariates that are associated with the random effects. Under the linear regression, linear mixed models, actually, the way that we specify the Cholesky's matrix, the values corresponding to the random intercept as well as the covariates actually is pretty sizable. You know, for instance, if you multiply these numbers by 2, you can see some magnitude. The random effects actually, the variance covariance is 9, some pretty high, large numbers. And however, if we increase the samples, the number of clusters from 60 to 500, we can see that the bias actually is improved a lot. Okay, the bias has become a lot less. And in terms of the empirical standard errors, obviously and expectedly, they decreased with the sample size or the number of clusters. The coverage probability of the 95% confidence interval actually is close, but somewhat under the nominal levels. And in terms of the percentage of selection, our selection rate actually is pretty good, either for the joint selection or the separate selection. And compared to our comparators, for instance, the RPQR approach, our results are pretty similar. And I also wanted to emphasize that the CD separate selection approach seems to perform better than the CD joint selection approach. For linear mixed model analysis with regard to the random effect selection, the results are similar. However, I wanted to put an emphasis on the computational time. When the number of cluster is small, say like 60, the computational time of our methods as well as the RPQR method, they're pretty comparable. They're pretty fast. However, when the sample size or the number of clusters increases to 500, you can see that some advantage of our methodology, our proposed methods in terms of the computational time. So our method actually is a lot faster than the RPQR approach. And for the random effects logistic regression, for the fixed effect selection, we are seeing some underestimates of the estimate in the CDJ approach, and the CDS approach, the separation method actually outperformed the joint selection approach. And this CDS approach also performs better than the RPQL approach. And in terms of the bias and the empirical standard errors, as well as the coverage probability and percentage of selection, their performance actually are greatly improved when the number of clusters increase from 200 to 500. Okay. And in terms of the computational method, our method seems to be a lot more computational efficient than the comparator RPQL.
Shuvan, this is Jaya. You have 1 more minute.
Oh, I have 1 more minute. Okay, then I probably will just jump right off to the data example. So going back to the data example, we are using the random effects logistic regression analysis with calcification as the dependent variable. And we only presented the proposed CDS method for people to get a feel. And we also threw in 2 randomly generated noise variables just to see if they were falsely selected by our approach. And this is the result. So only 8 years from radiation therapy, African Americans and HER2 positive and bilateral diseases are selected for the fixed effects. And in terms of the quote unquote, the statistical significance, except for the bilateral disease, the others all came out statistically significant. And luckily, the 2 noises variables were not selected. And then for the random effects, our approach, the CDS approach, actually picked up age, suggesting that age has some heterogeneous effect on the outcome. And the noises variables were not selected either. All right, some discussion. In this talk, we proposed some regularized estimation approach based on the confidence distribution of the MLE and adaptive lasso. And the proposed estimators have some estimation consistency, selection consistency, and oracle properties. We have shown it in theory as well as demonstrated them in the simulation studies. And we also have demonstrated some computational efficiency in the simulation study as well. And in terms of the ongoing and future work, currently I and some colleagues have been applying and extending our method to the framework of generalized estimating question approach for correlated outcome data and other applications. We're also looking into the extension of the methodology to more complicated models at this moment. So I'll stop my talk here, and thank you.
Thanks a lot, Shivan. You can stop sharing the screen so you can see everyone too.
Thank you.
Well, let's thank Dr. Shivan Lu for a nice description of variable selection and joint modeling. Thank you, Shivan. We are definitely out of time, encroaching into the next session, but I want to ask the audience if they have any quick question for Dr. Lu or Dr. Liang Yuan Hu at this time. If not, I would like to once again thank all our speakers, Dr. Pamela Strickland, Dr. Liang Yuan Hu, and Dr. Sharon Shivan Lu for joining us this morning in New Jersey, evening in India, for sharing their works with us. And I also want to once again thank Dr. Satish Kumar for giving us this opportunity for the session. And perhaps I will reach out to Pam, Liang Yuan, and Shivan to see if you have any references that I can share with Dr. Satish Kumar for distributing to his students as well, so they can benefit from learning more about your works on categorical data analyses and failure time data. So I will wrap up the session at this time and hand over to Dr. Satish Kumar before we begin the next session.
Thank you, Professor Jaya, for your nice organizing of this session. And especially at this moment, it is my pleasure to extend our gratitude to Professor Liang Yuan Hu, Pamela Strickland, and Shu and Lu for their wonderful presentations. In fact, we hope to have your association and collaborations in future also. And you are all welcome to Kerala, if possible, in the next conferences.
Yes, let's hope for an in-person conference in the future where we can all be together in person.
Yeah. Now, once again, thanking you, professors, in the session, all the speakers, and also Professor Jaya. I hand over the mic to Professor Jaya to carry over the next session. In fact, this session, the advances in statistical methods and their applications. In fact, it was a very successful session. Let us give a big clap to each one of the speakers.
And thank you, Dr. Satish. I also want to thank Gokul for his support of this session earlier. And we now wrap up this session and we will move on to the next session, which will be chaired by Dr. Shivan Lu. This next session will showcase applications of quantitative methods in different areas of public health. And as I mentioned just now, it will be chaired by Dr. Shivan Lu, who was also a speaker in the previous session. Dr. Shivan Lu is an associate professor of.
Welcome, Professor Shivan Lu, to the audience. In fact, you are we invite you to chair Professor Shivan Lu. In fact, already the Professor Jaya has detailed about her. So we hope no need to further describe. Once again, please carry over this session, Professor Gogul will help you in any way if needed, any type of. And we are.
Take it away, Shivan. Thank you, Dr. Kumar.
Welcome, please. Let us.
Thank you so much. Should I? Okay. So welcome to the session of quantitative applications in public health. Today we have three excellent speakers. The first one is Dr. Ayana April Saunders. Dr. Ayana April Saunders is an instructor in the Department of Biostatistics and Epidemiology at Rutgers School of Public Health. She earned her doctoral degree from Columbia Melbourne School of Public Health. She has also completed a postdoctoral fellowship in the Department of Medicine and Department of Epidemiology and Population Health at Albert Einstein College of Medicine. And Dr. April Saunders' research focuses on understanding the impact of social determinants of health inequities, and early life stress on cardiometabolic and cardiovascular disease outcomes across the life course in minority and immigrant populations. And as a researcher with a particular interest in developing interventions among adolescents and young adults, Dr. April Saunders' work seeks to identify risk and protective modifiable factors that influence trajectories of cardiovascular and cardiometabolic disease among underrepresented minoritized groups as well. And our second speaker is Dr. Varsin Khosrow-Kavar. Dr. Varsin Khosrow-Kavar is an epidemiologist with a focus on applying rigorous study designs and methods to assess benefits and harms of therapeutics among patients who receive care in clinical practice. He completed his doctoral degree in epidemiology at McGill University and a postdoctoral fellowship at Brigham and Women's Hospital and Harvard Medical School. As a new investigator at Rutgers School of Public Health and the Institute for Health, Healthcare Policy and Aging Research, Dr. Khosrow-Kavar plans to examine the benefits and harms of cancer drugs among patients who are underrepresented in clinical trials, including patients with multi-morbidity, frail patients, older patients, and minorities. And our third speaker is Dr. Noor Zinamari. Dr. Noor Zinamari is also an assistant professor of medicine at Rutgers Cancer Institute of New Jersey. Particularly, her position is with the section of cancer epidemiology and health outcomes. Before joining Rutgers, Dr. Zinamari was a TL1 postdoctoral fellow focused on precision medicine at Columbia University's Irving Institute for Clinical and Translational Research. And she's also an NCI-funded T32 postdoctoral research scientist in molecular and cancer epidemiology. The overarching aim of her research is to translate epidemiologic findings into clinical cares through more accurate risk assessment and to optimize risk-reducing strategies for outcomes after a cancer diagnosis. Specifically, she's interested in understanding the role of genetics, the environment, lifestyle factors, and their interplay on breast cancer etiology and prognosis. So maybe we will start with Dr. Ayana April Saunders to present her work. So Ayana, I'm turning the presentation over to you.
Great, thank you so much, and thank you for the introduction, Dr. Liu. Let me just get my presentation going.
You can click the upward arrow, Ayana.
Yes, actually, I don't use Google Meet too much, so I'm asked to pop back in. Is it okay if we start with another person then? Because I have to change my settings to allow me to share my screen.
Okay,
apologies
sure,
for that.
no problem.
Yeah, sorry.
So,
I'll be back in a moment.
Shuan, please.
Okay, so perhaps we could start with Dr. Farsi. Yeah.
If needed, we can share from here. No problem.
Oh, actually, you know what? I think it might be coming up now. Okay. So let me pick the window. Let me start it.
Anyway, you try, Dr. Anna.
Yes. Yeah, I'm gonna have to start. I have to restart. I have to pop back in. I apologize. So if you could go start with maybe Nora Farzin.
Speak up with the button. So maybe I can try sharing my screen here. Can you share PowerPoint on this or not so much?
I think when you click on the upward arrow, a dialog box will come. And if you click on a window, you can share your presentation through that.
Farzan, if you would like me to start, I don't mind starting because I think you just click on window. Would you like me to start?
Yeah, I have, you can share your entire screen, but I don't see
Yeah, it's
PowerPoint.
coming now. It's coming.
Oh, Ayana started. Oh, we can't hear you. You're on mute.
Yes, I had to restart my browser to get it going. So apologies for that. But let me see if I could just go ahead and start the presentation. There we go. Are you able to see, or are you seeing the presentation view?
Yeah,
yes.
Your presentation is fine. We can see both your presentation and you. You can.
Are you able to see the notes as well, or just the screen, just the slides?
No, just the presentation.
Okay, very good. All right, so I'll get started here. So thank you and good day, everyone. Sorry for the delay. So I'll just jump right into it because I have plenty of content to share, but I'll be reviewing my findings looking at patterns of early life adversity and associations with cardiometabolic health and pre-heart failure among Hispanic Latinos in the midlife. And so I just want to start with some, a little background on heart failure and some of the important items that come up in this literature. So heart failure is a clinical condition where the heart is failing to pump as efficiently as it should in order to supply the body with oxygen and nutrients it needs. An important term in this literature is a measure of cardiac function, so ejection fraction, and this refers to how well the left and right ventricles pump blood. And there are two general types of heart failure. There's heart failure with reduced ejection fraction, and it's also referred to as systolic dysfunction. And this is where the heart ventricles aren't pumping as well as it should to have the blood go to the body and function as well as it should. And the other type of heart failure is heart failure with preserved ejection fraction, also called diastolic dysfunction. And here the heart is pumping and contracting as it should, but not filling efficiently. And so it doesn't send blood to the body to meet the body's needs. And for each of these conditions, about 50% of patients are diagnosed with either if they're diagnosed with heart failure. So another important detail here is that recently the definition for heart failure was redefined, and it really emphasizes the symptomatic nature of heart failure as a clinical syndrome. Importantly, there's additional stage that was added that is relevant to this work here, stage B, which represents pre-heart failure and indicates in patients who are without current or prior symptoms or signs of heart failure, but have one of the following conditions, either structural heart disease, abnormal cardiac function, or elevated natriuretic peptides. And this was an important addition because previously this group is, kind of vaguely described as having subclinical heart failure, but now we could get a little bit more classification definition of who these individuals might be. And importantly, this reclassification is helpful for providing more precise communication and description of heart failure, its health and disease for research purposes. So looking at the epidemiology of heart failure, so heart failure is a major source of morbidity and mortality here in the US and is the leading cause of hospitalization and cardiovascular conditions. It is, we do see that the burden of heart failure is likely to increase for factors like advancing age of the US population, earlier age at onset of heart failure, and improved treatment and survival from cardiovascular disease. Importantly, echocardiography or the heart ultrasounds are essential really for the management of heart failure and in determining its etiology. So we can look at these images and understand from cardiac morphology where heart failure might have been caused due to factors like hypertension and diabetes. Importantly, we know that heart failure is prevalent among the elderly, but it does vary by sex, race, and ethnicity. For example, findings from the echocardiographic study of Latinos, the investigators found that a high prevalence of diastolic dysfunction and left ventricular stiffness existed in the cohort, and this suggested that Hispanic Latinos may be at a high risk for heart failure with preserved ejection fraction. Now, epidemiological evidence does point to some stressful experiences in early life, referred to as early life adversities or childhood adversities, as really setting the stage for poorer health across the life course. Early life adversities includes factors like household family dysfunction, child maltreatment, but also factors like violence in and outside the household, and things like bullying and peer victimization that exist when an individual is under the age of 18 years of age. And we know that childhood adversities are highly prevalent here in the US and really globally. And in this population-based study in the US, we see that over 60% of adults reported having at least one childhood adversity during their childhood years, and nearly 40% reported having two or more. Childhood adversities are also highly prevalent among those of racial and ethnic minority groups, those with lower income, and immigrants. And we can see here that even as income and other factors increase, Black and Hispanic Latino children had a higher prevalence of childhood adversity compared to their non-Hispanic white counterparts. So trying to understand some of the links between early life adversity and heart failure risk, there's a very rich and long history of evidence showing early life adversities being associated with known cardiometabolic diseases and cardiovascular risk factors like BMI, diabetes, hypertension, vascular dysfunction, and inflammation. But the pathways linking early life adversity and risk for heart failure are not really well elucidated, but they do share common risk factors, or pretty much the consequences of early life adversity are common risk factors for heart failure. But national policy statements like from the American Heart Association and other agencies do highlight childhood as this critical period for preventing cardiovascular disease across the life course. And with this evidence, seeing how prevalent heart childhood adversities is and increasing likelihood of heart failure as population ages, it's important to understand and examine the early life adversity constructs and to clarify the causal mechanism, as well as identifying opportunities for intervention and prevention, and particularly in our high-risk groups. So some of the approaches for measuring early life adversity really have evolved over the years. Historically, folks have taken each individual item and looked at it in association with particular outcomes, or some did a summation or accumulation of the early life adversity exposures as a way to operationalize it. But we can understand this is a very unidimensional, single level kind of assessment of early life adversities. And nowadays, we understand that early life adversity is this multidimensional construct. There's a number of types, there's differences in the severity and frequency, as well as the chronicity. And the types of early adversity don't exist on their own. They tend to happen or co-occur commonly for folks who are exposed to adversities. So there's growing belief that specific distinct early life adversity profiles may be identifiable among individuals who are exposed to adversities, and particularly more complex profiles might be especially deleterious to health in later life. And so we need some more advanced methodological approaches to really expand our knowledge of how early life adversities affects health outcomes, as well as inform our research practices. So as we all know, there are many different analytic approaches that we can use to answer our research question. We're familiar with the variable-centered approach to test the association between variables under the assumption that the study sample is homogeneous, and they're really best suited for questions pertaining to the importance of predictor variables and explain the variance in the outcomes. And these are methods that we're familiar with, like correlation and regression and structural equation modeling. But there are also approaches that identify groups of individuals who share certain attributes or relationships among attributes. And these approaches are predicted on the assumption that the study sample is heterogeneous rather than homogeneous with respect to how they predict or the predictors operate on the outcome. And they're really best suited for addressing questions that pertain to group differences in the patterns and or development. And some methods for this include latent class analysis and latent profile analysis. So here, it's just a classic model of the latent class profiles, where depending on how your indicators are modeled, either continuous or categorical, the latent class analysis and profile models are used to assess categorical latent variables called latent classes that stem down here. And these latent classes are factors that are made up of within-person patterns of profiles, and they're considered to be multidimensional because the items that help inform what variables or what goes into each class are thought to be multidimensional and have many different domains. So for this study, we use latent class analysis to assess the latent classes built from our early life diversity items. So they exist here in box X. And once identifying the latent class, we can understand specific early life diversity profiles, which are then used to test association, assess the association between the profiles and our distal outcome, which would be cardiometabolic disease and pre-heart failure measures. And this area of research looking at early life diversity and latent class studies is small and growing. There are several studies that came out over the last 10 years or so that I've identified, specifically 3 to 4 latent classes, such as physical and emotional abuse co-occurring and physical and sexual abuse co-occurring. They also found differences in the profiles by sex, which does informed by previous literature from early life diversity, where we see a greater prevalence of reported adversities in females compared to males. And in this work, they've studied the association of the profiles with behavioral and mental health outcomes, but none have really assessed these association of the early life profiles with cardiovascular endpoints. So given the evidence to date, this study sought to examine association between early life diversity profiles and cardiometabolic disease and pre-heart failure among Hispanic Latino adults from the Hispanic Community Health Study, Study of Latinos. We have 2 main aims here: is to identify first the distinct profiles of early life diversity for Hispanic Latino adults, where we hypothesize that the profiles will vary by sex, males and females, and determine, in our second aim, the association between early life diversity profiles and cardiometabolic disease and pre-heart failure in adults, where we hypothesize that higher diversity and more complex profiles will have a greater likelihood of cardiometabolic disease and pre-heart failure. And some of the implications here could be identifying target interventions for groups to make more significant impact to lowering the burden of clinical heart failure in this population. So moving on to the measures and approaches, the data for this study comes from the Hispanic Community Health Study, Study of Latinos, and this is a multi-center population-based study of Hispanic Latino participants, over 16,000 participants who are 18 to 74 years at baseline. And the study is continuing as longitudinal study and examines chronic disease prevalence, incidence, risk, and protective factors in Hispanic and Latino adults of diverse backgrounds. The study also had a number of ancillary studies, one being the social cultural ancillary study that is a subset of the parent study. They included a little over 5,300 participants after about 9 months after their baseline interview. And this ancillary study explores socioeconomic, cultural, and psychosocial influences of health in the adults, and included measures of early life diversity, which I'll get to in a moment. We also included measures from the echocardiographic study of Latinos, another ancillary study of SOUL, which included a subset, about 1,800 participants. Visit 1 baseline. There was also a follow-up of this study in 2015 and 2018 that included 1,643 participants. And its focus was to assess the cardiac structure and functioning of the participants using transthoracic echocardiography in adults who are 45 and older. So in capturing the study sample, we included those who had visit 1 and visit 2 echoes, and those who are also participants in the social cultural ancillary study to have a final sample that included those who had valid data with echoes, the adversity measures, and that gave us a final sample of 1,143 participants, and 500 participants were mainly excluded because they weren't, they participated in EchoSO, but not also in this social cultural ancillary study. So for our outcome measures, the cardiometabolic and cardiovascular disease measures included obesity, hypertension, diabetes, mellitus, hypercholesterolemia, measure of metabolic syndrome per the International Diabetes Federation definition, prevalent cardiovascular health disease without engine and heart failure. And these were all measured based on clinical assessment as well as self-report. Our measure of pre-heart failure and its domains are based on the definition that I described earlier, where pre-heart failure or stage B is any patient with any evidence of structural heart disease or abnormal cardiac functioning. They also could not have heart failure. And these were based on 3 domains of pre-heart failure. So left ventricular remodeling, left ventricular systolic dysfunction, and left ventricular diastolic dysfunction with the specific echo parameters described below. And so we had a primary outcome, which was here pre-heart failure, and then secondary outcomes of the domains described here. For our exposure measure, we looked at early life adversity that was measured from the childhood stress exposure from the social cultural ancillary study. And these included measures of physical, sexual, and verbal abuse, physical and emotional neglect, having family members who struggle with mental illness or depression, addiction to alcohol or other substances, or were imprisoned during the individual's childhood, also witnessing mother's abuse, such as domestic violence, and losing a parent to separation, divorce, or other reason. And participants were basically asked when they were growing up during their first 18 years, a series of questions, a sample here. Our assessment of physical neglect was based on the question, did you often or very often feel like you didn't have enough to eat, have to wear dirty clothes, or have no one to protect you, or your parents were too drunk or high to take care of you, or take you to the doctor if needed? And for all of the items, the 10 items, the response values were 1, yes, or 0, no. Our covariates included factors such as age, childhood socioeconomic hardships, so that was any time during childhood when the caregiver couldn't pay for basic needs, nativity status, and self-identified Hispanic Latino background, and modifier here was sex, coded as male and female. And for the analytic plan, we present descriptive statistics on baseline characteristics of the joint, echo, soul, and social cultural ancillary participants with mean and count statistics presented by sex. Also present the results from the latent class analysis, identifying early life adversity profiles. And then we use multivariable logistic regression models to estimate associations between the best fitted identified early life adversity profiles and each of the measures of cardiometabolic factors and pre-heart failure at baseline or visit 1 in the overall sample, as well as by sex and adjusted for covariates. And analyses use survey ways to adjust for sampling probability and missing data. And all the analyses were conducted in SAS except for the latent class analysis, which was conducted using M+. So turning to the results, here in table 1, just presenting the basic study baseline characteristics. So just to point out a few, the average age was about 56 years, the majority were female, about 61% had health insurance, 33% had less than a high school education, and the majority, or 71%, had an annual household income under $30,000 US. Most of the Hispanic Latino background was made up from Cuban and Mexican Americans, and majority were foreign born, and BMI on average was 30.3 kilograms per meter squared. Looking here at figure 1, it shows the prevalence of the early life adversities indoors, where we could see that 75% of the cohort reported having at least one childhood or early life adversity, and almost 40% experienced 3 or more adversities. So taking a look at the distribution of the early life adversities indoors, we did see differences by sex, with females reporting a greater prevalence of early life adversity and specific adversities such as emotional abuse, sexual abuse, emotional neglect, and mother domestic violence, and household substance was reported by females more so than their male counterparts. In terms of our cardiometabolic and pre-heart failure characteristics, we saw that overall these characteristics were highly prevalent. So obesity, hypertension, diabetes, and hypercholesterolemia were all prevalent with percentages ranging from 26.7% for diabetes and 50 to 51.4% for hypercholesterolemia. Metabolic syndrome was highly prevalent in almost 50% of the cohort, and just under 4% had heart failure. 43.7% were identified as having pre-heart failure, with left ventricular diastolic dysfunction being the most prevalent trait of pre-heart failure in the group. And we did see differences by sex for these characteristics. So females were more likely to have obesity than males, but males were more likely to have high cholesterol, pre-heart failure, and left ventricular systolic dysfunction.
Rihanna,
So here,
I'm sorry, you have
yes.
1 more minute.
Oh,
You have
one
one
more
more
minute.
minute.
Okay, so sorry about that. So I'll just I won't present this, but just show that we did identify 4 classes for the overall sample, 3 for the females and 3 for the males. And this just presents the figures showing the probability of answering yes. And we identified generally 3 to 4 types, so low adversity, household dysfunction, high adversity, and mixed adversity. So those are males and females. And to show the results of our multivariable logistic regression, not just for age, childhood economic hardship, nativity status, and Hispanic Latino background. The overall sample, we show that for each of the profiles compared to low adversity, obesity was, they were each associated with increased odds of obesity. In females, we also saw the same, that each of the profiles were associated with obesity, but not with any other of the outcomes of interest. And then for males, hypercholesterolemia was, or household dysfunction was associated with lower odds of hypercholesterolemia, and no other associations were observed. And just to summarize the findings, basically seeing that U.S. Hispanic Latino females were more likely to experience early life adversity and more complex profiles than males. We saw that more severe history or complex histories of early life adversity were associated with some of the cardiometabolic factors, but also noting that, we saw this inverse association with males for hypercholesterolemia, and then no association with pre-heart failure, which may be due to older age and lower reporting of early life adversities, and then just having older age and being associated with these outcomes more often. Also, maybe resilience is a factor that plays a role there. There are potential clinical implications here to inform interventions and understand better subgroup differences in these outcomes. And we provided some novel evidence on early life adversity co-occurrence with cardiovascular and metabolic health. So just want to acknowledge my co-authors and our colleagues at the Hispanic Community Health Study. And I will stop there, and thank you for your time and attention.
Thank you, Ayana. This is excellent. We have time for one question. So wondering if we have any students, colleagues who have questions for Ayana's presentation. Or maybe we could save some of the questions at the end of the session, and then we just move on for the time's sake. Maybe right now I can present our next speaker, Dr. Varzin Khosrow. So Dr. Khosrow, the screen is all yours.
Great, thank you. I'm still having a bit of a hard time finding PowerPoint on the application window for some reason.
So is your window popping up, Varzin? Yeah.
Say again?
When you press to share, there's another window pop up showing you your different screens.
Yeah, I have a window, and it's just for the application window. It's just showing Chrome and a folder basically. So it's not really showing my.
Then click on that window, and that share will be active, isn't it?
Okay. Let me try this.
A blue color.
Okay.
Yep. Now it is.
Okay, there you go.
Okay, so you're seeing this here?
Now it is coming. Now we can go to the slides.
Can you see my PowerPoint here?
Yeah, you can open it. You can just.
We can see your screen, but not your presentation, not your slides.
Okay, how about now?
Still your screen.
Yeah, let me see here.
You can choose your slides.
It doesn't give me that option for some reason.
If it is already opened, you can just click on make it. First you open your slides and minimize it, or
Yeah, my slides are open.
Okay. Now to move to the slides, just to move to the slides.
Yeah, just start sharing the PowerPoint, and I think it might pop up.
Select the slides.
Yeah, it's not sharing my slides for some reason. Sorry. Maybe I'll let Noor to go ahead, and I can come back in and see what the problem is.
Yeah, I don't mind going ahead if that's.
I can also send Jaya my slides as well in case I have problems. You can kind of share my slides.
Sure. Okay.
Okay, great. Thank you.
All right. So, yeah, thank you. Now we're turning the screen to Dr. Zinamar. Yeah, please go ahead, Noor, when you're ready. Go ahead and start.
Yeah, and you can, let me see if I present. Can you see my slides?
Yes, perfectly. This is good.
Perfect. So thank you very much for inviting me today. I'm really excited to talk about the role of polygenic risk scores in breast cancer risk assessment. So I wanted to give a brief outline of my talk. I'll just go over some breast cancer epidemiology, go over some of the risk factors for breast cancer just to familiarize ourselves, and then get into the genetics of it, the underlying genetic risk for breast cancer, and then how polygenic risk scores play a role in risk prediction modeling. So to start with, breast cancer is the most commonly diagnosed cancer in women worldwide. You can see it here represented on the world map in pink, and it counts for 24% of all new cancer diagnoses in women worldwide. And this is a map from WHO using Globocon data, showing the top cancer per country. And then in terms of mortality, it's the most common cause of cancer death for women worldwide. And you can see it from the map that it's the top cancer death in 103 countries worldwide. And this is shown again in pink. For us in the US, it's blue for lung cancer, but it's the second leading cause of cancer death here in the US. And just to briefly get into risk factors, these are the strongest risk factors for breast cancer. You can see here the pathogenic genetic variations in the BRCA1 and 2 genes. Breast cancer density, mammographic density, some of the high proliferative benign breast disease, a strong family history, and of course, increasing age. And then next, we have a lot of reproductive factors, including early age at menarche, parity, breastfeeding, and then postmenopausal obesity, alcohol consumption, and cigarette smoking. These are more related to lifestyle risk factors. And then finally, there's some protective factors, if you will, that have been shown to reduce the risk, including physical activity and some chemoprevention agents, such as tamoxifen. Not listed here is a raloxifene. And these are all things in the box here that can be modified. And then for prognosis, we know it's a little less, but age and the tumor characteristics are really what drive your risk for survival and then recurrence. But also obesity and smoking has been shown to increase risk of adverse outcomes after a diagnosis. And then, of course, the cancer treatment, physical activity, and again, these are just to focus on some of the modifiable factors are the ones here in the box. And so in terms of what is included right now in cancer risk models, it really varies on what factors are included. I have here listed colon cancer because it's also a very strong, one of the top 3 cancers worldwide. But just to contrast, the factors really vary. And the most of the discrimination of these risk models is relatively modest and increasingly increasingly models are including this polygenic component. So for breast, a lot of the models are both based on a first degree family history. There are some models that are based on multi-generational pedigrees, and then there's some models that really don't incorporate a lot of family history. Some models incorporate these high penetrance mutations that I alluded to earlier, BRCA1 and 2, and then some models also include non-genetic factors, including some of the lifestyle factors that I talked about, age, of course, and then reproductive factors. And when I say modest in range, I'm really talking about like a 60 to 65% discrimination. If you're interested in learning more about this is an older paper now, but the different models, I thought this was a really good review about, it gave a good comprehensive overview of some of the models and their validation. And so if we look at the landscape of breast cancer genetic susceptibility, this is a kind of a classic slide, but you can see that, the rare, I don't know if you can see my mouse, but on the far left, the rare high penetrance, mutations, these are the ones that confer some of the highest relative risk. And then we have moderate penetrance mutations, such as those in the ATM, the CHEK2, the PALB2 genes, and those really are, conferring a relative risk of between 4 to around twofold. But the focus that I'd want of today's talk is on these low penetrance alleles. So these are common, mostly single nucleotide polymorphisms, and they individually confer a very modest risk for breast cancer. I wanted to just go over really quickly what a genome-wide association study is, because these have really revolutionized how we look at, how we look at genomic risk prediction. And this is a figure from a great primer for GWAS studies. And so basically, it's thousands of individuals. We genotype them. And then we basically just look at, the association with a certain characteristic or disease. In this situation, it would be breast cancer. And then now we're kind of in the post-GWAS stage where functional annotation of, identified, loci or even the polygenic risk scores are is really just blowing up. So there's that. And then in a really simplified overlook of what a polygenic risk score is, it's a score that predicts disease risk, and it's really calculated as the weighted sum of risk alleles with weights. These betas here, they're specified by the association coefficients that we get from a GWAS. So really the PRSs just summarize very efficiently the combined effects of these genetic variants on disease risk. They've been a really hot topic in the past 5 years, and there's really rapidly evolving methods that incorporate a lot of different things, including the underlying linkage disequilibrium patterns and other considerations. I'll touch later on in my talk, but there's also been a lot of development in the past couple of years for trans ancestry polygenic risk scores. And the great thing about polygenic risk scores is they can really define lifetime trajectories because this is the germline genetic variation. So they have a lot of promise in terms of risk prediction for diseases later on in life. And in terms of breast cancer, I think that the most commonly used breast cancer polygenic risk score now is based on 313 variants. And this was developed using the Breast Cancer Association Consortium, mostly in or all in European ancestry women. And it's been associated, you can see in the figure on the bottom left, with a 4-fold increase in breast cancer risk for those in the highest 1% compared to those at average risk. And it's been observed for women with and without a family history, so it's independent family history. And then at the bottom right, you can see that the lifetime risk to age 80 by quantiles of PRS. In the figure on the right, you see that the PRS stratifies risk in both women with and without a family history of breast cancer. So it's really, it holds great promise for improving our risk prediction. The red line shows the 2.6% risk threshold here, corresponding to the mean risk for age 47 years. And the average 10-year absolute risk of a breast cancer for a 47-year-old woman in the general population is 2.6%. However, 19% of the women with the highest percent of PRS will attain this level of risk by age 40 years. So it can really change how we think about screening. So, you know, PRS has several limitations. Last year, a mentor of mine and I published kind of like a opinion piece about in cases of precision medicine, examining the role of PRSs in breast cancer risk. And while this is not an exhaustive list, some of the things that we highlighted were that PRSs may actually worsen existing health disparities, as many have been developed in women of European ancestry. So their clinical utility and performance in other women is unclear. Although there are really great initiatives right now to improve this in other populations, including Latina, South Asian ancestry women, and African ancestry women. And we still need to examine the PRS's clinical utility in clinical trials. And in fact, there are several ongoing trials underway doing just that. And those are going to be really important for answering questions about utility, but also implementation of the PRSs into clinical practice. And finally, it's important to note that the PRSs can't stand alone. So even when they're ready for prime time, we're only going to be using them as a complement to existing models, the models that I alluded to earlier. And strategies need to be considered along with everything else at our disposal. So yes. And then I wanted to highlight one of the studies that I conducted last year, really just trying to understand how previously developed breast cancer polygenic risk scores perform in a clinical setting for women of different ancestries. In our study, we focused on 3 ancestries: European, African, and Latina ancestries. We actually also, we didn't end up publishing it, but we also tried to look at Asian ancestries, and we just didn't have enough power. But for this cohort study, we used the eMERGE network, which is electronic medical records and genomic records, and it's included over 39,000 women from 9 contributing medical centers in the US that had EMR linked to genotype data. It was a really cool study because we identified breast cancer cases and controls through a validated EMR phenotyping algorithm. So I worked with the Department of Biomedical Informatics at Columbia to do this. And I won't go over every single part of the study for the sake of time, but briefly we examined 7 different PRSs, including 3 developed in European ancestry women, 2 developed or adopted to Latina women, and 2 developed or adopted to African ancestry women. And you can see the original PRSs, sources listed here. And these are I just want to highlight the main findings, which is that the PRSs derived from women with European ancestry for breast cancer, they generalize well for European, Latina, and African ancestry, although the effect sizes for women with African ancestry were smaller. We think that this is likely due to differences in risk allele frequencies and different linkage disequilibrium patterns in these populations compared to the European ancestry populations. So the European ancestry women here, you see them, they're kind of in this light blue, and we saw, depending on the PRSs that we're looking at, ORs ranging from 1.36 to 1.46. There was really attenuated odds ratios when we looked at African ancestry and Latina ancestry women. And so in summary, they generalized well, although there are, differences across ancestries, and it really highlighted the new need to improve representation of diverse population groups, particularly in our study, women with African ancestry and genomic research cohorts. But certainly there are other, populations of different ancestries that we really need to be focusing on. There was an editorial written about our paper, and I pulled out a quote because I thought it was great. So it says the work simultaneously highlights pervasive race-based inequities in healthcare, and a major criticism of the PRS is that they're disproportionately applicable to patients with European ancestry and are insufficiently vetted and developed in other populations. So shifting gears here, I just wanted to go over briefly the ongoing clinical trials of PRSs that are trying to answer some of these unknowns that I referred to earlier. So the first one is the WISDOM study, and this is really focused on how do we better inform breast cancer screening decisions. The hypothesis is that personalized breast cancer screening recommendations based on individual risk estimates will be at least as safe and less morbid than the annual age-based screening, and that it'll improve breast cancer prevention, and that hopefully it'll be accepted by women and preferred over the standard annual screening that we have here.
Noor,
So-
you have 3 more minutes.
Okay. So then I won't go into the study design, but I'll highlight one other study, which is the MyPEBS trial. And this is similar to WISDOM. This is an EU-funded clinical study, and it includes 5 different countries. Again, focused on European ancestry women, but it will answer similarly this risk-based cancer screening strategy using a clinical risk score combined with a PRS compared to the standard screening, which is according to the national guidelines in each participating country. Won't go into here. So the last thing I wanted to highlight was that the majority of polygenic risk scores for breast cancer have been focused on risk. And what about outcomes after breast cancer? And this is something that I'm really very interested in. And this is the topic of my research right now. I have a grant funded through the National Cancer Institute that will investigate if the existing polygenic risk scores for risk of breast cancer improve prediction of outcomes after a breast cancer. And these include overall survival, breast cancer specific survival, and second breast cancer events, such as a recurrence. And we're going to examine the impact of adding a PRS to existing clinical markers, that are used, such as, receptor status, and other prognostic tools that incorporate grade, size, things like that. And I'm very lucky because I get to use 2 complementary resources, including a cohort-based study of, or a family-based cohort study of breast cancer survivors, as well as a cohort of Black breast cancer survivors based here in New Jersey. So that's what I'm currently working on. Finally, I wanted to acknowledge all of my wonderful colleagues that I've worked with on the eMERGE study, as well as my currently funded NCI study. And so thank you. And here's my email if you've any other questions. And I will stop sharing.
Thank you so much. This is excellent. Wondering if there are any questions? Or for the time's sake, so Varsan, wondering if you are ready to present?
I'm ready. Seems like I'm having still the same issue that it's not recognizing PowerPoint on my computer for some reason. So perhaps Jaya, you could share yours, and I could just go through the slides.
Yeah, let me try to open it in a moment for you.
Thank you.
Okay. Are you able to see my screen?
Not yet. Yes, it's popping up.
And let me go to the presentation mode.
Wonderful, thank you.
Are you able to? Okay, so let me mute myself and.
Great, thank you so much.
And you can say next screen, and I will move to the next.
Wonderful, that's great. So thank you so much for the opportunity to present today. And Jaya, if you could just go on the the first slide. So today's talk is about using real-world evidence and using real-world evidence to assess effects of drugs in clinical practice outside of the setting of clinical trials. And so I thought an exciting example would be an emerging drug safety question with tofacitinib. And these are drugs that are commonly used in treatment of rheumatoid arthritis, but signals from safety trials indicated that tofacitinib might be associated with risk of cardiovascular disease. Next slide, please. And here are our disclosures, and this study was conducted at the Brigham and Women's Hospital at the Division of Pharmacoepidemiology and Pharmacoeconomics. Next slide, please. So just to begin with this slide is showing the hierarchy of evidence in health research or clinical medicine, with randomized controlled trials as the gold standard of evidence. And the reason for this is that, of course, randomization achieves balance in regards to measured and unmeasured baseline covariates. And at the bottom, you can see that in essence, we have the observational studies. These are cohort studies and case control studies and cross-sectional studies. And these are studies where, in essence, the patients are not randomized. So you do not really achieve this balance in terms of the baseline covariates, both for unmeasured covariates. So here in these types of designs, we try to adjust for systematic differences between patients in one exposure group versus, for example, a comparator group. Next slide, please. However, clinical trials do not answer all questions. So after drugs have been approved based on evidence from clinical trials, there are still major gaps in knowledge. So, for example, we know that clinical trials in oncology and in cardiometabolic diseases underrepresent older patients or frail patients, patients with multi-morbidities or ethnic minorities. Next, please. In addition, a lot of these trials include composite endpoints. So, for example, in terms of cardiovascular clinical trials, the the major endpoint that you see is typically MACE, which is a composite of ischemic conditions and cardiovascular death. And similarly in oncology, a lot of the times that we're not focusing on one endpoint. We focus, for example, on disease-free survival, which is a composite of recurrence and cancer-related death as well. Next slide. In addition,